All right, great. Hello, everyone. Good morning, and welcome to the first workshop on AI for 3D generation. I'll keep this pretty short. I think the speakers will be more interesting than me. Just wanted to give some context for the day and go through a little bit of logistics. So first of all, though this is really the first iteration of AI for 3D generation workshop, it's actually the second iteration in spirit, I guess. We had this AI for 3D content generation workshop last year at ICCV 2023. So you can go look at that for more similar content. And first, I wanted to thank all of the organizers for putting in the hard work to get this ready today. So a special shout out to Despina, who is joining us remotely today, but did a lot of the heavy lifting to really make this workshop possible. And in person today, we have George, me, Davis, and Amlan. So if you need anything during the workshop or have any issues, feel free to grab one of us and we can figure it out. I also wanted to thank the program committee that was able to review and go through all of the papers submitted and make sure we have a really high quality program, especially for our poster session later this afternoon. So just to give a little bit of context of what we wanted to get out of this workshop, this is really motivated by this ubiquitous need for 3D content. And this comes across many modern applications. We have simulation, especially in robotics, like autonomous vehicles, in games, films, virtual and augmented reality. There's this requirement for really high quality 3D scenes to build this virtual world. We need 3D objects to place in the world, and then humans, of course, to populate and dynamically move and interact with the objects even. And we also have many applications that focus specifically on digital humans, where we need these realistic and interactive characters that may interact with the user. Now, the big problem here is this is very time consuming and costly to build all of this content manually. So what we'd like to explore in this workshop and discuss is recent approaches and possible future directions for generating really realistic, high quality 3D data and content at scale. Because we anticipate that having these generative models, using these AI models that can reliably synthesize meaningful 3D content and be controlled as well, robustly controlled by artists and easily work into their workflow. This will really revolutionize how artists and these pipelines, these content pipelines will work. So in a little more detail, the kind of topics we'd like to discuss today through our speakers are what are the best representation to get 3D objects that are high quality in terms of texture and geometry as well, but also have this intuitive and robust control that they can be easily integrated into artist workflows. We also need realistic humans to interact with those objects, and this all needs to go in some 3D environment where we can hopefully manipulate the appearance, scene elements, as well as their spatial composition. So how all of these things kind of come together. And then humans moving around in the scene need to move dynamically, plausibly, and interact with the objects in scene. And then also at a higher level, there's a lot of ethical implications and ethical challenges from how an artist kind of works into these workflows with the AI models, and how privacy, likeness, these kind of things work into it. So hopefully we'll discuss some of that today as well. So to talk about these topics, we have a really stellar lineup of keynote speakers that you'll see throughout the day, both from industry and academia as well, to give us their perspective and detail the latest work in this area. We also have several spotlight talks, which will be more of early career researchers that have already contributed impactful work to 3D generation and content creation. And finally, in the afternoon, in the same building, I think we'll have this poster session with 28 different posters that explore a really wide range of topics in this area. And that'll be from 3:30 to 4:30 this afternoon. And we're at a specific poster slot. I think all of the posters for the workshop are in the same area. So we're poster 178 through 205, and you should have, if you're an author, you should have received an assignment already. If not, feel free to let us know. We can tell you where to be. So yeah, in conclusion, here's the whole schedule for the day. This morning, we have a series of keynotes and spotlights. And then after lunch, have more talks followed by the poster session. But I think it's a very exciting lineup, and we're looking forward to the day. Thank you. So our first speaker will be Andrea Vidaldi, and George will come up to introduce him.
All right. I don't think there would be a better way to start our workshop than with Andrea Vidaldi. So Andrea is a professor at Oxford University and a research scientist at Meta. His work has been recognized with the Best Paper Award at CVPR 2020 and with 2 more Best Paper Awards from BMVC. And for all of us in computer vision, we are grateful for Andrea because he's the OG open source software contributor in our field, like all the way back to the VLFit library. And Andrea has made important contributions in unsupervised 3D reconstruction and in generative reconstructions of 3D objects and 4D dynamic scenes. So we're very excited to start our schedule with Andrea. And Andrea, you can take it away.
All right, great. Thank you. Okay, let's see what this works. Maybe. Thinking about it. There you go. Okay, excellent. Okay, it's a pleasure to be here, and thank you very much for introduction. Also, let me see whether my mouse works at all. It's hard to say. Probably don't see it. Okay, so I will not be able to indicate, unfortunately, but I'll try to do my best anyway. All right, so what I want to talk to you today is some progress we have made in 3D generative AI in the past year or so, both at Oxford University as well as in Meta. All right. Now, before, so the topic we're going to talk about today is mostly text 3D. All right. So what I mean by that is our task is, given a textual prompt like Viking axe, is to come up with a corresponding 3D model of it. All right. So the input is text and the output is a 3D output. There is a related problem that we're going to use a lot as well, which is image to 3D. So instead of starting from text, we may also start from an image. And then from that, we can produce a 3D object. All right. And one thing you might want to use this to solve the first problem is to just take the text. I'm not in a Zoom call. Okay, we have our first technical problem. Just a second. It looks like I need to connect with Zoom call here. To which address did you send it? In the calendar. I don't have it. Sorry, guys. Can you send it to vedaldi@meta.com? Apologies. So for the next speaker, make sure you have Zoom installed and running. Apparently, that's a thing you need to do, which I didn't realize. Not yet. Is Vedaldi@Meta, right? The work. Yeah, there you go. Okay, let's try this one. So I should just share screen, right? And join also with audio. Okay. All right. Here we are. Can you see that? Okay, apologies for that. Is the audio fine? Everything's fine on Zoom? Okay. So I suppose maybe I should bring it up a few slides. And actually close this and that. All right. Yep. But now you do. Okay. All right, apologies about that. Let me start again. So I'm going to talk to you about some progress we have made in 3D generative AI. And what I mean by that is mostly text to 3D. So starting from a textual prompt like a Viking axe, we want to generate a 3D object. Or there is a related problem to that, which is image 3D. So in this case, we start instead from an image, and we want also to produce a 3D object in response. And of course, you can see how you may be able to use the second problem to solve the first, as long as you have a text-based image generator. Okay. If you think about it for a second, so obviously this is a challenging problem because it's very ambiguous. So you only have an image, or even worse, just a bit of text, then there are many different ways in which you can associate an object to that. So this task, this reconstruction task, if you like, is really a sampling task. It's stochastic, it's not deterministic. So what we want to do is to be able to sample a posterior distribution. So let's call our 3D model M, the image I0. So what we want to do is to draw a sample from a conditional distribution P of M given I0, all right? Now, this is a problem that we know how to solve quite well now for a certain class of problems, in particular, image generation. And for that, typically what we use today are diffusion-based models. So just as a quick refresher, the way this works is you start from an image that you want to generate, and I want to train a model which is able to reproduce that started from text. So the way you do that, you take the image, you apply some Gaussian noise to that, so you get an image that has some of the information destroyed. And the training task you set is to learn a network, a generator, that takes the noise version of the image and produces back the clean version of that. All right. And not only that, but you also condition this generator with the additional information you have, for example, the textual prompt. Now, why do we do this? Well, one reason is that this is really, really very good at learning on a large scale. So you can learn this from billions of images, which are weakly structured. All you need is are some captions, and these captions you can also get automatically using some captioning system. Now, this is great because you can essentially go on the internet and learn from, say, 1 billion images. And this is really also crucial because we want to be able to interpret any image or any prompt which is given as input and still produce a reasonable result. So we want our methods to be open-ended. And this is difficult, very difficult to achieve if your training set is not large enough. Now, this is great. And in principle, you could take that and extend it to 3D. All you would need is a equivalently large collection of 3D objects with the textual prompt or maybe image prompt. And this is where things don't go so well for us. The problem is that we do not actually have such a large collection of 3D objects. So what are we going to do? So we have a technique that can scale up to billions of images, but we do not have billions of 3D objects to train this from. So what we usually do is to co-opt a pre-trained image generator, right? So we start from an image generator, say Stable Diffusion, for example, or EMU if you're in Meta. And you fine-tune it in such a way that instead of starting from a prompt, maybe that starts from a textual prompt, maybe that starts from an image, viewpoint change, a camera. So I have I0 and C, the camera. And condition on that, you generate a new image or a new view of your object from a different viewpoint. So the reason why this is useful is that you can start doing that from a model which has been primed or trained from 1 billion images. And now a relatively modest amount of 3D data, you can condition it or tune it to be able to solve this new view synthesis task. Once you have done so, you can start from an image I0. You can apply your model to generate a bunch of other images or other views of your object. And now once you have the new views, and so far there is no 3D as such yet, well, you can run some reconstruction algorithm that, given the views, can give you the corresponding 3D object. Now, this is a very general blueprint. And if you look at the literature in the past year or so, many different methods have used this. So just to repeat, so this happens in 2 stages, if you like. First, we start from our prompt, single image or text, and the first multi-view generator produces a set of new views of the object. And then there is a second network, or maybe just some handcrafted mechanism that takes that and reconstructs a 3D object. And these 2 things can be run in sequence, or they can interact somehow in a loop. That depends on exactly how you do this, okay? So that's a general way we're gonna approach this problem. Now, you may wonder what are the variables here that make this harder or easier. So a crucial one is how consistent is this 2D model that generates new views of your object. So ideally, what you would like to do is to be able to sample n different views, I1, I2, In, condition on the view you have, I0, all right? But because of limitations on how well you can train this joint distribution, this joint sampler, what you end up doing is sampling something which is in between that, the joint, and the product of marginals, Pi1, Pin. That would also be not conditioned even, all right? So the thing that you can actually sample, depending on how well you train your multi-view generator, is going to sit in between this joint distribution condition on prompt to this product of marginals. Now, the least consistent you are, the more you approach the product of marginals, the harder it is to extract a 3D object from the images you sample. So in order to reconcile this inconsistency, you have options. So one thing is to use something like score distillation sampling, in which you try to iteratively achieve this sort of multi-view consistency that the 2D model doesn't quite give you. Or you can try to work with images which are not perfect, but you're training a network that can reconstruct a 3D object despite the noise. Okay, so you have these two options. But it's clear that the better your image generator, the more consistent it is, the easier is your life, right? So the simpler it is to actually sample consistent views and therefore also to reconstruct the object. So now here I'm going to give you some examples of models that appear in the past year or so that strike a different trade-off into these two axes: multi-view consistency and reconstruction effort. Okay, so the most simple is just you have a distribution that doesn't know anything about multiple views. So, and that would be the original Dream Fusion. Now, this means that this works, but you really need to pay a lot of effort in order to be able to reconstruct a sensible 3D object from that distribution. Then you can have something like Real Fusion, which is an extension we did soon after, which is at least conditioned on one real image, and that is a little bit better, but still is not multi-view consistent. Then there have been other works like 3D and 0123 that have taken this idea of generating multiple views conditioned on a camera, or at least a new view conditioned on a camera, that already give you better view consistency, and BDream that gives you several views at the same time. And in the process of building these networks, we have learned some best practices. And here I'm going to give you a few. So usually you start from a diffusion model, which is a UNet. And what they want to do is to denoise jointly more than one image, more than one view. So you can set up this as several denoising processes that happen in parallel. But the first thing we're going to do is going to extend this to take as input also our conditioning image and conditioning viewpoint. And the image, we're going to put that as input to the network, an additional channel to your noise, if you like. But we also condition that, we're also going to use that as a conditioning for all the layers using some cross-attention, all right? Then we also, the other thing we're going to do is we're going to set up some cross-attention layers between the different parallel streams in such a way that there is some communication between the views. And this is necessary to encourage the model to make it possible to actually learn this consistency. And this is well known, well, for a value well known, because this has been happening for about 24 months, all right? Maybe even 12 months, okay? 1 or 2 years. More recently, we have a paper in the CVPR where we have found a few more best practices. One is to use a different way of conditioning the camera, which is taken from light field networks, which is to use Plaque array modulation, and that gives you better control of the viewpoint, and that actually really does help in achieving better and more consistent results. And the other thing you can do is, if you want to get views which are more consistent, you can use a very simple trick, which is to use the same noise, the same Gaussian noise applied to all the different views. Because these denoising networks are continuous functions at the end of the day, then this tends to produce results which are already more consistent between different views when it comes to hallucinating these different aspects of the object. And if you do that, you can get results like those, where this is called free 3D because there is no 3D model underneath. This is just a 2D model which is being fine-tuned to generate different views. And you can see that, yes, it seems like, it looks like it's 3D, but this really is not. Okay. And so this is free 3D, and it's a little bit better on this axis, multi-view consistency, reconstruction effort trade-off. But then if you want to get even better, what you can do is start not from an image generator, but start from a video generator. So that's it. This is what we have done in IM3D. So this is a version of Emu Video, or a model in the Emu class that was trained to generate multiple views of an object as if this was a little video, turntable-like video. So the camera goes around. It's almost like you get a little animation, as you can see here on the slides. And it makes sense that if you were to start from a video generation network instead of image generator network, then this network would actually have already some experience or some understanding what it means to change viewpoint. And of course, there are more recent model like Sora that makes that quite apparent. So the idea here is that if you start by fine-tuning a video generator for this solving this task of generating new views, then you can get better results, more consistent results. To points where you can be quite lazy in the way you actually do the 3D reconstruction in the end. So here we'd use Gaussian splatting. So everybody knows about that now. So you represent your 3D scene as a collection of color 3D Gaussians. All right, so that's your scene. Of course, these Gaussians in practice are much smaller than that. So you can think of those as three-dimensional pixels. And then we have a differentiable rendering function that takes this collection of Gaussians G, takes the camera viewpoint CI, and then can generate a corresponding views I hat, all right? All you do is you take that, compare that to the view you have as input, could be ground truth, it could be generated in our case, and then you just optimize your 3D Gaussian collection to fit those views, and off you get some 3D model. It's a bit more complicated in practice, but that's at the high level is the idea, all right? And these are the kind of results you can get in this case. So here we start from videos that are generated using this fine-tuned version of Minimoo video. And because these are actually quite consistent, then we can just apply 3D Gaussian splatting to get corresponding 3D models, which look quite reasonable. Now, if you look carefully, you will see that the 3D models are not completely perfect. And the reason is that the multi-view consistency of this video model is still not completely perfect, but is already quite good, all right? And the advantage is that you don't need to do any score decision sampling. This is really, really very efficient. So in about a couple of minutes, basically you can get your problem solved. Now, there is another way of doing this, which is to use maybe less views, or fewer views, or maybe less consistent views, and train a better 3D reconstructor. So an example here would be large reconstruction models by the folks in Adobe. These are great, but they're really powerful. They can do a very good job of reconstructing your object from inconsistent views or maybe few views. But the issue with that is that it takes forever to train these models. It takes 385 GPU days to train one of those, okay? This is fine if you're Adobe, if you're in Meta, but if you're in Oxford, this is actually quite annoying because you don't have that kind of GPU power. So what we did in Oxford was to try to develop methods for 3D reconstruction for few views that were actually much more efficient. And to do that, we introduced the splatter image. So this is also presented here at CVPR. And it's a very basic or simple method that actually is surprisingly efficient and effective. So what we do here is we use Gaussian splatting, but we train a network to do this construction quite fast. So we start from an RGB image. Then we have something like a UNet that takes that and produces another image as output, but this is not an RGB image. Now, each pixel has attached to that a bunch of channels which represent corresponding 3D Gaussians, okay? This is a pixel-oriented version of 3D Gaussian splatting. Now, just to clarify what this actually means, so here's your camera. So you have a camera center, you have the image pixels. And then what we do is with this UNet, we map each pixel to a set of parameters, sigma, mu, capital sigma, RGB plus, and delta. So what these are the opacity of the Gaussian, the mean, the location of the Gaussian in three-dimensional space, the shape of the Gaussian, that would be capital sigma. RGB plus would be the RGB color of the Gaussian, or maybe spherical harmonics if you want to have that. So you can get view-dependent colors. And then you also get an off-the-ray displacement, which is actually quite crucial. So what do we mean by that? So we get depth. So primarily the Gaussian we get is some distance along the ray, all right, some depth along the ray to be more precise. But we allow the network to displace the Gaussian off the ray that we get, okay? So it means that the Gaussian does not actually have to sit on the ray, and this is actually crucial. Now, of course, this happens for all the pixels in parallel, so you get this collection of Gaussians that represent or approximate your object. So you see here applied to the Code3D dataset for the class teddy bears. So to the left of each pair here, you see the input image, and to the right, you see the 3D reconstruction we get. This was obtained using this UNet, estimating 1 Gaussian per pixel. And you see something quite striking that you can reconstruct the back as well of the object, not just the front. So not only the pixels which are visible, or the points which are visible are reconstructed, but also the ones which are not visible. And this doesn't work just for one class at a time. Eventually, we trained it also on Objaverse. And then here you can see it applied to Google scanned objects. So you transfer between data sets, and you don't need to make too many assumptions what kind of objects you're looking at. Now, you may wonder, how can this work? Because at the end of the day, this is very much pixel-oriented. So here you see a bit of analysis of what the splatter image actually does. So you see the input image to the left. Sorry for the low resolution. This was a low resolution experiment we did here. Then you get the first layer you see there is the opacity. So you see that where it's black, then that Gaussian is switched off. So it doesn't matter that you have more Gaussians as you need. The network can decide to just throw some of those off if you don't need them. But then you also see something striking. So you see almost like a doubling effect where certain features of the object are replicated. Actually, that's your model using some of the Gaussians that would otherwise belong to the background to try to approximate parts of the object that are not visible in the image. So you see there at the top for the wheel of the car. So we're modeling the wheel, which is not visible. That's indicated by the arrow. And you see that the displacement vectors there actually make it possible to take that Gaussian on the ray and displace it such that it falls in the right place to approximate that part of the car, all right? And the same happens there for the chair, where we do not see one of the legs, but these pixels that wrap around the leg are enough to be able to reconstruct that part, which would be otherwise missing. And the point of this is that this gives you a reconstruction quality, which is very competitive with state-of-the-art, but it is much faster. So you can render very fast. Okay, this is Gaussian splatting, so you can render this as basically 600 FPS. You don't really care about that too much, though. What you care about is that the reconstruction is also fast. So this reconstructs at about 40 FPS. But most importantly, especially if you're not in a big company that has thousands of GPUs, this trains fast. So this was trained on 7 GPU days. And even so, it was competitive with state-of-the-art reconstruction quality. More recently, we have extended that to scenes. So of course, you don't need to just do 3D objects. You can also do 3D scenes. So here we go from a single image to a Gaussian splat of the scene. We call that Flash 3D. This is just an archive as of a few days ago. And I don't really have much time to discuss that in detail, but this is suffice to say that one striking thing we were able to get here is by starting from a state-of-the-art monocular depth estimator network, we could fine-tune that if you like, or extend that and fine-tune it to get state-of-the-art UV synthesis for scenes, okay? Again, very fast. You can train that with university-level resources, just a couple of GPUs for a couple of days. And we get something that can get state-of-the-art results, say, on real estate 10K for this UV synthesis tasks. But then you can take that model, apply it to Tonkiti, which is a very different data set, and you still get state-of-the-art results, or at least comparable to state-of-the-art results, okay? So this is really powerful. And part of the reason is that you can really start from a very good monocular depth estimator and extend it to be able to do that. Okay, so that was for the first part of the talk. In the second part of the talk, I would like to dive into connected but slightly different topic, and that's Meta 3D Gen. So this is something we didn't show before, so we're introducing this at CVPR here today. And this is about a year of work of us trying to tackle the text to 3D problem in Meta, all right? So this is not university resources. This is what you get if you're in Meta. All right, so the task we set out to solve here was to try to ask ourselves, what does it take to get pro-level 3D generation, all right? I'm not gonna say that we got there, but our goal was to try to get as close as possible to that. If you think about 3D generation, it's actually really hard because it's not just about generating a bunch of pixels as like an image generation or video generation. You need to think about a bunch of factors which are actually really hard to achieve together. So you need to have high quality shape, high quality textures, obviously, high quality control. Again, that's in common with image generation or video generation. But then you also need to get high quality materials. Maybe you want to get part-oriented generation. So you get a model which is decomposable. You want to get very good UV topology and quality. You want to get very high quality mesh topology. You want to get rigging and so on and so forth. And all of these are things that professional 3D artists require you to do before they go and like, yes, we can use this in a game, all right? And here we're gonna focus on these 4 characteristics, but of course the rest is something else you need to work on, all right? So we're gonna focus on quality as well as materials. So let me talk about a little bit about the materials first. So what we do here is to use physically based rendering, or PBR. So what this means is that we don't estimate just the RGB color or shapes, but we estimate the albedo, which more correctly should be called base colors for the family of BRDF, bidirectional reflex and distribution functions we use here for modeling. Anyway, so that's albedo, the intrinsic color of your object, base color more correct. We also estimate the roughness and the metalness. Okay, so this would be a pug made of metal. So it's a dog which is supposed to be made of metal, so you see that the metalness is really high there. Okay, so we want to have that kind of control in our textile prompt, and we want to be able to generate those properties. So once you have that, what you can do is you can relight your object. So you can see here the same 3D object that has been subjected to different environmental illuminations. And you can see that the response is actually realistic. The reason is that, of course, we're using physically based rendering to get there, and this is possible because the model is estimating the necessary parameters while generating the object. So here you can see some examples of control. So we have a cat made of shiny plastic. So you can see here that the roughness is really low. That's because the object is shiny. The metalness is also really low because this is not metal, it's plastic, right? Base color in this case was decided to be black, except for the eyes, which are yellow. And see here, so you see here on the left how this is being shaded eventually. Here we have a cat which is made of shiny silver. So now you can see that it's still, the roughness is still low, but the metalness is now high because, well, it's silver. And this is a cat made of rock, all right? So this is as high roughness and low metalness, obviously. And finally, a cat made of rusted iron. So this has both high roughness and high metalness. And you can see that this makes sense. So once you have this control, then the shaded object actually looks the way it's supposed to look. Now the question is, how are we going to get there? So here is our usual blueprint. So we have a prompt, a cat made of rock, we have a multi-view generator, and you have a reconstructor network. Now our reconstructor network is supposed to be able to reconstruct also albedo, roughness, and metalness. These are things we didn't have before, all right? So how would we get there? So we have two options here. One would be to try to take our multi-view generator and extend it to generate albedo, roughness, and metalness, which makes it quite easy for the reconstructor to extract those channels. So here I say that the arrow that goes from the 2D views to the 3D reconstruction is deterministic. It's a bit of a lie. It's almost deterministic, but there is very little ambiguity because you are providing enough information with your 2D model, all right? But the 2D model, on the other hand, has a very high statistical gap between natural images. Remember that this is trained from, say, EMU images. So this didn't see metalness or roughness during training from 1 billion images. So now if you add them, when you want to learn to generate that kind of data, when you want to get this to work for 3D, then that's a big statistical gap. And that's actually quite hard for the model to learn that without destroying its ability to generate nice looking images. So the other option is you don't care. So you just generate standard shaded image with your 2D model, and then you offload everything else to your reconstructor network. Basically, you task it with reconstructing metalness and roughness automatically as well as intrinsic image. But now that's hard because this task is highly ambiguous. So it's very hard to go from a shaded image to the individual components. So this is a non-deterministic mapping. So we thought about this for a while and then eventually come up with this, which was the best solution for us. So what we do is we task the multi-view generator with producing two kind of channels, the shaded channel as usual, and the albedo channel, which is just that with the shading removed, okay? But we do not try right away to generate metalness or roughness. And instead we task the reconstructor network to do that reconstruction for us, starting from albedo and the shaded version of your object. Now, this is fine or better for us because the statistical gap is smaller in terms of multi-view generation compared to your training data, which is billions of internet images. But also the reconstruction task is deterministic enough, okay? It's not deterministic again, but is close enough to be deterministic that you can get good results. And so here you see the difference. So this is a shaded reconstruction, 4 views, all right? That's what we do. And this is albedo. So again, shaded, albedo. They look very similar, they are. But the albedo version, well, doesn't know how to have the shading, all right? So here's an example of what you get. If you try to do the decomposition using a reconstructor, which only uses shaded multi-view inputs as input, okay? And you can see that, yeah, you can do a good reconstruction of the shaded version, maybe also the albedo, but the metalness or roughness are off. So here you should see that the bear has certain parts of the armor that are supposed to be metallic, but now all the object is actually turns out to be metallic in this case. So that's wrong. But if you put as input these two versions of the bear, the shaded as well as the albedo, then the 3D reconstructor is able to do a much better job and figure out what is supposed to be metallic and what is supposed not to be metallic. Okay. So that's one thing we did. Another one thing we did was to work on the reconstruction architecture. So you go from 4 views and then you have a choice of constructing a 3D-dimensional representation of that. That could be a neural field, could be maybe using some volumetric representation, triplane, or it could be Gaussian splatting. What are you gonna do? So if you want to follow the trend, maybe you would use Gaussian splatting, but I would say that there are pros and cons in both choices. So Gaussian splatting is really fast, as we have seen before, but when it comes to extracting nice meshes, nice 3D surfaces, it's actually not that great. I know that there are works and we're improving that aspect of Gaussian splatting as well, but for us, it wasn't that great, okay? And also is a bit more prone to local optima when you train this. So the alternative is instead to train a Gaussian splat, to train to generate a NeRF, but that tends to have a very large memory footprint, which makes it very, very hard to use pixel level losses. And so rendering all the pixels every time can take gigabytes of memory, and that really doesn't bode well when you want to have large batch size when you train your reconstructor. On the other hand, it gives you much nicer 3D surfaces when you do the reconstruction from that, and also better convergence we found. So so again, this is NeRF. So NeRF needs to take these samples along each way to do the rendering. And if you implement that in a naive way, when you do backpropagation, then all those samples get materialized in the memory of your GPU with corresponding backprop calculations attached to them, if you like, or intermediate calculations that can really blow up the amount of memory you need to be able to do that. So last year, we have introduced this additional module that is called light plane kernels that implement effectively rendering using NeRF in a way which has a memory efficiency which is comparable to Gaussian splatting, all right? And in a certain sense, uses some of the same tricks, although there was concurrent work. But at the end of the day, there are some tricks you can do to make backpropagation memory efficient while rendering high resolution images using these models. And now this is also possible with NeRF. You use these kernels, which do the calculations in a sort of fused manner. Okay, and here you see the difference on a log plot. So the blue line is light plane kernels. You see the image size on the x-axis and the amount of GPU memory which is being used up on the y-axis. So this is really great because now we can use really NeRF in place of Gaussian splatting and still be memory efficient. So we can learn with high resolution images and pixel level losses, which we couldn't do otherwise. Another thing we did was to switch NeRF to use SDF functions. Again, implementing these kernels, the vol.SDF version of SDF that allows you to render as if that was a radiance field with an opacity function. And you can see here the difference that you get in terms of quality of the 3D shape, which is reconstructed. So here, put everything together, you get your 3D reconstruction. You fit your mesh very simply using marching cubes, marching the 3D, I should say. You get a UV map using XAtlas. That's also something that should be improved in the future, but for now, we just use that. And you get a texture. Another thing we did was to work on the texture quality. So here you can see 4 images, in this case of a ground truth object popcorn box. And you can see that our network is able to reconstruct a UV texture map once you have the UV mapping. Then you can sample the 3D volume to get that. And you can see that you get a texture which is okay, but it's not perfect. So you can see it's a bit blurry. So this was obtained by taking the mesh and sampling the 3D volume to determine the color of each UV element in texture space. An alternative way of doing that is to go back to your views, which are actually sharp, and back project them onto view space. But this will give you something which is incomplete and also not completely consistent between views. Because each views, yes, will give you sharp information, but not every pixel is visible in every view. And also you might have inconsistency, which are due to the fact that those images in practice will be generated, so they will not be perfect. So what we did was to introduce another network that takes the first kind of texture and for the projections, and using a transformer, reasons about which pixels are essentially, or which places should be used to determine each point on the UV texture to do the best job possible, and also fixes some of the mistakes that you might be doing in that case. And here you can see the difference between before and after, which is quite striking. And so here you can see again differences with and without the texture enhancer. You can see that now we can read what's actually written on the box once you reconstruct it. Details here on the IRDB, which becomes much sharper, much closer to the ground truth. Again, this is a reconstruction task, not generation task. And here you can see also this working with complex geometry. I put everything together, and those are the kind of results you get. So you get nice, fairly high resolution reconstruction with good quality albedo, metallicity and roughness, good quality geometry, et cetera, et cetera. So here's a few more examples. And because, in Meta, you need to have some llamas around. So here you can see some physically based llamas where we can change the illumination. And because this is physically based rendering, then this stuff reacts correctly to your changing light. In the last 2 minutes, I'm going to improve the results a little bit further. So we're happy with this, but not quite. So we really want to get something state of the art. And our texts were good, but not quite good enough. So then we went back to the drawing board, and what we did was to develop, in fact, actually we developed this in parallel to tell you the truth, a model which can generate a much better, high resolution texture for an existing 3D geometry. And this is really crucial. So if you try to generate a texture, but you already know the shape of the object, it turns out that you can do a much better job at it. This is kind of intuitive, but it's actually very useful because now you can take that network that does this 3D condition generation of the texture and get much better high quality outputs. So how does this work? So you take the input 3D object, you take your prompt, in this case, a brown hair. But what you do is you also render 3D features on the 2D views. You put everything here in another transformer, essentially, which is a fine-tuned version of another EMU model or model in the EMU class. And off you get new texture views or views of the texture object or views of the object as if it was textured, which are actually better than what you get without conditioning on the 3D shape. And for conditioning 3D shape, it's actually very important which kind of information you put in. You could put in depth. Actually, it turns out if you put in position maps and neuron maps, it works a lot better because you get information which is, because the position maps more absolute, it's not relative, but absolute to the reference frame of the object. And in the case of neuron maps, because it really shows you details of the 3D shape you might be missing if you were to look at depth only. So here's a simple example of what you can get if you take a 3D artist generated model of butterfly and you apply these reconstruction network. So here you see the text prompt, a majestic monarch butterfly, and here you go to your texture. And then you can change that into, say, well, a magical butterfly, arcane sigils on its wings, sparkling glitter on its body, all right? And that's what you get. So you can get quite poetic, but the point is that you can, given the same 3D object, you can replace the texture, stylizing it the way you want. And of course, you can use this to enhance the texture you get originally. This brings me to the last few slides, where I want to show you the final results that we got. So this is the complete package. So this is Meta 3D Gen. And this is Meta 3D Gen rotating. So you can see a collection of a few sample objects we got. Those look quite nice in terms of shape, materials, and texture. Again, the texture are quite high resolution 4K. You don't get Janus effects. You don't get any of those things because, well, for a bunch of reasons. For example, because the texture are conditioned on this position maps, which really help with that. And here you can see that you can also stylize this. So this is in style of Christmas. And now while we rotate it, you can get the horror style instead. And the next trip is going to be, forgot what. Let's see. Starry Night. This is a little bit cheesy maybe, but it really shows how the model is doing a good job of capturing the concept and still trying to match it, show it on top of these objects with very sharp boundaries and very nice looking textures. And here we get steampunk, for instance. Okay, so this kind of things you can get. So we compare this to competitors, commercial competitors like Lumen, Meshi, and Rodin in using user studies. Here we found crucial to use professional users or 3D artists to do the evaluation because they're much better able to judge whether your generations are sensible or not from the viewpoint of the pro quality. And yes, so in most cases here we win. Competitors are strong though, so it was not easy to beat them, especially we beat them when it comes to a more complex kind of prompts. And you can see that here. So we divided the kind of prompt based on simple object, characters, and then a combination of objects and characters. And as you get prompts which are more and more complex, then the better we do compared to competitors, okay? Some cases where competitors will still win out, although not in the majority of cases. So here is the results you get with Luma, for example. Here are the results you get with Meshi. And we can put everything together here. And I know that it's very difficult to see that at this level of zoom. So I'm going to zoom in on some details here. And you can see the difference when generating, for example, the dinosaur face or the pig face, or the pig there, or the raccoon. And, you know, Meshi does a very good job at high resolution texture, but they're a little bit messy sometimes. Luma does a very good job all the way through, but maybe these shapes are a little more cartoonish. And we get a different compromise, I guess. A bit more realistic shapes, very good texture, very high realistic textures. If you want to know more, the papers will be on arXiv, hopefully later this week. There are 3 papers here, one for integration, one for the 3D asset generations, one for the texture generation. And finally, just a few thanks for the Oxford team. So you see here everybody that has contributed to this and other works that couldn't present today. Also our sponsors, the Meta Gen AI 3D team. Most of us are in London, Tel Aviv, and Paris. Here they are. And then conclusions, finally. So what I wanted to show you today was a bit of progress we have made in the past year or so in 3D generative AI. So I'll show you some best practices. We want to also achieve better control, which we have done by adding, for example, the ability of controlling materials. We focus really on quality, try to have high quality, nice looking textures, which also have PBR material decompositions, and also efficiency. So I mentioned that we have splatter image and now Flash 3D that can allow you to do 3D constructions really, really quickly. And you can think that you can combine those techniques with image-based reconstruction or generator networks to actually get to 3D generation as well. And so I think this is going to be very useful because, again, allows you to do experiments in this class of problems, even if you are not have company level resources, just university level ones. Okay, that's all. I hope that was more or less on time. It says 35 minutes here. Apologies for a slight delay due to the technical problems at the beginning. Thank you.
Thank you very much, Andrea, for the very impressive talk. If you have any questions, you can come at the center. There is a mic. If you want to ask any questions, we have time for 1 or 2 questions.
Oh, okay, it works. Could you give a quick intuition to why this multi-view generator works? Like the idea of spatially tiling the views feels like magic. I assume one reason is the receptive field of the transformer covers the entire spatial domain, and it...
Yeah, correct. So, I mean, you get these self-attention layers, so they can look within the grids that you are generating and find out correlation between different views. You can implement this differently. You can stack the views along the channel dimension and do cross-attention different ways. They're all similar, really. This is just one simple way of doing it, but it's not particularly magic, I would say. It's just the transformers can take a bit about anything as input and give you about anything as output, maybe. That's another way of looking at it.
Okay, thank you. Yeah, I was hoping there is, it just feels like magic that just works out of the box.
I don't think it's magic. It's just being able to look between views using cross-attention, really.
Fair. Thank you.
Yep.
Hi. Firstly, great work. I had a question more around the temporal consistency of maybe an approach like this for dynamic objects in the scene. Is there any work being done on that front?
We have some works looking at that a little bit. I wouldn't say it's something I'm doing in a major fashion yet, but certainly some people in our team have been looking at dynamics as well. There are some works already out about that too. Yeah, you can. I mean, it's kind of obvious. The future is 4D, it's not 3D. If that's what you want me to say, for sure. Yes. And with this new class of high quality video generator models like Sora, and then everybody else is going to have a version of that, possibly even better in the future, then you can really see 3D and video generation converging into 4D, I think.
Good. Sounds good. Thanks.
Sure.
Hi, thanks for a great talk. I'm actually curious about the Meta 3D Gen AI. I remember you just showed us a lot of result for Tactile 3D and compare with Meshi and other baselines. And how about image to 3D? And can you share more about this part? Like, have you what's the status of Meta 3D Gen for image to 3D to 3D, and how does it compare to like recent like?
It's a good question. So I don't think we have direct evaluation of that. Okay, so in the paper you'll see that we have evaluations of how well the reconstructor works, starting usually from ground truth multiple views of an object, though. So we have comparisons against that, and that for sure works quite well. If the goal is to start from, well, maybe that answers your question, I suppose. But we're using synthetic data for those ablations, though. So if you have a data set of multiple views, and you want to know how well we're doing compared to competitors, then we will need to run a few more ablations. Yes.
Thanks.
Great. Let's thank Andrea again. All right. And our next speaker is Ruoxi Liu. I think I'm set up. So Ruoxi is a PhD student at Columbia University, working with Carl Vondrik. and he's one of the most prolific PhDs of this era. And also he's particularly famous for his 0123 work that is that people loved, both the method there and the name. Like we have seen so many papers following like similar names there. And Rossi is interested in generative models trained from large amounts of unsupervised data with the goal of generalizing and being useful for downstream tasks and applications. And I think that the talk today will be about some of these downstream tasks. So Rossi, you can take it away.
Thank you very much for the generous introduction. So today I want to talk about a topic I'm very excited about, which is 3D generation for physical intelligence. So there's no doubt that 3D generation has been one of the biggest topic in computer vision. This thing. Oh, this one. Got it. Okay. All right. Thank you very much. Yeah, so 3D generation has been probably one of the biggest topic in computer vision. We see exciting papers coming out pretty much on a daily basis. But if you look closer at these papers, most of them are motivated by applications for the virtual world, such as game asset creation or content creation. Well, we live in a physical world, and as of now, 3D generation doesn't have much impact on the physical world yet. So this is the question I want to ask today. How can 3D generation help us in the physical world? Specifically, I want to break out into 3 components. I want to talk about 3D generation that could help us for physical reconstruction, design, and interaction. So the 2 questions I want to answer today is, how do we build better 3D generative models? And how can 3D generative models help us in the physical world? So let's start with the first question. So if we look at the progress of 2D generative models, we can easily see that as we have better generative models behind the scene, we have better and better, higher quality, large quantity, high quality data sets, which is the unseen hero behind the scene. At the beginning, we only have small data sets like MNIST, and now we have Lion. So we have better and better, very impressive 2D generative models. So that's exactly what we did for the 3D side. We try to bring out and scale up data sets. So we introduced Objaverse XL last year, which is one of the biggest 3D data set in history of 3D, which is composed of 10 million plus high quality 3D assets, fully open source. So all the PhD students can download the data set and run it in their servers. And to put things in perspective, the small dot is everything combined before Objaverse, and on the right is Objaverse XL. And you can see that it's much bigger than everything combined before Objaverse. And ever since the release of Objaverse, we've seen a lot of work base their work on Objaverse XL and train their models on Objaverse XL. And we are very excited by the progress, and we expect to see more and more exciting works coming out of it. So 3 data sets are cool, but a constant question I've been having is data set scaling enough for 3D generation? Right? If you put things in perspective, Objaverse XL is the largest 3D data set, which is composed of 10 million plus 3D assets. But in front of the largest 2D image data sets, such as Lion 5 billion, it's still order of magnitude smaller. That is because 3D assets are intrinsically much more expensive to collect than 2D images. So that brings me to the next work I want to talk about, which is 0123, which to me basically is a tool to channel knowledge in the vast amount of 2D images into 3D. So 0123, as many of you know, is a novel view synthesis model. Conditioned on an input view of an object, as well as a specified camera viewpoint transformation matrix, 0123 could basically generate the novel view for you. Similar to Stable Diffusion, 0123 is a conditional diffusion model. And when trained on a lot of 3D data, such as renderings from Objaverse and Objaverse XL, 0123 display very impressive zero-shot generalization abilities. For example, it generalizes very well on impressionist paintings, works well on oil paintings, cartoons,
line drawings, and even sketches, which are traditionally very hard for classical 3D reconstruction or novel view synthesis methods. So we just briefly talk about, 0123 being a bridge to channel knowledge from 2D image data sets to 3D. What about robotics, right? Robotics is the field where data is even more limited, and it's even more expensive to collect data for robotics than in 3D. So that brings me to the second part of my talk, which is 3D generation for physical interaction. So we have a dilemma in robotic data today, which is a dilemma between robot data and visual data. So on one side, we have robot data, which is limited, but it's very useful for robot. Any skills learned from robot data can be directly deployed on the robot. On the other side, we have the ocean of internet visual data, which is composed of a lot of examples like a dog running, a person folding a cloth. It contains a lot of useful skills for physical interaction. So it's very diverse, but there's a crucial problem, which is there's a huge embodiment gap between the internet visual data and robot, because you cannot extract explicit robot actions from these visual data. And large companies like Google and Meta train visual foundation models on these visual data. So the important question to ask here is, how can we use the ocean of visual data, which is kind of unstructured, to help robot learning? I think we basically need an interface between visual data and robot control. So we introduce Dr. Robot, or differentiable rendering of robot. Given a pose, differentiable robot rendering could render a robot body, which is a pose-conditioned 3D Gaussian splitting of the robot surface under that pose. And sampling a camera perspective, we could differentiably render a robot image. And a gradient on the pixels of the rendered image can be back propagated into the control parameter space for optimization. Basically, Dr. Robot allows visual appearance of a robot to be differentiable with respect to the control parameters. Given a pose, we render an image, and this image can be input into visual foundation models such as clip or text-to-video models. And the control signal can be back propagated into the robot action parameters for control. I want to draw a connection here between Dr. Robot and 3D generation, a classical work in 3D generation, which is Dream Fusion. Dream Fusion basically optimizes a NeRF field with a text-to-image diffusion model. And this is exactly what Dr. Robot is. Dr. Robot is a NeRF, but for a robot, which is deformable. And if you render an image with Dr. Robot, you could interface it with a visual foundation model for optimization purposes. Same thing as Dream Fusion. So it's basically 3D generation, but for a robot. So before I go into a few applications of Dr. Robot, I want to briefly talk about how we achieve the differentiability of the rendering function. So we decompose Dr. Robot into three main components. With a pose, we input it to a forward kinematics model, just forward kinematics, which calculate the skeleton of the robot in a differentiable way. The second step, condition on the skeleton, we could use an implicit linear blend scaling function, which is used in graphics, to project the canonical 3D Gaussians to the surface of a robot under a certain pose. And at the end, we use an appearance deformation function to adjust the appearance of the Gaussians to make them look better and improve the visual quality. And this can be trained end-to-end by optimizing for the L2 loss between the rendering and the ground truth image. So after we learned this differentiable robot rendering model, we could basically use it to do a lot of different tasks. For example, here, we perform robot pose reconstruction from a single image or video through analysis by synthesis. And here shows the example. On the left is the original video, and on the right is our reconstructed robot and their poses, and as well as camera parameters. We could also perform visual model predictive control with CLIP. So here shows an example where we optimize for the joint angles, the 24-dimensional joint angles of shadow hands towards to optimize for the CLIP similarity between the rendering as well and the text prompt of victory sign. So you can see that as the CLIP loss goes down, we could control the robot, which is the shadow hand, to do a victory sign. This will be extremely slow and inefficient if you use traditional gradient-free optimization algorithms such as reinforcement learning or evolutionary algorithms. And we also could use Dr. Robot for robot control with a text-to-video model. When we fine-tune the stable video model on the ASU tabletop data set, we could prompt the model with a prompt, with a text prompt, like pick up the blue can, and the video model can generate a video of the robot executing that prompt. But because the video doesn't have actions, we could use Dr. Robot to extract the robot actions and replay that trajectory in a simulation or in the real world. And we could also use it for motion retargeting with a low-level point tracker from Meta. So in this task, we could basically transfer the motion from a human hand, which is my hand here, and we optimized for the transfer distance between the point tracks of the human hand and the robot hand in a differentiable way because of Dr. Robot. And we could basically perform the same action as a human hand, basically doing motion retargeting. So we talked about basically a differentiable rendering model for robot. What about policy learning? So before I go into detail that, I want to add a little bit of context here. So a visual motor policy is when you see an observation of an image of tabletop scene. A visual motor policy needs to generate a sequence of actions, basically motor actions, that the robot can then execute. For example, the task here is to scoop the bowl of beans to the other empty bowl. And behavior cloning has no doubt been one of the largest trends in robotics in the past year. What it is basically supervised learning of human behavior. You have lots of observations and their corresponding expert demonstrations for certain tasks. You basically, with this paired data, you can train a visual motor policy model in sort of a regression way, right? To imitate human behavior. So we introduced an alternative way to parameterize visual motor policy. Instead, we use video generation as an intermediate action representation. So given the same observation that we saw before, our model will condition on a tool. We prompt a video generative model to generate the plan of a person holding the tool to solve that task. And then we just 3D track from the generated video of the tool location. And we could basically use a robot to follow that track to perform the physical execution in the real world. So in a nutshell, we basically decompose visual motor policy into two components, dream and imitate. In the dream, we basically generate a video of a human doing the task, and imitate, we have the robot follow the trajectory of the tools in the generated video to perform the same task. Or as we call this framework, dreamitate. And here shows the dreamitate controls the robot to perform a rotation task of objects on the table. And these objects are all unseen by the policy. We could also perform scooping tasks, scooping one unseen granular media to an unseen bowl with a bunch of unseen destructors on the table. And we could perform sweeping tasks, sweeping particles towards the target. And we could also push shape into their target, which is a very challenging task because it requires multi-step planning. It cannot be done in just one planning step. And compared with our baseline diffusion policy, trained on the same demonstration data, you can see that our policy is able to generalize much better to novel shapes. So that brings me to the third part of the talk, which is 3D generation for physical design. I want to use, specifically, I want to talk about designing paper tools, which means using a robot, take paper as a material to design tools. Why paper, you may wonder? Well, paper is an attractive, recyclable, and useful medium for design. It makes a lot of useful tools in our society, such as paper bag, paper straw, paper filters, and is environmentally friendly for our society to make more tools out of paper. And we pick a very fun and interesting design, but still challenging design task of the design problem of a paper airplane. So if a human wants to learn to fold a paper airplane, we will think of a design, we'll physically fold it, we will throw it out, and we'll see how far it flies. And we repeat this process iteratively to basically learn what kind of design flies further, right? So the question here now is, can we replicate this process with robots? So to do that, we could parameterize the paper airplane design. We could have robots physically folded. We could have a robot arm to throw it out, and we can have camera to measure how far it flies. And this is what we built in our lab. So a robot will load a paper into the folding deck, and it will fold the right and left wing sequentially, and it will grasp a holder to stick on the paper to create a grasping point. And then a robot arm will throw it out. And at the end of this, a 2 top-mounted RGBD camera would track how far the plane flies. So now we basically automate the paper airplane manufacturing process, but there's still a problem remain, which is how do we learn to design the paper airplane? To do that, we adopted a optimization framework based on surrogate-based models, which is parameterized by a neural network. So the goal of the surrogate model is to learn how far each plane can fly given various paper airplane design. And after it's seen a number of trial and errors, it actually fold paper airplanes in the physical space and measure how far it flies. It learns a pretty good function. And we could basically perform optimization in the design space of the paper airplane to optimize for the travel distance. And here we visualize the learning process of the learning to design paper airplane. And you can see that as the robot gain more and more experience, it sees more different designs and how far it flies, it learns to find better and better designs. And at iteration 91, it basically find the best design, which flies over 20 feet or 6 meters. We compare our method against several baselines, including the classic gradient-free non-convex optimization algorithm, which is evolutionary algorithms. We also compare against a human participant subject to the same number of trials. And you can see that our method actually outperforms human participants by a little bit. We also apply our design framework to a practical task of designing Kirigami gripper, or basically gripper that's made of cutting paper. Prior work on Kirigami gripper relies heavily on physical analysis, which is time-consuming and expensive. We basically apply the same automated design framework that we apply to paper airplane design to Kirigami gripper. And we built a physical system to manufacture the Kirigami gripper by using 2 robot arms and a Quicker Maker 3 machine, which basically cuts paper into certain shapes. And we also use 2 load cells to measure the horizontal gripping force of the gripper as a reward signal. And as you can see, with only 100 trials, our method is able to learn Kirigami gripper design that outperforms all the baselines. At the end of the iteration, the optimization cycles, we obtain a gripper design that's able to exert 0.93 Newton of force, which is equal to the weight of 4.5 strawberries with only a piece of paper. And here we show our design gripper grasping a strawberry. And here we show our design gripper grasping various objects we can find in our lab. If you want to know more detail, please go to our website. And as a disclaimer, we recycle all the paper used in the experiments. So this is basically automated design framework based on robots. To apply this framework, we can actually use it to design useful tools in our physical world by incorporating priors from 3D generative models. And to do that, we basically require a 3D printer, which prints out the geometry of the tool in the real world and have a robot to use it. We could basically apply the same surrogate-based optimization framework. However, there's a problem, which is 3D printing is kind of slow. So to do this framework, to accelerate it, we probably need a farm of 3D printers, which are kind of expensive. So it's also kind of the reason I haven't been able to convince my advisor to pay for it yet. So if there are industry funders in the audience, please contact me during the conference. I personally believe that this design framework is able to lead to marvelous tool design that's beyond humans' imagination. So that brings me to the last part of the talk, which is 3D generation for physical reconstruction. So we want to solve the problem of 3D reconstruction of completely occluded human. For example, in this image, there is a boy that's running out of the car and that's completely occluded by the car in the front. That's a very physically impossible task, right? But it's very important for autonomous driving to detect this kind of incident to prevent accidents. There would be a way to make this possible if the car in the front turned into a mirror. So through the reflection of the boy in the mirror, we could basically see the 3D location and body information of the boy. And turns out this is actually exactly the case in the infrared spectrum. So here's the side-by-side comparison of a normal camera and a thermal camera. And you can see that there's no reflection of me walking in front of the car in the normal camera, but there's a clear reflection in the infrared spectrum. So why is this? Where does this reflection come from? And can we use it to reconstruct 3D human? So it actually relates to black body radiation, which says that every object beyond absolute 0 degrees Kelvin emits thermal radiations. Hotter objects emit radiations with shorter wavelength, and as they cool down, the radiation become longer wavelength. And with a constant body temperature of 37 degrees Celsius, human actually emits long wavelength infrared light with a wavelength of about 9.5 microns. That's why it's far beyond visible light spectrum, which is why we don't see human glowing in everyday environment. But with a small thermal camera like this, you're able to see human as a light source. So that's basically the title of the paper. Humans are infrared light bulbs. So as you can see here as a side-by-side comparison, when you turn off the light in the normal camera, you don't see human anymore because human reflects visible light in our environment, but you can still see human in the thermal spectrum. And cats are also infrared light bulbs. And this is my cat. And many objects, because the wavelength of the light is longer, they tend to reflect in a specular way instead of diffuse. Such as here, a glass is transparent in a normal camera spectrum, but in a thermal camera, they're very reflective. Same goes to the whiteboard. You don't see any reflection in the normal camera, but you can see a clear reflection of my body in the whiteboard. So based on this observation, this interesting physical phenomena, we propose a method based on analysis by synthesis to reconstruct human body and 3D objects in the environment. So to do this, we basically first sample from a 3D generative models as latent space. We use 3D generative models of objects as well as 3D generative models of human, which is SMPL. We basically sample initialization of the scene, and we write down the differentiable rendering of reflection function to basically differentiably render the reflection image as if it's captured by the thermal camera. And we basically optimize this render image towards the actual observation of the reflection. And at the end of the optimization cycle, we basically can reconstruct both the human body and the object, their geometry, as well as their location and orientation in 3D. And here shows the results with a single RGB image as an input, as well as the thermal image in the same view. We can reconstruct both the geometry of the car as well as the human body, their body pose, their location and orientation, which is consistent with the ground truth scene captured from another camera's perspective. So that concludes my talk. I talked about 2 works for 3D generation and applications of these work in physical interaction, physical design, and physical reconstruction. I personally find this to be a very exciting space to use 3D generation in the real world. I hope this inspires more future work in this domain. And at the end, I want to thank all the collaborators and my advisors, as well as the collaborating institutions. And here are the references to the papers I talk about. Thank you very much.
Right. Thank you very much, Rossi, for the great talk. If you have any question, you can come at the center. There is a mic. So we have time for 1 or 2 questions.
Yeah, I have a question actually. So great talk. It was very,
much.
a lot of fun actually. So when it comes to designing this, generating these mechanisms, how do you actually do that? So you have these parts that, especially something mechanical like, I don't know, spanner, for example. you need to have this, gears and stuff. These different parts need to be generated and combined together. Is that something you can already do properly?
I feel like that's related to the design problem that we were trying to solve, like the paper airplane design. I feel like it's kind of hard. So I think the 3D printing is actually the key in this problem. Do we have if we have efficient 3D printing, that we could have automated design framework for this. And I also think a related area is physics simulation. So there's a lot of work on differentiable simulation. And if we have tools like that, we could basically perform inverse design. Yeah. And interface that with the 3D generative models, which is pretty exciting. Yeah.
So don't you think that there is a difference between building a paper plane, which is one piece, and building a mechanism which has maybe 2 or 3 gears? To me, there is a gap there.
Yeah, I think the gap is very mature 3D printing technology. So the reason we picked paper as a material is because, first of all, it's super hard to simulate. It's a thin shell object. It's deformable, and pretty much there's no simulator that could accurately simulate paper. It's let alone like you fold them multiple times and fly them in the air, right? There's interaction between deformable objects and fluid. So it's extremely hard to simulate. So we kind of picked this very challenging task and to motivate 3D. But I think it's a very interesting. I hope it could become like the MNIST of design. It's one piece. It could be folded easily with robots and perform design. So I think whatever method, we could use this as an example to work on the design method. And this could be applied to if you have multiple components, when you actually hook up to a industrial 3D printing or manufacturing pipeline, it could still work there. Yeah.
Okay, cool. Thank you.
All right. Thank you, Andrea.
We're a bit over time, so we'll conclude here. Thank you. Let's thank Ross again. And can we have our next speaker? Dugu, can you maybe start sharing your screen? And also unmute to see if we can hear you as well.
Okay, can you hear me? Can you hear me now?
Yes, we can hear you.
And you see the screen?
Yes, we also see it on Zoom.
Okay, shall I go ahead then? Should I start? Just let me know.
Yes, just a moment. We're figuring out
Okay.
some technical details. Better? Okay, so after figuring out some technical issues, our next speaker, we can go to the next speaker. Our next speaker is Dugu Ceylan. So Dugu is a senior research scientist with working with Adobe Research. She got her PhD from EBFL, working with Mark Pauli, and she has been with Adobe since then. She has received the Eurographics PhD award in 2014 or 2015, and then the Eurographics Young Investigator Award in 2020. And Dugu is working on all things 3D, with always in the intersection between computer vision and graphics. And she has a special interest in when it comes to humans, which makes her work very close to my heart. So without further ado, I think Dugu, you can take it away.
Yeah, thank you so much for the invitation and also for the kind introduction. So today, I'd like to share some of our recent work and some thoughts towards multimodal generation with you. So we are all aware of the fact that generative AI is revolutionizing content creation, and especially text-to-image models have led this revolution, and there has been many examples of very high quality text-to-image generators. So Adobe's Firefly being one of them. So basically what this gives us is now we are able to just type short, complex text prompts and then immediately get very high quality content such as these images. So this is all great. And of course, once we are able to do such high quality generations, the next question to ask is how do we control this process in addition basically to text prompts? So before diving into that, so how do these models work? Not going into too much detail, basically the underlying machinery is this diffusion model, which is a generative model that would try to model the distribution of natural images. So starting with noisy images like sampled from Gaussian distribution, the model would try to basically learn to denoise the signal and then eventually have this high quality image. And the two main important blocks of the diffusion model, whether it's a U-Net architecture or more recently the diffusion transformers, are these attention layers. And in particular, we have these self-attention blocks where the image attends to itself. And this is very important for basically for the final structure and the appearance of the image. And then there is the cross attention where you can start attending to different signal modalities, for example, text. So now I have this basically very powerful 2D generator that I can prompt with these text descriptions. And as I said, the next question to ask is what type of other controls can we enable? And one of the immediate controls one can think about is, of course, spatial control, for example, controlling the structure of the image using depth, edge, pose, or other modalities. And there has been a lot of work in this domain, and ControlNet was one of the most popular that came out last year, basically, that enables to control this process with various signals. Of course, spatial signal is one of them, but there are many other interesting signals people have been starting to look at, for example, audio, because usually sight and sound are very connected to each other. So how would you do conditioning with a signal that may not be directly, that may not be represented as a spatial signal? And the idea is actually kind of very basic, similar to how we do text conditioning. One can also start introducing these additional cross attention layers where we can do basically attention with respect to these other signals such as audio. And basically the power here is one can also do that without really changing the base text to image model significantly. One can introduce only these additional blocks and train only them while keeping the rest of the network frozen. And that means basically you can try to add these additional signals with a moderate data set size. So once you do this, basically this is from a recent work that we've done. Hopefully you can hear the sound, but in this case, the input is basically this audio clip and the model is able to generate the images that you see. So this is a sound clip of basically hitting some dry leaves, and this is the image that you generate. And in this case, it's the sound of basically playing with water, and the method is able to generate these images. And now that we have basically kept most of the functionality of our base model and only added this additional control signal, we can also basically apply all the editing operations these models are able to do, but using an audio signal. For example, here, given an input image, we apply some diffusion-based editing method conditioned on the audio signal, which basically tries to preserve the original structure or the content of the image as much as possible, but only change or edit it based on the conditioning signal. Okay, so now basically we have the generator. We are able to control it with different modalities. Of course, the next question to ask is, how about output? So we are now able to generate images. Can we move towards other modalities like video and of course, eventually towards 3D? This was a work that we have worked on last year. Basically, the main question was, given this powerful image generators, can we use this to edit not only single frames, but edit an existing video? For example, here I have this input video of a swan, and then I provide some text prompt. Using the image model, I can obviously edit one of the frames, let's say the first frame. How do I propagate that edit to the rest of the video while basically ensuring temporal coherency as much as possible? And again, it turns out that by just looking at these attention blocks, one can do this task using only an image model to with surprising success. So the idea here is now we repurpose these self-attention layers, and not only the image not only attends to itself, but basically it starts seeing and attending to the features of the previous frames. And with this very simple, basically change, we are able to repurpose this image model to do video editing. And here are some results. And obviously, this simple trick can be applied to any underlying base model. In this case, this is using Adobe's first image model, and you see the input video and the edited result. And this is another example. Again, given the input video and the text prompt, we are able to do this per frame editing in as consistently as possible manner. So this kind of brings us to the intersection of 2D and video, but it's not 3D yet. So that is the next question to ask. How can we basically leverage this technology for 3D workflows, or how can we bring 3D to help with these workflows? So we've looked at this problem basically in the context of extending the pics to video work. So basically, previously I showed that given an input video, we can try to stylize it using the image model. But in this case, I still need the input video. But we also know that in 3D, we have all these tools to create the animation or the motion we want. For example, I can use physically based simulation. I can try to set up a scene and then do some camera path planning. I can capture humans or other rigged characters, so I can do mocap. So there are many, many ways of creating the exact motion we want. And the question to ask then is, can we utilize these tools to create the scene, to create the motion, but then turn back to the image generation models to help us basically map this scene and animation sequence to the final pixels that we want to render. And this, I think this is basically a first small step towards this direction, but overall I feel this concept of generative rendering is very powerful as we bring 3D tools and generation models more tightly together. So how do we do this? Basically, there are some common observations for this task and also for the video stylization task or video to video workflows. I had already mentioned one of them. So one key observation is that self-attention layers of the generation models are very effective in controlling the final appearance of the frames. And by just converting these to cross-frame attention, basically letting multiple keyframes attend to each other, one can already generate very consistent looking results. The second observation here is, of course, we do have an input 3D scene, and we do want to preserve the structure of the scene in our final generations. So then we return back to spatial guidance, for example, depth or edges, to preserve the structure. And in this case, this spatial guidance is, of course, ground truth rendered from the input 3D that we have. Another important observation with diffusion models is actually the initial noise that we start the diffusion process is very related to the final images we will get. And this is why for many image editing or video editing tasks, you'll see that people use some methods basically to invert the images or the frame or the video frames. In our case, however, we do not have RGB frames to start with. So we have a 3D scene which has no texture. So we cannot directly do inversion. So instead of that, I'll describe next. We actually try to initialize the noise in a more 3D aware way. And finally, because we also have the 3D information and ground truth 3D correspondences, we can start playing with the output of the attention maps to further improve consistency. Okay, so first let's look at noise initialization. So we have the 3D scene, which means for each object, we can also assume we have a UV mapping, basically that maps that 3D object to the 2D UV or texture space. So instead of basically initializing noise in the frames, the rendered frames, we can initialize the noise in the UV space. So now you can think of this as a multi-channel, basically texture map, which is just random noise. And using this and the 3D scene, we can render a noisy image for each frame. So here is like, if I stop this animation at every frame, basically it just looks like random noise. But actually, if you play it, you will see a motion, hopefully that comes through Zoom. But basically, this kind of gives you the idea that this noise pattern is in fact very important. And if you just run the diffusion process with such correlated noise, you'll see that you will already get frames that are very similar to each other, and that already has quite a bit of temporal coherency. So then the next step is basically how to improve this even further and get more coherent results. So let's see how we do that. That's basically really playing with these self-attention layers. So we have our animation sequence. Basically, we do this cross-frame attention for a set of keyframes. And basically, at the end of this self-attention blocks, we have the key and value features of each frames, basically what the self-attention layers process. So again, because we have the 3D and we have this mapping to the UV space, what we can do is take the output of these self-attention blocks for each frame and basically map them again to the UV space. Basically, again, treat them as textures. We can project them back to our common texture space, blend them in the texture space, and we can now render it back for each frame And again, I can do this because I have this 2D to 3D mapping. So now as a final step, when processing each frame, what we basically do is we get its original post-attention features and blend them with these basically blended features in the UV space and that are rendered back, and basically update them. So what this basically does is try to correlate the features, attention features of each frame in the UV space through this 2D, 3D mapping, and then make them, blend them in a consistent way, and then render back. So now that we have this setup, basically what we can do is, again, as I said, we can use any 3D tool to create a scene and a motion, and then use the generator just just for the final rendering task. So here, for example, you see this fox, this quadruped motion, and then given different text prompts, we can easily map that to different stylized renderings. Here is a motion capture sequence, which you can basically get from your available mocap data, or use any 3D pose estimation methods, and then map it again to these different stylized renderings. And of course, we can also just do it for static objects, but the motion could be created by moving the camera. So in this case, basically, even though the object is static, we can create this almost 360 type of sequence and then try to render it. So basically, these are examples of how different modalities, whether be 2D, video, 3D, or even other modalities like audio, coming more and more closely together. Of course, so far in the works that I've used, we've been using image models, but the video generation world has moving very fast. I think even today, Runway has announced their new text to video model. So that means like all the machinery we have developed, we could now potentially also bring it to these text to video models, which are more powerful, already have a sense of temporal coherency and also some 3D knowledge. And people have already started extending these works for 3D generation. For example, one use case for stable diffusion video was to be able to generate these full 360 turntable videos, which you can then reconstruct as 3D. So yeah, with that, like, I really think we are moving towards this multimodal universal generator, which will be able to take multiple modalities as input, text, other structure controls, audio, and so on, 3D, but will also be able to spit out RGB images, maybe intrinsic properties of images like depth, segmentation, mask, albedo, shading. Will be able to render videos, but also be able to generate 3D. And I guess we'll see more and more examples of this type of work in the next few months, and I'm very excited about it. And yeah, with that, I think that's all from me. And if you have any questions, happy to answer.
Right. If you have any question for Dugu, you can come in the center. There is a mic. So I have a question. So for the last work you presented, you had this hard-coded, effectively 3D representation to generate this consistency for the video. The question is maybe more of an opinion, like, do you expect in the future that we will need to have this hard code in the model, or we'll be able to have this type of, we'll be able to achieve this type of 3D consistency just from data-driven approach? And I'm referring to the consistency we see for models like Sora, for example, where, as far as we know, there is nothing hard-coded when it comes to 3D, but in many occasions, it seems to be 3D consistent.
Yes, yes. No, I think large models are already learning a lot of the 3D consistency. I think what excites me still is two things. One is like these powerful generators for 3D workflows. I think in still like in many applications, I may want to design the exact 3D scene and the exact motion that I want, and then maybe just use like the video model as a rendering tool. I think that is still powerful and will be useful. And yes, these models are learning a lot about 3D, but I guess still there would be a place for, it may not be an explicit mesh representation, but somehow a notion of implicit 3D maybe, to still, I guess, like capture very long range interactions, or if I want to generate maybe multi shots of the same scene, very zoomed in versus like very zoomed out, there I kind of tend to think we would still need some form of 3D representation, but it may not be the explicit 3D mesh that I guess traditional workflows are using today.
I see. Makes sense. And if there's no other question, I think that we can thank Dugu again.
Yeah, thank you so much.
And now it's time for our first coffee break, and we will reconvene at 10:45, I think. So yeah, see you soon.
Takes a little bit. Resets and does it a few times.
This is actually my first entire conference, so I'm a bit nervous.
All right. Hope everybody had a good coffee break and are excited for the next set of talks. Next up, we have Dongsu Zhang. Dongsu is a researcher at Seoul National University. He works in 3D generative models, specifically on a class of models called generative cellular automata that he's going to talk to us about today. Dongsu obtained his master's from SNU as well with Professor Youngmin Kim, and he's also interned at NVIDIA with Professor Sonia Fiedler. Super excited to hear from Dongsu. I feel like this is really exciting work. It's a new direction in 3D generation. And without further ado, take it away, Dongsu.
Yeah. Thank you for the introduction. Okay. Okay. Hello, I'm Dongsu from Seoul National University, and I'll present our work, Generative Cellular Automata, which is a 3D generative model for scene completion at scale. And part of this work was done when I was an intern at NVIDIA. Whoops. The goal of our work is to generate a complete scene geometry from partial point cloud obtained from sensors. So given an input partial point cloud of indoor or outdoor scenes obtained from sensors such as LiDAR, we aim to reconstruct the whole scene geometry. Oops. This takes a step towards our vision of using 3D sensors as content capture systems to generate high-resolution content, which might find eventual use in simulation or even AAA games. Previous works have employed discriminative model for scene completion. While discriminative models generate reasonable completions in dense point clouds, sometimes point cloud obtained from sensors are sparse, noisy, and incomplete as seen on the left. There may be multiple plausible completions for an ambiguous input. So discriminative models tend to average out the multiple solutions and might not generate high quality completions. Therefore, a conditional generative model capable of generating multimodal distribution might be more suitable for scene completion. Thus, we present GCA, a spatially scalable 3D generative model suited for scene completion. Building a scene-level generative model is challenging because complexity of the dense 3D grid increases in cubic to the size of the completion. Thus, high-fidelity completions are hard to scale using a naive dense grid representation. The first key idea to building a spatially scalable generative model is to leverage sparsity. In 3D, as we use higher resolution, the rate of the occupancy cells decrease. So if we only focus on occupied parts, we will be able to efficiently handle 3D shapes. Thus, we utilize sparse convolution layers to handle sparsity. Contrast to vanilla convolutions that perform convolution on all dense grids, sparse convolution operates on only occupied regions. Therefore, it is more efficient compared to vanilla convolutions in 3D voxelized shapes. The second key idea is to exploit connectivity of 3D shapes. Most man-made 3D shapes tend to be connected. To leverage connectivity, we employ the traits of cellular automata. Cellular automata is defined in grid of cells and models a transition over time. The transition rules follow the local update rules that depend on neighborhood of each cell. With this simple predefined rules, cellular automata can create complex structures such as snowflakes. In our work, we learn a neural network to predict local update rules that generate 3D shapes and sequentially grow them. Now I'll introduce generative cellular automata, GCA, that utilizes sparsity and connectivity. GCA represents a 3D shape as state S, which is a sparse occupied voxels of the surface using sparsity. Given an initial state S0, GCA computes the transition kernel PST+1 given ST, modeled with a neural network and samples the next state. We yield the final shape ST by recursively applying the transition kernel T times, similar to diffusion models. Now I'll explain in detail how a single transition works. For each transition, given an intermediate state ST, GCA computes the occupancy probability of neighborhood occupancy cells with sparse CNN. Then we average it to obtain neighborhood occupancy probability of the whole state ST. And we just sample from it. Because GCA models a transition kernel with only sparse convolution, the transition is local and spatially scalable. For a single shape completion, GCA generated sharper shapes compared to the previous state-of-the-art baselines. The transition kernel of GCA acts locally due to sparse convolution. Therefore, even if GCA is trained to complete on a single instance shape, it can complete a whole scene with distant, incomplete objects. While GCA is a 3D generative model suitable for scene completion due to locality and scalability, it has a limitation of generating voxels with a fixed resolution, unable to generate continuous geometry for content creation. Therefore, we extended GCA to generate continuous geometry. We utilize deep local implicit fields to generate continuous surface. Local implicit fields divide a continuous shape into a grid and then stores the latent code for each cell. The latent encodes a nearby local continuous surface using a neural network encoder. We apply the local implicit field to GCA. We introduce sparse voxel embedding, which augments the sparse voxel representation with the latent code Z that encapsulates the local shapes of the grid. We maintain the representation sparse by setting Z to 0 if not occupied. Sparse voxel embedding can be created from the implicit function with an encoder and decoded back to produce the implicit function using a decoder. Now I'll explain continuous generative cellular automata, CGCA, that generates continuous geometry with using sparse voxel embedding. CGCA, like vanilla GCA, starts from an incomplete initial state as 0 and recursively samples from the marker chain. Unlike vanilla GCA, it samples the latent code Z for each cell, which the easiest way to think of it is sampling color for each occupied voxels. For the last several steps, we use maximum likelihood estimation instead of sampling to remove the cells with low likelihood occupancy. The final state can be converted to a continuous geometry using the previously mentioned pre-trained decoder. The transition kernel of CGCA can be factorized into neighborhood cells and further factorized into occupancy probability and latent code for each cell. The occupancy probability follows the Bernoulli distribution with the parameter estimated by the neural net. The latent code follows the normal distribution with the mean estimated by the neural network if occupied. If not, we just set it to 0. This way, we remain sparsity. During training, we only have the initial state as 0 and the complete state X. So we emulate the intermediate states by sampling from an infusion kernel Q that is also close to P, while ST converges to X. The infusion kernel is factorized into occupancy and latent code similar to the transition kernel. The occupancy follows a Bernoulli distribution, but we inject ground truth occupancy X to the probability. The same goes for the latent code by injecting the ground truth. The transition Q is similar to in that the parameters are mixtures of the estimated distribution P and the ground truth. Next, I'll introduce a full training procedure that uses this infusion kernel. During training, we sample from the previously mentioned infusion kernel and minimize the KL divergence of Q and P. Sampling stage from Q is expensive since we need a neural net evaluation. Thus, in practice, we use a replay buffer to cache infused intermediate states. And we compared our method to state-of-the-art baselines on shapeless scene datasets. A synthetic scene comprised of multiple objects. VGCA generated diverse high-fidelity shapes from the input point cloud. We also trained and tested our model on synthetic 3D front datasets comprised of room-scale indoor scenes. VGCA can indeed generate multiple high-fidelity completions from a single observed point cloud. In our next project with NVIDIA, we moved on to using GCA for outdoor scene completion from real-world LiDAR scans, which is accepted to this CVPR as a highlight paper. The difficulty of competing from real-world input signal is that we often do not have ground truth data for supervision. Prior methods use accumulated LiDAR scans as supervision signals, leading to noisy and incomplete results. Instead, we propose a new task named outdoor scene extrapolation to distinguish with the previous works. The task aims to generate completed geometry in regions that are completely unseen by LiDAR through height limits or occlusions from several LiDAR scans. We achieve this through training on synthetic scenes while showing strong sim-to-real generalization to real-world LiDAR scans with our method. We also note that we do not use semantic labels like previous works. Our model, Hierarchical Generative Cellular Automata, HGCA, leverages a spatially scalable GCA in two-stage coarse-defined manner. In the first coarse stage, given a point cloud from the LiDAR scans, we voxelize the input and use GCA to generate a completion in low resolution voxel. Then in the second stage, we upsample the coarse completion from stage 1. We concatenate the coarse completion with the input point cloud. Then we use CGCA in a final resolution conditioned on a coarse completion and input to produce high resolution sparse voxel embedding, which generates a final continuous mesh using a pre-trained latent decoder. GCA is a local model and often completes scenes without global consistency. Thus, we append global features to coarse GCA's unit architecture by proposing a lightweight planar model that extracts bird's-eye view features. We splice the initial incomplete scan S0 into 2D using a local point net and pass it onto 2D units to obtain the global bird's-eye view feature. Then we promote the bird's-eye view feature into a sparse 3D unit in a space-like manner, while predicting the rough dense occupancy. During training, we apply auxiliary bird's-eye view loss against the ground truth occupancy to enforce a planner to learn global features. Note that we name the global consistency model planner since it plans ahead the persisting bird's-eye view feature solely with initial state S0, which remains through the Markov process of GCA. We train our method on a mixed synthetic dataset of TurboSquid scene and Carla. We compare our method against the state-of-the-art scene completion methods. Here we show that HGCA generates more realistic scenes compared to the recent baselines qualitatively. In the main paper, we also show that our method generates accurate completions quantitatively. We validate our method on Waymo dataset to show that our method generalizes well on real-world LiDAR scans. HGCA shows superior generalization capability, which we suspect stems from local transitions of GCA and using a hierarchical formulations, which tends to be more robust to noise. Our method can generate beyond the LiDAR field of view more than the accumulated scans. HGCA scales well to large real-world scenes using a single GPU, making it scalable and even extrapolate heels on the bottom. Also, HGCA generalizes to unseen objects from training data, such as complex trunks of trees. HGCA can generalize to complete three-wheeler unseen from training data. To conclude, GCA is a scale is a 3D generative model that basically grows. It is spatially scalable model suitable for scene completion, and it generalizes well from scene to real. So I would like to acknowledge all my wonderful coworkers from SNU and NVIDIA. And lastly, a bit of advertisement. Please check out our paper, Outdoor Scene Extrapolation with Hierarchical Generative Cellular Automata in Arch 4AE, Friday, 10 a.m. Also, I'm applying to PhD program in 2025. So if anyone's interested in having a chat, let's chat. And lastly, thank you for listening.
Thanks a lot for the talk, Dongsu. There's a mic over here. If anybody has any questions, please come up. You can come up right here.
Hi, I have a quick question for your first nice talk. So for your last work, do you think it is possible like to take also like RGB into from camera and into of this virtualization process so that you can fully reconstruct the texture, the color scene? Yeah.
Are you suggesting that we take RGB camera as
yeah.
input?
And so that combination of LiDAR and RGB, so like you will have a LiDAR to be calibrated so that RGB camera can see the same thing with the LiDAR. It's possible to bring the color to those LiDAR point cloud, and it is possible to do this to run this scene compression together.
We actually haven't tried it, but we actually once discussed using the RGB features to extract dino features and do something with that. But in our current method, no, but I think that will be kind of our future work for now.
Okay. Okay, thanks.
Yep.
Hi, thank you so much. I learned a lot today from you. I'm Shri and I work for Volkswagen Innovation, and I'm working in this space right now. So I have a couple of questions, but I'll stick to one for today. At the end, when you go from point cloud to mesh, what type of decoder do you use?
Oh, it's actually the same decoder that we use in the CGCA, and I think you're referring to this part, right?
Yeah, exactly.
It's just a local IFNet type of hierarchical decoder that takes in the features and the XYZ coordinates, and it outputs the SDF values, not SDF, but unsigned distance fields. So, and
Gotcha.
we use marching cubes to generate mesh.
Okay. What about when it's a volumetric mesh and you have things like castings or extrusions that maybe join two parts together in a car, for example? Do you think that it's a good method or is applicable here?
I'm honestly not sure what makes a difference. If
like more details. So like in
Ah.
this case, you can't make out the difference between the bumper of the car and the crash box, right? So these are kind of practical implications of using point clouds versus graphs.
Uh-huh.
I'm just trying to figure out if this is a good solution for that.
we use kind of like the basic, the most vanilla decoder that we could think of. An IFNet paper is like 3 or 4 years ago.
Mhm.
So I think if you use the techniques from like recent, like Mosaic SDF type of representations,
Right.
we could get better meshes.
Gotcha. Yeah, there's something called point to mesh. That's the current state of the art, but still doesn't perform well enough to have a well-defined generated mesh.
Mhm.
So super interesting work. Excited to see where it goes. Thank you.
Thank you.
Thank you so much, Dongsu. Thanks for the great talk. Thank you. All right. So next up, we have Varun Jampani. Varun is a lead researcher at Stability AI, where he leads the generative vision team. He's worked at Google and NVIDIA Research, and throughout his career, he's made key contributions across computer vision. He's worked in inverse graphics, 3D, 2D perception, 3D reconstruction, and now 2D, 3D generative models that I hope he's going to talk to us about. Really thrilled to have Varun here today for his keynote talk, and just going to let Varun take the stage. Thank you.
Yeah, thanks, Amlan, for the nice introduction. Share. Hi everyone, I am Varun Jampani, a lead researcher at Stability AI. Today I will be going to talk. I'll be talking about adapting image and video generative models for 3D generations. Before going into the main topic of the discussion for this presentation, I would like to share some of my thoughts on what it means to have a generative 3D model. So 3D generative models, just like image and language generative models, they learn a conditional distribution of 3D content given some practical input such as text, image, or video, nothing, which are quite easy to input. And so these 3D generative models can make the 3D content creation quite practical and feasible. But unlike language and image, there are several differences to 3D. 3D is different. There are several key differences, which I will briefly mention here. So one is that there is no standard universal 3D representation. So different 3D applications require different 3D representations like voxel, meshes, graphs, projections, descriptors, etc. And also 3D is for niche, right? And it's for power users. So most of us on a daily basis interact with text, and also we interact with images and videos on a daily basis. But most of us, we don't usually interact directly with 3D. So it's mostly for power users like graphic designers, movie art, VFX designers, or game artists, etc. Another key difference is that like the 3D data, the available 3D data is orders of magnitude smaller. For instance, we train some basic image generative models with using 5 to 10 billion samples of images. But on the other hand, the 3D data sets at most are kind of like a 250K to 10 million samples kind of thing. And also much of the data is not very high quality, to be honest. So this makes it quite difficult to train a 3D generative model from scratch. And so because of all these differences, there is no single unified generative model that exists for different 3D use cases kind of thing. For images, if you have a generative model like Stable Diffusion, that is widely applicable for a lot of image tasks and most of the image tasks. And for video, we have, let's say, several models like Sora or Stable Video Diffusion that can be useful for a lot of video tasks. But because of all these differences, there is no single unified 3D model. Also, it's not clear whether we will have it, whether it makes sense to have a single unified 3D model because of the diversity in 3D applications and use cases. Despite that, I still believe that like generative 3D technologies can form foundation for a wide range of 3D applications. So I'm quite excited to be in this field and to be working on this new 3D generative models stuff. What this means is that, like, for instance, we have a lot of 3D applications like gaming, virtual reality, movies, 3D shopping, etc. And what used to happen is that like a lot of these applications are still like they're actually supported by a lot of technologies, 3D technologies like human avatars, virtual try-on, or like scene understanding and synthesis, etc. So what is going to happen, or what is happening recently, is that like there are some core models on 3D that actually these core generative models, that's 3D object generative models or 4D generative models or face human generative models, that are going to support this lot of these technologies, which in turn can support a lot of 3D applications. So the goal of research in my 3D team is that, like, let's see if I can move this. No. So the goal of research in my 3D team is to actually work on some of these core 3D generative models that can have wide range of applications in 3D technologies and applications. So despite not having a single unified 3D generative models, there are actually two emerging technologies that are coming up in 3D generative AI in the last 1-2 years, I would say. One is the direct 3D prediction, and the second one is multi-view generation. And for direct 3D generation, these generative models takes a single input image or text as input, and they directly output a 3D model as output, like a 3D mesh or a triplane SNERF or some other 3D representation. One of the positive side is that they're usually quite fast due to direct predictions. And on the negative side, they need quite a good amount of 3D data sets to train and generalize. So LRM work from Adobe Large Reconstruction Model forms one of the pioneering works in this space. They showed that like from this single image, by using a transformer network, we can actually get a very good quality 3D generation outputs like this here, the triplanes in this case, nothing. So at the time, this model is not open source. There is some open version of this called OpenLRM. So we also trained some in-house model, which we call TripoSR. This is in collaboration with Vast AI Research. And where with this TripoSR model, this can generate 3D mesh from a single image in less than 0.5 seconds. On this bottom left, I show some 3D generation results that is compared with OpenLRM, which is an open source version of LRM. And from these results, we can see this TripoSR has much better 3D reconstruction results compared to OpenLRM. And on the bottom right, I'm showing a plot. On the x-axis, it's an inference time. And on the y-axis is a 3D reconstruction accuracy measured in terms of F-score. So in this plot, we want to be on the top left side. We want to have a high 3D reconstruction accuracy while being quite fast, while being low inference time. So as you can see from this plot, this TripoSR has one of the best, it's actually one of the best and fastest 3D generative models among open source. And since we open source this model, and because it's a quite fast and versatile, there is a quick adoption of TripoSR in the community. There are actually several interesting use cases and workflows that already people have been using. For instance, people are using TripoSR to actually create 3D models within Apple Vision Pro environments. And they're also training this TripoSR with some sketch to image models so that we can generate from sketch to image to 3D within just a matter of few seconds. A related work that we are presenting at this CVPR is called Zero Shape, regression-based zero-shot shape reconstruction. Here we take slightly different approach where we make use of off-the-shelf depth networks called DP, like this DPT networks. We adapt it to predict both depth as well as camera intrinsics. And then we unproject and this depth and do some 3D normalization to get a partial point cloud. And then we actually complete this partial point cloud into a complete shape using a transformer network. So in this work, we mostly focus on shapes. We get some quite good quality shape estimations from a single image in this work. Please see the paper for more details of this work. So this direct 3D prediction is one of the emerging techniques, and the second techniques that is widely used recently is this multi-view generation, right? Like So where we take existing image and video generative models like Stable Diffusion or Stable Video Diffusion, and then we do view prompting to it to generate an image from different views, novel views of that given object, given input image. And then from this novel multi-view predictions, we can optimize a 3D object using some loss functions like SDS loss function or reconstruction losses. So the nice thing about this technology is that like it leverages an image and video models that are trained on large data and thus have very good generalization. And on the downside, they are usually slow because these image and video models are usually quite slow. They're usually diffusion based and usually slow. And they also require further processing to get 3D objects out. We do some kind of like NERF optimization and stuff. So there are two main aspects to these multi-view generation pipelines. One is this view prompting. Earlier works like Dream Fusion and stuff, they use text-based view prompting. And more recent works like 0123XL and other more recent works use camera-based, more precise view prompting with camera pose-based control. And second important aspect is that like how can we go from multi-view predictions to 3D objects? So there we typically use core distillation sampling losses and reconstruction losses kind of thing. So in the rest of the presentation, I will explain some of the works in this space. Some use text-based prompting and camera pose-based prompting, and some use SDS losses and other reconstruction losses. So much of the focus of the presentation is on this multi-view generation. So one of the pioneering works in this space is this Dream Fusion that introduced this core distillation sampling loss, followed by other recent works like followed by other works at the time like Latent NERF, Magic 3D, etc. So here the key thing is that like we optimize a NERF representation, and we project this NERF, we render this NERF onto different views like side view, back view, front view kind of thing. And then we pass this rendering along with this text-based view prompting, like the peacock from a side view, peacock from the back view, peacock from a front view kind of thing. And then we pass this through this, here the Imagine-based network, and also, or we could use other networks like Stable Diffusion as well. And then we can get the loss function, which is called the core distillation sampling loss function that we can backprop through this NERF model that we are optimizing. Nothing. So here this view prompting is kind of like a hidden thing, but it's kind of actually is very important to get these 3D consistent results. And one of the nice surprising things with this Dream Fusion is that like with this simple text-based view prompting with SDS loss, we can get quite good 3D reconstruction results. Nothing. And in the next few slides, I will introduce a bit more detail in one of our works called Dreambooth 3D, where we use this text-based view prompting and SDS losses for subject-driven text to 3D generation. So in this work, the problem setting is that like in addition to the text prompt, like a photo of a dog or some other text prompt, we also have some input exemplars as input like this, let's say this 3 to 6 casual captures of this dog. And the intended output is this like the 3D NERF model of this particular subject that is following this text prompt. So we based this work based on the Dreambooth, which is one of our earlier works, where we showed that like we can easily adapt existing text to image models with some input images, with some simple fine tuning. We can actually generate very photorealistic images of this particular subject with this Dreambooth model. So once we have this Dreambooth model, one could simply say that like we can actually first train a Dreambooth model on these few exemplar images. And then we can actually do text-based view prompting with SDS loss, and then to get these 3D models out, kind of. But unfortunately, this did not work out. One of the key issues is that like this Dreambooth model overfits to the given input views of this object of this subject thing, and when we actually query such a Dreambooth model with different views like side view, front view, back view, we usually don't get very consistent outputs. So that's why the resulting 3D model is not very coherent or consistent. So as a remedy, we actually propose a 3-stage optimization pipeline for this. So in the first step, instead of training a full dream booth model, we actually train a partial dream booth model. That means we train we do an early stopping for dream booth. So this way we can still get a 3D consistent NERF model with SDS loss on this dream booth model, on this partial dream booth model. But this initial NERF do not have high subject fidelity, but it's more 3D consistent. So from this initial NERF model, we do this multi-view NERF renderings. And from these NERF renderings, we actually translate into these pseudo multi-view subject images using image-to-image translation like SDEdit. This is again using the fully trained dream booth model for this subject. And then from these multi-view generated data from these multi-view subject images, we train another dream booth model, which we call multi-view dream booth. And since it saw more views of this object, and this SDS loss with this view-based prompting works better, and we can get a final NERF model from this multi-view dream booth, which is more 3D coherent. So these are some of the results. One of the nice things is that since it takes also the text prompt as input, so we can actually generate, we can actually easily recontextualize given subject in 3D in different context. Like for example, these in this bottom row examples, we can put this dog with a green umbrella in 3D. Also, we can do some interesting stuff like we can also do some fancy pose changes just with a simple text prompt changes like a V dog sleeping or a V dog jumping. And even though none of the input images have a sleeping or jumping dogs, we can actually create quite realistic jumping and sleeping dogs from this. So that is about Dream Booth 3D. Next, I will briefly discuss explain this for RT. Noise. So here the goal is that given a noisy web images in the wild for animals like a zebra, giraffe, or elephant, or any other animal. So we want to reconstruct articulated 3D models from these noisy web image collections in a self-supervised fashion. So we do not assume any ground truth supervision like any key point annotations or any other annotation. So it is actually completely self-supervised from these images. So it's kind of like a quite challenging task. So we again leverage SDS loss on stable diffusion model for this task. So when we experimented with standard stable diffusion model with SDS loss, we find some issues. This SDS loss we need to backprop. It actually backprops the gradients through encoder in stable diffusion model because it is a latent diffusion model. And we find that it actually provides, oops. Yeah, with this SDS loss, we find that it actually provides some noisy gradients, and it also has a high computational cost due to this backpropping through the encoder. And here I'm showing an example image, and after one training step of SDS loss, how his image is updated, you can see a lot of noise around the boundaries stuff. So as a remedy, we actually propose a decoder-based accumulative score sampling loss. So here the key idea is that instead of backpropping the gradients to encoder, we actually do the score distillation in the latent space, and then we actually accumulate gradients in the latent space, and then we decode the gradients to get the image target, and then we compute the loss based on this image target. So it has a low memory consumption, and we also observe that it has a cleaner gradients and provides more stable training. And here I'm showing an example with after one step of training with this DAS loss, we can get much cleaner image. So we use this DAS loss in an overall reconstruction pipeline for animals. I won't go into too many details here, where we actually optimize a part-based MLPs to optimize each part of the animals along with the texture maps for each of the parts. And we have this previous work called HiLASI, where we actually introduce several reconstruction-based losses. And in addition to that, we introduce this DAS loss on top of Stable Diffusion. And these are some of the results. Top row shows some input images, and the middle row shows HiLASI results. One of our works, which is a previous state of the art on this task. And in the bottom row shows Arctic 3D results. And as you can see with Arctic 3D, we can get much better 3D reconstructions compared to previous works. And yeah, stepping back, so far these works, these Dreamboot 3D, Dream Fusion, Arctic 3D, and all these works are mainly based on text-based view prompting and on the Stable Diffusion or Imagine or some other image generative model. But it only provides rough viewpoint control, right? That's why the results are still not precise and stuff. And one could do more precise camera control with this the camera post-based view prompting. So one of the first works in this space is 0123. Ryushi presented this earlier in this workshop, where we can get the precise view control with camera conditioning and kind of thing. So one of the nice things with this work is that it showed how easy it is to adapt an image generative model like Stable Diffusion to have a view control on top kind of thing. And it works surprisingly well. And one could also use the SDS losses on top of it or reconstruction losses to actually do some reconstruction of NERV on top of it. So we try and improve internally at Stability. We have an improved version of 0123, which we call Stable 0123, and with some improved training things. And we show that with the Stable 0123, we get considerably better novel view synthesis results compared to 0123 or 0123 XL. So here I'm showing some results of Stable 0123 in the bottom row and compared with 0123 XL. As you can see, Stable 0123 results are much more multi-view consistent and coherent. And this model is open source, so you can also give it a try. And along this similar, one of the key issues with this viewpoint control, even with camera poses, is that there is still a lot of multi-view inconsistencies in these models, 0123 and other things. So there are several works in this space that try to improve multi-view consistency. I'm just mentioning two representative works here, which takes slightly different directions. One is the SyncDreamer type of works, where they actually also propose to maintain some explicit 3D representation during this diffusion process. Here some voxel representation, so that we can actually get some multi-view consistent novel view synthesis outputs. Another set of directions, take exemplified by MV Dream, is that we always try to predict if novel views at fixed camera angles, so that the network can be more multi-view consistent. Along the similar vein, we have a work at the CVPR, which we call MV Diffusion, which is single view 3D via depth consistent multi-view generation. So we actually propose some depth aware 3D attention layers to actually generate to actually have this consistent novel view synthesis using Stable Diffusion model kind of thing. I'm not going to do the details of this work here, so please see the paper for details. Next, I will go into some details of the Stable Video 3D model, which is along these lines of generating novel multi-view synthesis and 3D generation from a single image using latent video diffusion model. So this work is based on Stable Video Diffusion, which is also released from our lab at Stability AI, which is scaling, where we scale latent video diffusions to large data sets, and it is still probably one of the best open source models out there for video generation. So we make use of the Stable Video Diffusion, which has a very good temporal priors on it. And then we actually conditioned it with the camera pose trajectories in our Stable Video 3D model. And then we fine-tuned it using some 3D data sets. Yeah, specifically this Stable Video 3D model takes single image as input and also takes some static orbits, this camera orbits, and it outputs quite consistent novel views of that single image kind of thing. So here I'm not showing the 3D results here. These are actually the predictions of this video model, which we can see are temporally quite consistent. In addition, this stable video 3D model can also take these dynamic camera orbits. They need not be like a circular orbits, and it can also generate novel views along these camera paths. So these are some of the sample results of the stable video 3D model. As you can see that results are quite multi-view consistent. And this is the comparison with several state-of-the-art works in this space for novel view synthesis. And most of these works actually try to leverage stable diffusion or adapt stable diffusion for these tasks. And as you can see with the stable video 3D, we can get much more multi-view consistent results compared to most works in this space. So in addition, once we have these novel multi-view synthesis using stable video 3D models, we also propose some novel techniques to get 3D objects from generated views. As a result, we get state-of-the-art multi-view and 3D generation results. Specifically, given these novel multi-view video thing, and we first optimize a NERF using a coarse NERF using purely image and geometry losses, and then we also optimize the illumination modeling so that we can have an illumination disentangling from this optimized NERF model. Otherwise, shadows will be baked onto these NERF models. And then we use marching cubes to convert these 3D NERF model into this tetrahedral mesh, which is a high resolution tetrahedral mesh. And then we further optimize with image and geometry based reconstruction losses. And since these stable video 3D provides quite good multi-view synthesis results, just with image and geometry losses, even without SDS loss, we get quite good 3D reconstruction results. In addition, optionally, we can actually, since these novel views do not cover all the corners of the object, we also propose to use a soft mask SDS loss using this SV3D model for further improving the 3D reconstructions. So these are some of the sample 3D generations from this stable video 3D model. As you can see, they're quite 3D coherent and quite decent quality. So in this previous work, we showed that like we can adapt these video and image models for 3D reconstruction for 3D generation, but we can also go beyond simple 3D shape and textures with these image and video models. The stable diffusion can also be adapted to predict other related 3D attributes such as environment, illumination, or material properties, etc. So one work we're going to present at this CVPR is this diffusion light, where we show that like we can get light profiles for free by painting a chrome ball, where we adapt stable diffusion to paint chrome balls to estimate HDR lighting from a single image. As we can see from these results, these environment maps predicted are quite realistic and feasible. Yeah. Briefly about the technique, we use this depth-based control net to actually paint chrome balls onto a given input image. But since this is a diffusion process, we usually get different chrome balls. If I actually run it 10 times, we get a different chrome ball each time, kind of thing. So we have some simple techniques where we use a medium chrome ball and again repeat the process until we get a robust estimate of this environment illumination. So we also estimate HDR map, HDR environment illumination by training some LoRa's and with a different that actually covers different dynamic ranges. So please see the paper for more details, or also come to the presentation. And another work along this direction is that like is Alchemist, where we adapt stable diffusion for precise material control in images, where we show that like we can fine-tune stable diffusion to actually change material properties like metallicness, roughness, or the transparency, or even some complex properties like transparency, like as shown in the figure here. So we get quite realistic results. They may not be completely physically plausible, but they are quite realistic. So here again, the technique is quite simple. We actually generate lot of synthetic data sets using using some cycles renderer and some existing synthetic HDRA maps and synthetic objects. And by using these synthetic data sets and with these fine-grained changes in the material properties, we fine-tune the stable diffusion model here, the instruct pix-to-pix model, to actually output these precise changes in these material properties. Another work in this space is the JEST, where we actually fine-tune, where we actually leverage stable diffusion in a zero-shot manner to transfer materials from one image to another of thing. So it's kind of like a quite simple technique, but it's kind of quite powerful, where we show that like a given an input image and a material exemplar, we can actually apply these materials onto these images in 2D without any explicit estimation of 3D shapes or 3D materials or anything. Everything is done implicitly by stable diffusion here, which is quite powerful. So that concludes much of my talk. So in summary, we show that like these generative 3D technologies can form a foundation for a wide range of 3D applications. Despite not having a unified 3D generative model, there are two emerging technologies in generative 3D space. One is direct 3D prediction, and second one is multi-view generation, which both are quite promising, and we are in a very exciting time for both these directions. And for this multi-view generation, these image and video models can be easily adapted to actually get quite good results. In general, these 2D generative models can act as world models and can be adapted to different types of 3D generation tasks. That concludes my talks, and thanks. And any questions or comments?
Please come ahead. Thanks for the wonderful talk, Varun. For questions, please come ahead to the mic that's right in the middle. You can come ahead. Thanks.
Hi, thanks for the great talk. Yeah, so that actually I have played around SP3D before. So like I noticed that if sometimes I input images with some text, then it may produce some consistency across the generated image. What is the major challenge in those fine detail multi-view consistency when generate multi-view images?
Yeah, I think yeah, SP3D provides a good multi-view consistency, but still there are several issues to fix there and stuff. It's just that like probably we did not see enough training data in observers. There is not enough textures and stuff with this text things. So probably scaling up to more data sets and more in the wild multi-view data sets might improve the results.
So a follow-up question. So that I noticed that in general, the large shape will be looks multi-view consistent, but it's just maybe like some texture, a little bit detail, looks a bit inconsistent. What do you think to be the major difference between these general coarse resolution consistency and those fine texture consistency? What is the technical challenge you have that so that this coarse multi-view consistency cannot also guarantee like those fine multi-view consistency?
Yeah, that's actually a good point. So there are actually several techniques used in 3D graphics literatures and gaming community where they actually disentangle coarse geometry with fine textures kind of thing, let's say with UV mapping and stuff. So we have some works in progress where we are actually also trying to disentangle these for such 3D generation things. So yeah, so there are actually multiple trade-offs. So there is no simple answer to that, but yeah, depending on the type of application, we may have to disentangle fine-grained textures with coarse geometries.
No, okay, thanks.
Quick question. Have you considered generating a whole scene instead of individual objects?
Sorry, if I understand correctly, the question is.
Have you considered generating whole scenes in 3D instead of individual 3D objects?
Yeah, so the question here is that like have we considered generating the scenes instead of objects? Yeah, so far we have mostly focused on objects, but yeah, that is we have several works in progress where we are also where we're also considering scenes. The main challenge is that like the availability of data sets for scenes, and but we are hopeful that like with the more powerful video generative models, we can also go into scenes as well.
I mean, do you just take individual objects and place them? Is it just a placement problem, or you it's like, is it like an object composition kind of problem, or you use the whole scene for generation?
It is not just an object composition problem. I think scene has much more background things like walls and floor and other things as well. So there is actually much more data set problem as well. And it's yeah, one could tackle both, like background generation and putting objects in the scene stuff. Yeah, there is no single right way to do it.
All right, thank you.
Thank you for the questions. We'll be able to take 2 more questions. Thank you so much.
Thank you for the talk. So, assuming that the 3D data sets are going to grow in the time, what do you think have bigger potential for 3D generation, the direct 3D prediction or the multi-view generation style?
I think given enough 3D data, the direct 3D prediction has a lot of potential because it's quite fast and it's actually quite seamless and stuff. And in general, it's difficult to scale 3D data sets too much unless we get a lot of data from gaming companies and stuff. My general hunch is that like we might need both. Probably one could directly predict 3D and then use these multi-view optimization based techniques for further optimize these 3D generation quality.
Thank you.
Yeah, thanks.
Hi, Varun. Thanks for the great talk. One question regarding direct 3D prediction. What is the resolution of the occupancy field that you're predicting? And how do you see the way forward in predicting high resolution 3D objects natively rather than doing multi-view generation that seems to be the paradigm in the recent past?
Yeah, I think I would not say multi-view generation is the main paradigm. Direct 3D prediction is also is gaining a lot of attention and stuff. For this triplane resolutions, I think for this work we use 64 by 64 by 64, which is somewhat small. We don't get high resolution stuff. And again, there is some disentangling. We should do some disentangling of geometry and textures there. Geometry can be low poly and low resolution, but textures can be high resolution and stuff. So one could go to higher triplane textures, or one could do this disentangling to get high quality 3D.
How do you see the way forward to go from the 64 cube limitation to, let's say, 512 or 1K large geometry generations?
Yeah, there are ways to scale up. There are several transform. For instance, in this work, we use these transformer layers to predict these triplanes. And there are also several advances in transformer attention layers one could leverage to directly predict 512 or 1024 things. But I feel the main bottleneck is not the triplane resolution, but probably availability of such high quality data sets to train those.
Thanks for the share. And I've noticed that the most popular generative 3D model is about point cloud and surface, but is not quite friendly for editing in CAD software. So, and there's MeshGPT and Polychain, which doing multi-stage to translate point cloud to mesh. But what do you think? Why is there so not that large number of projects about the reverse engineering stuff? What's the major difficulties? Do you think?
So sorry, can you actually be more specific on reverse engineering? What you're thinking about?
I mean, so mostly the generative 3D is in surface. They generate surface and point clouds, but not meshes. But I believe mesh is better for industrial and better for editing. So.
Yeah, in general, the current strategies for most of because meshes also have these. We also need to deal with this connectivity. It is actually a graph problem. Mm-hmm. So the usual strategy now is to actually either predict point cloud or these triplanes or NERF representation, and then actually post process it to get some meshes out in a differentiable marching cubes or even some standard off the shelf techniques kind of thing. But I agree that like meshes are much more suitable for industrial applications and a lot of applications, but maybe we will see more and more works where that directly try to predict meshes.
Thank you.
Thank you so much. Thanks so much, Varun, for the great talk, and thank you for the questions. We'll move on next to Junyan.
All right, so our next speaker is Junyan Zhu, who is an assistant professor with the Robotics Institute at Carnegie Mellon University. And prior to joining CMU, he was a research scientist at Adobe as well. Junyan has been involved in a lot of exciting early results from generative models for 2D image synthesis like GauGAN and Pix2Pix, and has done a significant work exploring how to best control these models, especially for generation. He's also worked recently with 3D aware generative models, and today he'll be telling us about controllable 3D generation. So excited to hear that. Takes a few cycles to, yeah. Yeah, you're sharing the screen in Zoom. Turn on your video too if you want. Yep.
Hello. Yeah, thanks for the introduction. I try to be quick so you can have your lunch earlier anyway. Very excited to be here. We will talk about some of our recent work on controllable 3D generations. So we have seen two types of paradigm. One is such as you can modify the shape and edit the material in Blender or ZBrush. You get very precise control of what you can get. But the drawback is might take a lot of expertise and workload, and so that's one method. The other method is go to the other extreme. Let's just using text prompt, since everything is about prompting nowadays. So you can write a simple text prompt, and hopefully you can generate an asset with some method like Dream Fusion, but other more recent works as well. So one issue with this kind of paradigm is it's very hard to describe shape, even material, using a text prompt. For example, we try to say a car with a rounded shape, smooth curves, and somehow you get something like this. So, it's very hard to describe these things in words, and it's not sure even you can describe it. The model may or may not work that well if you provide a very detailed shape description. Okay, so we would like to find something in between these two paradigms. Okay, so one work which has inspired our recent efforts is a very one of my favorite paper called the TEDdy system by Takeya Igarashi et al. At SIGGRAPH 1999, which his work enables us to create a 3D object with very simple 2D scribbles. Okay. And it's very hard to believe this work was produced like 25 years ago, but I encourage you to look at his system. So we inspired by this work, we would like to add spatial controls such as user scribbles into recent 3D generative models, either GAN models or 3D diffusion models. So one of the first thing we have tried, that was also 4 years ago, is we wrote one of the first paper on how to editing generative nerve or 3D GANs like that. So a generative nerve looks like this. Is basically you are able to generate different types of nerve if you sample a different shape code or appearance code. And this is how the standard nerve looks like. And so there's a very well-known paper called Graph, which basically adding shape code and color code to the nerve architecture. And this allows you to generate a random object with different shape and appearance in the test time. So we have done some slight modification in 2021, which we introduce a shared branch which encodes the common shape of the cars or chairs, and also the shape code was fed to the is controlling the instance specific shape variations. Okay. Then our method allows us to generate different types of chairs with different materials and different shapes as well. But the work this particular work was focusing on editing the nerve rather than just generating random nerve. So we would like to modify the appearance and shape of a nerve model. Now the next question is which part should we edit? So for the shape editing, we can actually just modify the weights of the nerve networks, and by matching the predicted depths versus the user provided guidance. And for the color editing, it's even easier. We can just ask the nerve to predict the color, and we'll try to match that color to the user provided color scribbles only at that particular regions. And importantly, to keep the background color the same, we also have some background color constraint so that you don't color the entire thing as a particular color. And for the color editing, it's much easier because we can keep the rest of the geometric branches the same. So the color editing is very efficient. Only takes several seconds, but the shape editing is more involved. It takes you need to modify more layers. And here is how the interface looks like. Okay, so try to play the video. This is the render views from the nerve. Okay, and you can pick up a particular view, and you can pick up a particular color, your favorite color, and you can apply a very sparse scribble onto the shape. And then you need to, and our method will update the weights of the nerve to reflect your edits. And you also need to specify which color you would like to preserve. It's called background strokes. And now once you achieve that, you can actually render the same nerve at different viewpoints, just like a regular nerve. And here are some additional editing examples. For example, here we can change the color of the card. And here we can remove parts of the object as well. Another changing the color of the chair. Okay. I'll remove parts of the object as well. Yeah. So this is our first way of adding the controls through by adding the user scribbles as constraints and try to optimizing the shape code, appearance code, as well as part of the layers to match the user's constraints. So one limitation we are facing here is since we are doing optimization-based method, optimization is fairly slow, especially for the shape editing. So it might take you several minutes per user edit to update the nerve weights. Which is not a very good experience for if you want to achieve interactive editing experience. And also we need to implement different types of optimization methods for different type of user edits. So we need to manually see how we can implement each loss differently for particular user edits. So it's not very scalable. So having working on this direction, but the next idea we have is maybe instead of adding doing this kind of test time optimization, test time tuning, we can directly adding the spatial control like user scribbles as the conditional input to the generative nerve architectures. So this is the work produced by last year's CVPR, done by student Kengo and Shen as collaborating with Deva at CMU. So there are already lots of work on along with similar ideas. Basically, this is a sketch mesh. You can generate a mesh given the user sketch. And here is another work which try to editing the face, although they only apply to the frontal views. So in this paper, we would like to have a framework which allow you to support all kinds of user controls and supports all kinds of subjects, not just faces. So the idea here is we would like to generate a nerve object given conditional on a single 2D user sketch. But now the next question is, once you generate objects, maybe you are not happy with certain parts, you would like to edit the object. Maybe it's very hard to edit some parts from a particular viewpoint. So when you edit the object, you might want to also change the viewpoint. Okay, so to facilitate these functions, we actually train the model to predict both the 3D appearance and shape, as well as the 3D labels. Either can be a sketch label map, also can be a 3D semantic label map. Okay, and this allows us to modify. So once you generate the object, you can change to a different viewpoint, and you can modify the shape of the car, make it more round from a different viewpoint. Notice that this edits is very hard to achieve if you do a left-facing viewpoint. Okay, so here is how the interface looks like. A user can create a scribble, and we can generate a car. And you can further edit it, and we can further refining the edits. Okay, it not only works for the cars, but also work for like other objects like cats and faces, and some other cats. So let's see how it works. So the basic idea here is the input is a 2D label map, and we would like to produce both the images and the 3D labels, which is encoded by a NERF model. Okay. Okay. Here is how the visualization of the 3D label map. Okay. One requirement for the training data is we do assume we have access to the images, and we can run a segmentation model, or we have ground truth label map, and we also assume that we know the camera pose in the training time. The pose and label maps can be obtained by the off-the-shelf models for certain categories like cats and cars and faces. Might be harder for some other categories. Okay, and we can sometimes get the parts labels by clustering the dyno features. So we can get edge labels by using long edge detection method. So now, given this training data, let's see how it works. We start with a very famous architecture by Eric Chan et al. Called EG3D. So the idea of EG3D, I'm pretty sure people are very familiar with, is you can have positionings and condition on the latent code. It can produce density and color here. Okay. And then you feed a discriminator, and you apply a GAN loss to make sure the rendered 2D view of generated images is the NERF is still realistic. So one thing we can do is we can just simply add this conditioning to the EG3D, which we call a baseline called EG3D-C. C means conditional. So here the idea is you can just tune an encoder to encode your label map and to the latent code, and you rest of it is exactly the same as EG3D. Okay, and now you can render the view as well. This is our first attempt. Unfortunately, it doesn't work that well. I think it does generate some realistic samples, but the one issue here is the alignment between the output and input is not very good. For example, here you can see this forehead is different from does not respect the hair labels in the inputs. And sometimes you put a glacis, it doesn't respect that as well. And it just doesn't, it can produce realistic samples, but it does not respect the input. So the reason for that is, one of the reasons is there might be two reasons. One reason is we have an encoder and encoder all the spatial information into a very narrow bottleneck, so it loses lots of high frequency information in the input. And the second reason could be we are not explicitly designing a loss to ask the network to respect the input. So we made some modification to these baselines. The first thing we have been doing is we ask the network to also predict the semantic logics, like either the path labels or edge labels or semantic labels. So the network can render both the image as well as the label map. Okay. It's very simple. Just add an additional branch to predict the semantic logics. Okay, and then in the training time, we ask the network to produce both the semantic logics and intensity. You can get the semantic logics very easily by this is your standard NERF formula, but you just need to also ask network to predict the semantic logics along each point in the array. So it's very, very straightforward. And during the training time, so there are two types of scenarios. One scenario is we given the ground truth image. Since we already know this is the ground truth image, we know the pose of the ground truth image. We can generate image and minimizing the reconstruction loss. between the render image as well as the ground truth image. And since we can also derive the ground truth label map, so we can also render this model in that particular viewpoint and minimizing the reconstruction loss in the semantic label map space. But for other cases, which we can also add a GAN loss to make sure this looks realistic. But for other viewpoints, since we are interested in generating this image in different viewpoints, we can sample a novel pose, and we generate all kinds of semantic label maps. We generate all kinds of images, and we can ask the network to produce these images. But since we don't have access to the ground truth of the rendering at novel poses, all we can do is we can enforce a GAN loss to make sure the rendered label map looks like a natural label map. The rendered image looks like a natural cat images. So we do that 50% time with novel poses and 50% time with ground truth poses. And here is our results. You can see our results can respect the input label map much better than a baseline model just by adding conditioning to image 3D. Okay. Additional things we have done to further improve the results, especially for editing, is we would like to make sure, given the different, given the label map of the same person at different viewpoints, we should be able to generate exactly the same 3D shape. So we call this cross view consistent loss. So the idea here is we would like to start from pose 1, and then we can generate a 3D label map. We can sample a different pose called pose 2. We can render this 3D label map at pose 2, and then we apply the step back again and try to generate the 3D nerve object, and then we can render the semantic label map at pose 1. So this is kind of like cycle consistent loss, but just with pose 1, pose 2, back to pose 1. Okay, and this allows us to roughly keep the identity of the object, building the user editing, where if you user want to change different viewpoints. And this method works much better than some of the previous work as well. And here I will show more results. Okay, and please check our website for more results. Okay, and here we show a visualization, which we basically try different input layout as well as we sample different appearance code. And this can give us to generate an object with the same input, but with different appearance. Okay. Here is a video of it. Okay. So this work still has a bunch of limitations. First, it's if you input a very strange sketch inputs, it will tend to generate something which are within the data set. So it's very hard to generate a car with a very unusual shape. It does not generate very well to out of distribution user inputs. And more importantly, we are using EG3D, so you have to train a separate EG3D model for each category, right? So if you train a model on cars, you cannot use it to edit cats. So it's very category specific. And more recently, people are more interested in like generic text to 3D generation rather than the category specific ones. So there are lots of nice papers like Dream Fusion, Magic 3D, and there are lots of interesting follow-up papers and which very recently. Okay. So one issue we do observe from recent text to image to 3D method is this issue of the baking lighting. For example, here is the results from very nice recent work of Fantasia 3D. It produced very nice results, but you can see some of the lighting has been is baking them in the texture maps. So if you change the lighting, you put the same assets in different lighting environment, it will look the same. So which is a little bit strange. So in very recent work, we proposed a new method, again, it's led by student Kengo in collaboration with Roblox as well as Stanford Manish group. So the paper is called Fresh Text. So we try to generate relatable textures given given an input mesh with light control net. So we'll talk about what light control net means. So here are some results. Is we given the same mesh, we can type different kind of text prompt and allow you to add different kind of texture to the input mesh. Okay. So here the input and output. Input is the input mesh provided by the user, and the user also needs to specify a text prompt. And our goal is to produce texture mesh which can be rendered in different lighting environments. Okay. And there's lots of prior work was trying to generate this kind of PBR material map. For example, here the Fantasia 3D will try to generate the diffuse term, the roughness term, metallic term. So and it does generate PBR map, but the map is not very disentangled with the lightings. So and we were wondering what was the issue here? Why the Dream Fusion type of approach always create baking lighting in the results. So I'm pretty sure everyone is very familiar with Scott distillation loss, but just give a quick recap. You try to produce some material, try to render it, you add some noise. You ask the diffusion model to predict your noise and check the difference and try to do the backpropagation to the framework. But one issue here is to render an image, you need to specify the lighting, right? So you, in addition to the material and the geometry to render an image, you need to specify the lighting. Now the question is, which lighting should we use? And okay, maybe you can use a predefined environment map. You can manually define some lighting, sample some lighting. Maybe it's okay. But the most serious issue here is you sample a lighting L star. Diffusion model might produce an image or produce a noise about this image, and that image or noise may not correspond to the lighting you sampled, right? So this is the biggest issue: is you sample lighting, but the diffusion model may not respect the lighting you sampled, and we are not aware of that. And then all this the lighting difference between the lighting in the generated image versus the lighting you sampled, the difference will be distilled into the texture map. So this is the one of the issue we have observed. So our solution is try to add in controls to this Scott distillation loss. The control can include the shape, but it can also include the lighting explicitly. So we will teach the diffusion model which type of images we would like to generate, which type of lighting we would like to generate. Okay, so our main efforts is trying to make diffusion model be aware of the lighting. And we use a very standard approach called control net, which hopefully we can tune a control net conditional on the geometry as well as the lighting. Okay, so our proposal is to feed the control net, the text prompt, as well as a shaded image under a specific lighting conditions L star, and also with different materials. And we can train this model using some synthetic image training set like Observerse, since we are the one who rendered the final image. So here how it works, we sample a lighting and we apply a different type of materials, can be non-metal, non-smooth, half metal, half smooth, and pure metal smooth. And then we can render three shaded image under three different materials with the same lightings, and we can concatenate these three grayscale image as RGB image to the control net. And so this is control net inputs. You see a shading image at different with different materials as well as text prompt, and the control net is asked to generate this image, which we render using Observerse. And now, and we call our network light control net. And once you have this network, given the same input, you can render, you can feed different text prompt, and it will generate an image with different material. But interestingly, it will follow the input lighting conditions very precisely. So even it has different material, it follows the same input lighting conditions. Okay, But you can also render the same material with different lighting conditions and it still follow the lighting conditions. Okay, there are some more details about how to train this network. For example, we need to come up with some name and tag, and we also need to extract some original texture material. And then we need to try these 3 different types of conditioning material, and this is our training inputs. And once we train a light control net, we can directly using this light control net with a standard framework like score distillation laws. And here we use a particular representation called texture hash grid. So and we sample a random views and lightings. And once we sample our lighting, we can feed this lighting, we can render the shaded images, and we can feed these lighting conditions to the light control net, and we can still add the same noise, and then we can prediction noise using the light control net, and subtract the difference and backpropagate to these networks. But the interesting thing here is since we using a light control net, the light control net can give us the correct noise prediction given the same lighting conditions, which are follow the same lighting conditions which we use to render this image in the first place. Okay, so this is the basic idea. To initialize it, to make it much faster, we have 2 tricks. One trick is we can actually initialize the network with light control net as well using multi-view prompting. This is our initialization. And we can use this image as our to train the model with reconstruction loss. Okay, so we can just take feed forward pass, and then we get these images, and we can use these images our reference image using reconstruction loss to optimize the texture maps. Okay, and this will enable us to get much faster results because the score distillation sampling is very slow. Compared to direct reconstruction loss like LPIPs or RGB loss. And another thing we have observed is to compute this SDS loss, you have to pass your network to VAE encoder in the diffusion model. And eventually we found out actually this VAE encoder takes 50% of time of backpropagation. So most of time, half of time you will spend your time on these VAE encoders. So to speed up this part, we actually distill this VAE encoder, which takes more than 100 milliseconds, 500 milliseconds to backpropagate the gradients. We distill it into a small network, remove some attention layers, and our distilled encoder is about 42 milliseconds for the forward and 81 milliseconds for the backward. And the backward is, we do care about backward because we are using the SDS loss to optimize the texture map. So by doing that, we can actually speed up our method from 1 hour. If you initialize the texture map using light control net, you go to 10 minutes. If you distill your encoder, you can reduce the inference time from 10 minutes to 4 minutes. Okay. So again, a quick recap of the pipeline. We used our light control net with multi-view prompting to generate consistent multi-view images and use this as the reconstruction loss to initialize the texture hash grid learning. And then we further apply SDS loss again with the help of light control net to make sure we can disentangle the lighting and materials in the SDS loss. Okay. And we use a very standard like PBR representation, like which includes the whether it's metal or not, the roughness, bump map, as well as the base diffuse color. Okay, and here is some results comparison. The first row is Fantasia 3D, and the second row is our results. Our results is not perfect, but does a better job than the baseline. And here we show our material rendered with different lighting conditions. Okay, and here are different environment maps. Two additional environment maps. Here are more results. Again, please check out the website for additional results and comparisons. Great. So again, promise I will keep it short. So in summary, we talk about three different ways of adding user conditioning, like user scribbles, to a pre-trained 3D generative models, either as game models or diffusion models. And there's different ways, and we can add controls as constraints and do some optimization. We can add constraints as conditioning inputs to the network, so it works much faster. And also, more recently, we are interested in adding these controls to the score distillation sampling loss. Thank you. Yeah.
All right, thank you for that nice talk. If anyone has questions, you can use the microphone in the middle. We have time for several questions. Maybe I can ask one while people line up. So you talked about this trade-off between using constraints for optimization and direct conditioning, and ideally we'd like to do direct conditioning for a lot of this, but for really fine-grained control like the edge maps you showed, or maybe 3D constraints, it's much easier to do with optimization. You get a lot more accuracy, I guess. So do you think like moving forward, we should be doing a trade-off of using both of those, like conditioning first and then optimization on top of it? Or can we get conditioning to the point where it's accurate enough to just directly do a feed forward pass through a network and hit constraints exactly?
Yeah, I think this is a great question. So I think one thing we have seen people doing in the 2D editing is you always apply the feed forward encoder, and then you try to optimize for like 10 iterations. So that's, again, depends on how good your encoder is and how much iteration you need. But I think a hybrid approach is very promising for 3D editing as well. Yeah, thanks. Yeah.
Hello, I have a question about flash text. In this work, you trained a control net that is conditioned on lighting, right? But I think you do not explicitly control the material properties to be consistent across different generations. So is it possible that the generated material properties are inconsistent, so the optimization process may be slowed down?
So yeah, the question is whether we enforce the material to be 3D consistent, right?
Yes.
Okay. Yeah. I mean, we do use the 3D like hash grid, right? So so you need to so given XYZ position, it will produce this PBR material. So it's kind of 3D consistent by default, and then you need to project into a 2D. So we use a 3D hash grid.
But your generated image may reflect the material properties, right? But the generated images, the material properties in the generated image may be inconsistent. Is it right? So you are using generated images to optimize the material properties.
Yes.
And the material properties in the generated images may be inconsistent. Is it right?
I think since we are using a rendering to render the 2D image given the 3D asset, so it's kind of it's consistent by default. It may not be correct. You maybe still have some like baking. It might not be perfect. I think it's consistent by default when you render like a 3D asset with material into 2D image.
Okay, thank
but
you.
it may or may not be correct. So yeah, okay.
Thank you.
Yeah, thanks for your question.
All right, with that, let's thank Junyan again and all of our speakers from this morning session.
Thank you.
So now we're going to take a lunch break until 1:30, where we'll resume with more keynote and spotlight speakers. Thank you. It's starting to upset me. We need to shift the project. My intern job, they had a guy from Microsoft. Really great practice. Loved the idea of PDB. Tried to get it looking at there too. And eventually they fired him because he kept missing deadlines. He was insisting on hitting sort of system speed. And like we like 4 or 5 developers, including myself. And it just everything took like 2 weeks, 2 or 3 weeks longer. I asked the question in chat, like, hey, does the project, my manager know, does Cody know that he wants to increase our schedule? Like, I got no answer. I mean, like I said, I did it for like 6 months. It's a different way of thinking about it. Just the problem is that like, you spend half the time writing tests. And one thing that I can tell you is that obviously tests have bugs too, of course. So it's you're introducing more opportunity for bugs. Plus, everybody has to be very familiar with something like that. I don't think that maybe we can like optimize testing and testing. He did read through the PR by himself. You've heard everything in the last week. Yeah, I think actually that is I would say that like I would end up just asking I was like, hey, I have this feature, and it didn't matter. Like, one time I think TJ was meant to hear, buddy, and like he just couldn't get to it. Do I just sit here then? Yeah. And it was like, okay. And so what happened is that I ended up being each other's PR money every single time. And I was like, I don't know if this helps any different than what we previously did. Yeah. TJ definitely tried to introduce a lot of like more advanced content. So it's the big kind of the rest of us are like, okay, yeah, we'll fill in the rest. Yeah, so we joined right when we were doing like design documents. That we had our chance to do it. We didn't get it done. I think it's going to be one of the things that. So I told them like, my job now is to slowly refactor across architecture until it's like getting usable space, and that's all we do.
slowly start taking it to code over time. The thing is that once you put it in the field, we will never, like, we'll never rewrite it because the process of that stuff is like, okay, we have to deploy the site, we have supported code, therefore always have to do that. At least, well, if we do a rewrite, we then have to go through the whole process of re-improving our pipeline. And that's going to take a long time. And I guarantee that the sales team is going to bring us a customer around the customer saying, hey, new products, you know. So I'm trying to push the emphasis that data that we can take product, you know, okay, 3D content creation, add it into simulation, use Aurora to stylize it better and get it into training. We have a chance that we're not going to be candidates. I think that's what the ultimate side of our failure is, that we start innovating and training. Every single time that we do that, it costs us more. Section, like what we do right now, we take an image and I saw in some paper that people were trying to use that for automatic notation. So they would, you know, you have a decent model that picks, and they basically take the change detection and they keep that as the notation. And they pick a bin, and then they have to cycle it around. So it's like if you pick a whole bin, and just completely automatic, pick a whole bit, you export the annotation from everything on top, and then we pick to another bit, basically dropping it, and you just keep going back and forth, building an annotation. It's kind of slow, I mean, but it's more accurate than human annotation. Not that that's like, oh my God, you know, they're definitely having issues. I think the problem with those types of systems would be difficult. I would be, I'd probably don't do something like that because someone has to think, why did they grab this? Or like, why did they miss this? You probably, you know, and it's kind of a game that have a lot of time, it's research money, but hard for explainability around the concept. Yeah, like the things I get asked, like, I made the whole like big order system for Ultra, and like people ask, well, why did they do that? Why did they do that? I'm like, okay, here are the rules. Like, okay, early on, my boss Joe asked me, oh, well, why did they do that? Like, because the algorithm had to oh, it would be better. So I made a game, and I said, okay, pop it up on your web browser, and it gave you a list of all the boxes on the wall. But here are your candidates. Pick which one you want. And so you could enter the box number, go all the way through it, the algorithm would sort it, and it would be like you were X percent faster, so yeah, here's my algorithm. I was like, okay, you know. Some of the other engineers, like James, they like put it in their face like play it. And I think James figured out a couple of quirks that made it faster too. So I was like, oh, that's cool, great. So something came out of it. Yeah. If I was to try to do that with like AI, because I've seen like stability prediction algorithm. There's a shape stack that they basically stack of blocks, and they move the bottom, like say, oh, which of these is stable based on the movement. And they were using that to predict sort of how to unstack columns. And I could put this in there, but inevitably it would come down to the AI to help. That's not what any customer, or that's not what Joe wants. Also, it's very hard to produce like physical robotic constraints. But for instance, we pick on the side of a code, you know, like there's no good way to tell beating up what's not feasible. But then you have to worry about how well that type of the provider. That affects the code. Final one sharing. They're like, oh, like 503 says, okay, so, kind of say that. We're out of time. We got this one. Always funny, like, I talk to people that use like full TV like protection stuff, and they're like, why is it, you know, their system gets like 50% accuracy, and like you give them 98, but why is it missing this one thing? Massive increase. But I think next step. annotate all pickable, or I can annotate like one optimal thing. Make it equal. Yeah, I like that. No, you're good. for the weekend, 60 to 80. I'm a little cold, but I'm like, oh, it feels so nice. Uh, it's nice there. Yeah. But I went the wrong way. So walked around like a park. I was just like, nah, PJ no. Yeah. Funny thing is that so it's like pretty small. No, it's like I think I've been around Dallas. Traveled a bunch of them. one of those things like
All right, hello everyone. We're going to get started with the afternoon session here. Our first speaker is Gordon Wettstein, who's an associate professor of electrical engineering at Stanford, where he leads the computational imaging lab and co-directs the Stanford Center for Image Systems Engineering. Gordon works on really an impressive range of topics, including computer graphics and vision, AI, computational optics, as well as applied vision science. And as part of this, he's really been at the forefront of work into modern 3D representations and neural fields since he published Scene Representation Networks back in 2019, and has really since been continuing to innovate on these 3D representations and generative models. So today we're going to hear from him about fun with generative AI. I'm looking forward to it.
All right, thank you for the introduction and welcome back to the afternoon session. I'm Gordon Wettstein. My appointments are in EE and also in CS. So traditionally, I've been working on a lot of image and display systems engineering. So examples like that include design and fabrication of novel types of VR and AR displays or imaging systems. So for example, just 2 weeks ago, we published a paper in Nature on full color 3D holographic AR displays with Meta Surface waveguides. I'm not going to talk about this, but I'm going to use this as an introduction to tell you that typically I give talks to the optics and physical sciences audience on why it's important to have a display embedded in your eyeglasses and all the cool experience that enables. But today I'm going to make the argument that for many cases, you don't actually need a display. Building a display into your eyeglasses is really important and really difficult also. So, but in the near term, we might be able to deliver real value to consumers using a stylish form factor by simply embedding a camera and an eye tracking system into a pair of iframes and connect it to a multimodal LLM. We call this Gaze GPT, and it's a really fun thing. You can think about it as an interface between the user and the generative AI. And it's actually really useful. So let me just introduce that. So many of you probably know what a multimodal large language model is. GPT-4V, for example, you give it an image and you ask it a question, for example, you show these bananas and ask how many calories are in this. And these multimodal LLMs are very good. It tells you that, you know, a medium-sized banana contains about 105 calories. Cool, that's great. So now imagine you have a camera that looks into the world embedded in your eyeglasses. It's going to see a lot more than just one banana. If I just look into the room, there are about, well, the room isn't quite full, but there's quite a few people in this room and lots of different things. So if you ask the same question on an image like this, you know, how is the LLM supposed to know what you're actually referring to? So this is where we dive into the topic of contextual AI. Contextual AI is this idea of knowing everything there is to know about the user through various means, and then helping the user achieve a task faster or more efficiently that they want to do. And there's a lot of gadgets out there that are fostering this. For example, Meta and Ray-Bans have partnered to develop smart frames. There are some wearables like this AI pin, for example, and there are even dedicated smartphones now that are just meant for AI applications. Now, how successful are any of these in the market? Well, I think time will tell. But the basic idea is that each of them have a camera that sees what the user is seeing, and they help the user understand their world around them. But they use different interfaces for how the user can select an object and pay attention to something specifically. So the frames are pretty intuitive. The camera rotates with your head because the camera is basically attached to your frames, which rotate with your head. The wearable, not so intuitive. You basically have to rotate your body in order to select something. And without visual feedback, that's actually really hard to do if you've ever tried this. A smartphone is really good at that because it has a viewfinder. It shows you what it sees, so you can naturally align the phone with whatever object you're trying to interact with. So now going back to this example of the fruits, if I asked the GPT-4o how many calories are in this, it just has no way to know what I'm actually referring to and what I'm paying attention to. So it's going to give me all the viable answers there are and tell me about everything that it sees in this object, in this scene. And that's not really what I want. So it lacks the specificity, it lacks the understanding of my attention. And so this is where the gaze part of Gaze GPT comes in. Gaze is, or vision is our most important sense, and the eye gaze direction is a super fast and natural interface for providing precise context about our attention. A gaze tracking system basically measures the direction the eye is pointing, and thus where the user's gaze lands in the scene. So with the gaze, you can index into the world-facing view, and you know exactly what the user is looking at. Gaze tracking systems have become very small and performant. For example, it's used in the Apple Vision Pro. You've probably seen that there's 2 cameras per eye that actually track your gaze, and they replace the mouse, the keyboard, many other aspects of the interface, and replace it with this gaze tracking system and also hand gestures. Now, we've been prototyping with these types of ideas for a couple of years now, and one thing that we put together was a prototype system that looks like a pair of frames. It has a world-facing camera. It's basically just a high-resolution webcam that is pretty wide field of view. It has a microphone, it has speakers, and it has a binocular eye tracker in here. And what this allows you to do is basically track the gaze, index it into the scene. It has speech to text and text to speech embedded. This was GPT-4o, but it's basically doing the same thing as GPT-4o. And then you can basically just go around in the world and ask questions, and I'll just show you a video of what that might look like. Hopefully we get the sound here. Do we get sound?
Do I need to water this one frequently? Let me look that up for you. No, it does not require frequent watering. Allow the soil to dry out between waterings.
Okay.
What is this plant called, and does it typically need a lot of maintenance?
Is there something I need to do for the sound
Let me
here?
look that up for you.
Or just... Sorry, I don't think the sound works. Oh, no, this sounds.
Oh, the echo. We need to shut that off. Do you need to share the sound? with the rest?
I do need to share the sound, yes.
Okay.
Oh, okay, cool. So I think you get the idea. This is real time, it's not staged. This is a one shot type scenario where we just captured it walking past the person who's using it. We didn't do it 100 times, we just did it once. You ask the question and you get an answer, and the answer is very reasonable. So if you ask about the plant, it'll tell you how often to water it, for example. Okay, but how do you get sound on here? Oh. I'm not
The
getting
plant
sound. Oh.
is a Sansevieria, commonly known as snake plant. It is low maintenance and can thrive on minimal water and light.
This includes supporting multiple languages.
Cum îl cheamă pe caracterul ăsta?
Let me look that up for you. Acesta este Zuma, un personaj din desenul animat Paw Patrol.
I don't know if you have kids, but they love Paw Patrol.
And translation of the user's surroundings on command.
What does this say?
Let me look that up for you. The text says, Kein Zutritt außer für Befood, which translates to no entry except for authorized persons in English.
Okay, so this is just a really fun thing. It works in many different languages. We tested it in Spanish, Portuguese, Romanian, Polish, German, English, French also. It's just baked into the LLM, right? Like we didn't do anything special for this, but it's just such an intuitive interface to put this on your pair of eyeglasses And we ran a whole bunch of user studies and we're able to show a few intuitive things. So there's not anything surprising there really, but it was good to quantify it. And the thing is, like, how accurate can you select something? Well, if you use a phone and you have visual feedback, you can very accurately select something because you get the visual feedback. If you use your body without visual feedback, it's horrible. You don't know what you're pointing your body at. It's just not a natural way to select something. If you use your head, it's pretty good. But as humans, we use gaze as a visual selection mechanism within maybe 35-degree cone or so. So you can get a rough sense for what somebody's looking at, but it's not super accurate. And so gaze is very accurate as a way to select objects in the real world. And that's reflected in this scenario. So the gist is that for no visual feedback type devices like eyeglasses, gaze is the best selection mechanism, and this works really well. The selection time is actually really fast for gaze because it's just so natural. For phone, it's not so fast because you need to pull it out of your pocket. You need to aim it at something and then start the app or maybe double tap some buttons, and that all takes time. And the accuracy is directly related to the selection error. So if, the accuracy isn't very good if the selection isn't very good, because if there are a lot of objects in the scene, then you're going to get the wrong one, right? So this part of the talk had nothing to do with generation, and this is what this workshop is about. So I want to dive a little bit more into that topic, but I just wanted to give you a sense of what my team is sometimes working on. It's this really fun intersection of wearable devices, AR, VR, and generative AI. So let me talk a little bit about what the rest of my group is doing on 3D generation, for example, with camera controlled video. So all of us have probably seen the recent announcements. I mean, Sora was the first, Luma came last week, Runway just came, when was it, this morning or yesterday or something? I mean, this is amazing, like, wow. We live in a time where we can generate photorealistic videos, right? I mean, it's fantastic. And the step from the last generation, like Animate Diff and so on, to these diffusion transformers is pretty large. So I think we're starting to see these tools being really useful. I think we're not quite there yet in terms of like having them being useful for creators quite yet, because there's a lot of prompt engineering around it. And prompt engineering is just not a natural way to create content necessarily. So the question is, like, how do we take a really capable model like this and make it useful for creators who are not necessarily super technical and who are not well versed in engineering prompts that are 100 lines long? So one of the first things that you might want to control is the camera pose, because imagine you want to have a certain shot and you want the camera to move in a certain way. Well, text to video generation models don't enable that out of the box. So we've been thinking a little bit about how to do that. And, one simple way to do it is to think about this as a conditioning signal. So you could take the camera pose and then condition the video model based on the extrinsic or intrinsic parameters or a combination of that. Or you can use those and also some kind of a plucker embedding. You just need to find a good way to encode the camera pose in a way that the video generation model can understand it and translate it. So the way we prototyped this was using a combination of plucker embeddings that are happening per pixel, basically, and the extrinsic parameters of the camera. That goes through an encoder that generates features that are then injected into a pre-trained video diffusion model. In our case, it was Animate Diff. So with that, you can generate videos with a prescribed camera motion, and the quality of these videos isn't exactly the same as we saw in Sora just now because it's limited by Animate Diff, but the idea is directly applicable also to things like diffusion transformers. So I think this is something that we're definitely going to see very soon. And with that, you can enable text to video generation using a prescribed camera trajectory. As you can see here, looks pretty plausible. I think the results, at least qualitatively, aren't hugely degenerated from the original Animate Diff quality. If I don't have that as a reference here, but we evaluate that quantitatively also in the paper. And then you can also do things like image to video generation. So you specify a single image along with a camera trajectory, like zoom into the image or move left, right, down, rotate, and so on and so forth. And that works quite well. And it also works with a lot of the customized video model. So if you want to have something that looks like a Van Gogh or some kind of a stylization, it works pretty well. So we did some initial experiments on this camera-based conditioning on diffusion transformers, and it seems to work there as well. So it's definitely something that we're going to see pretty soon. Okay, so we can basically think about 3D generation as in one of two ways, at least I do. One way is we take a video model and we add camera control. That gives us a 3D model because we can move the camera anywhere we want, right? But one of the challenges is really that the camera control with conditioning isn't super precise. So the camera motion looks correct qualitatively, but if you were to do some kind of a structure for motion on that, you're not going to get the exact camera poses back, right? And in many cases, that's what you want. You want to be able to precisely specify the cameras. And that's not really something you get. You're going to get guidance on where the camera might move, but there's also no guarantee that it will. So it is a little bit challenging to control still. So the other way to think about it is, well, we could use a 3D generation model and add some type of an inductive bias that forces the network to generate something in 3D. And we could do that with a 2D diffusion model or a 3D diffusion model, and I'll have some examples of both of these. So when we first started thinking about this with my student Eric Chan, we thought about it in this context of, well, we don't have any 3D training data, we don't have any 3D diffusion models, we really only have 2D diffusion models. So back then, back in the day in 2023, which was just a year ago, this is a fast-moving world, right? We thought about, okay, we're limited to 2D diffusion models, and what we're going to do is we're going to try to be clever about how to force this 2D diffusion model to be as multi-view consistent as possible. So what we did is we took an input view, and this is single image condition novel view synthesis. So single view comes in, we take a CNN, extract some features, we're going to lift these 2D features into 3D by using just a back projection. We're smearing them along the rays, basically. So there's nothing really clever about this. We're going to take this 3D volume within the frustum and re-render it into our novel view. And there, we take these features and send them through, we use them to condition a 2D UNet decoder. This is a diffusion model, and everything is trained end-to-end because Eric was doing an internship with NVIDIA at the time, so we were able to do that with their GPUs. And it works pretty well. We presented this last year at ICCV, and the basic idea is that you can take a 2D image like this fire hydrant, and you can now control the camera explicitly. And again, it does that by extracting the features, lifting them, reprojecting them, and then injecting those into the 2D diffusion model. So at the time, we had Viewformer and PixelNerve, which were slightly different approaches to this, and our approach called GenVS. And GenVS works very well. It's very sharp. And the main insight is that approaches like PixelNerve that are trained on an L2 loss will just gradually get more and more blurry as the target view moves away from the source view. There's just nothing you can do about it because it basically averages over all the possible scenarios that could explain the single input view. And GenVS basically samples from the posterior and gives you a very plausible answer. We did a lot of engineering about trying to make it consistent to reduce the flickering, because that's the main challenge here. It's not that getting it to be multi-view consistent, it's actually to reduce the flicker. But it works reasonably well. And we were able to do this also for room scale things by training it on Matterport 3D. So again, on the left, you see the input view. There's look outside the room, which was the state of the art at the time. And in the middle, you see these generated views from GenVS. They look good. They look plausible. They don't look like the reference. So this is not a reconstruction task, right? This is an ill-post inverse problem. Ill-post inverse problem, that means there are infinitely many solutions that are equally good. We're not trying to find the original scene because it's impossible to see that. There are many parts of the scene that are not part of the input image. We're just trying to generate something that looks plausible, that looks like it could have been there. And that's exactly what we get for a limited sequence, which is, in this case, fairly long. So again, we actually did this work about 2 years ago, and then it was only published at ICCV after. A related idea is something we explored more recently, where we focused a little bit more on humans, and we wanted to extend this idea to 4D. So when I say 4D, I mean it's supposed to be 3D and also dynamic in time. So we call this generative rendering because we're using a lot of ideas from the graphics community. And what we're doing is we're rendering a template, a very coarse template, in this case, a simple mesh with UV coordinates. We're now using the simple conditioned single image generation approach, stable diffusion in this case, with a text prompt, and we can generate, well, whatever you want to generate, in this case, a manga of the Joker dancing. And now what we're trying to do is use the features from the diffusion model and reproject them using this template mesh, because we have ground truth correspondences via this template mesh in 3D from one frame to another, right? So we don't even need to lift anything or learn this correspondence. We actually have a template that's pretty good, and we can use the template to reproject our diffusion features. So it works okay, and then we can animate it. It looks fine, mostly consistent. There's a little bit of flickering. I can run the same example with many different text prompts, and it works okay. So this was all done before any video diffusion model was really available, right? So this is all sort of like image generation model. With a video model, you could do the same thing and probably get a lot more consistency, but it looked pretty good. This is actually a paper that will be presented later this week at CVPR by my student, Shengshu Kai. So if you're interested in this topic, stop by the poster. Now, these are all small steps towards something that, you know, serves as a 3D foundation model. So what's actually a 3D foundation model? Well, we want to build a 3D model that is perfectly multi-view consistent, ideally, and that enables a lot of different downstream tasks. And by downstream tasks, I mean things like text to 3D generation, cat wearing eyeglasses, a beagle in a detective's outfit. So 3D objects that you never see in reality, right? But equally, we want the foundation model to enable other tasks like single image to 3D generation. And again, this is something that you couldn't do with reconstruction. I just want to stress that. Most of you will probably know this, but you can't nerf this or do any kind of 3D reconstruction simply because there's only a single input view. There isn't enough information to know anything about how this Louis Vuitton purse looks from the back, simply because you didn't see it, right? There could be a cat hiding behind this bag and you wouldn't know it because you just don't see it. So the best we can do is hallucinate it. We need to hallucinate something that is plausible. And because the model hopefully has seen many different Louis Vuitton bags from many different angles during training, it will come up with something that looks plausible to you. And this works pretty well. These are all results from a paper called a Gaussian reconstruction model that I'll tell you more about it in the next slide, but works pretty well. And another thing that we might want to do is a multi-view image to 3D reconstruction. So we think about this as reconstruction, but it's really a sparse view reconstruction. So we're thinking about maybe 2 views, maybe 4 views, and you still want to get the full 3D scene out of this. So this would be more constrained than the single image to 3D case, but it's not as much constrained as a NERF where you need hundreds of views of the scene to reconstruct it. So it's not a reconstruction task. It's really a constrained hallucination task where the constraint are the 4 input views. You want to make sure that from those camera poses, the scene looks like those 4 views, but you have to make up what happens in between. And so what we looked into, and by we, I mean mainly my postdoc Yinghao and our collaborator Zifan, was this architecture that was using a pure transformer, takes the input views, 4 input views. It uses a standard vision transformer to tokenize them, and then has a pretty standard transformer architecture, but with a upsampler architecture that's based on pixel shuffle. And what it basically does is it's a transformer that takes 4 views in, and that still gives you 4 views, but it translates the RGB values in each pixel to pixel-aligned Gaussians. So it takes the RGB values and turns them into all the different attributes that you would expect from a 3D Gaussian. And so now you have 3D Gaussians aligned with each pixel of the 4 input views. They define your 3D scene, and you can change the camera as you please. Now, importantly, we really trained this sparse view to a pixel-aligned Gaussians module as a transformer. We did not do the single image to multi-view generation or text to multi-view generation because there are a bunch of tools online that already do that part. So we just use them out of the box, like Instant3D, 0, 1, 2, 3, ++, or tools like that. They are fully compatible with this model. So this was a really big step forward, I think. And you can use this to understand 3D scenes too. You just have to break them up into individual objects. So this is an object-centric 3D generation model. But for a complicated scene, you can use SAM or your favorite segmentation technique, identify individual objects, segment them out, and then do a single view reconstruction of those. All right. Oh, and I should mention that this happens in like a second or so. So this is really fast. Compared to SDS-based approaches that we've seen in the morning session, they take a long time to optimize. This is a single feed-forward model, is one example from a class of emerging feed-forward 3D models. So these are really fast and really good. So good stuff. On the 3D side, why are we not seeing results that look as good as Sora yet? I mean, it's partly because of the lack of available training data. The internet is full of images. Lion has 5 billion images. I mean, you know, if you train an image generation model on 5 billion images, it's probably seen everything there is to see on this planet. Maybe not your cat or your dog, but you can customize it with just a few images. If you think about videos, there are not quite as many videos out there, but there are a lot of videos. And we can train video models based on this vast amount of data. For 3D, that's really not the case. We have Optaverse, which is great. And I congratulate the Optaverse team on letting all of us work on really interesting projects on 3D generation, but it's just not enough, right? If you look at the diversity, these are all computer-generated assets that look like computer-generated assets. They don't really look like photorealistic content. And we have about 10 million of them, maybe a few more. So 10 million 3D objects versus 5 billion images in Lion, that's like almost 2 orders of magnitude of a difference. So, you know, we need to close this gap or be really smart about how to do it. So this is a really great research topic. And for all of you students out here in the audience who are thinking about what to work on, I think this is a pretty good topic because 3D is just not quite solved yet. Maybe in a month it will be because we're moving so fast, but who knows? There is, again, as I said, a ton of training data out there that is photorealistic, that is just single views of a person. For example, FFHQ is a data set that NVIDIA compiled a couple of years ago already. They trained all the GANs on this. That has 70,000 images of faces that are very diverse. So it's not 5 billion, but for this specific category, it's pretty good. And we're starting to see large-scale 3D data sets like DL3DV coming out, but these are also very small. So one question is, can we train a 3D generative model on 2D data? Well, I'm going to go back in time just 2 years. It seems like an infinite amount of time by now, but back then we worked on exactly that idea. How do we train a 3D generative model on 2D data? It doesn't seem easily possible, but back then we had GANs. We didn't have diffusion models yet. And it actually worked really well. We came up with this idea of a triplane representation to represent a scene, and it's actually pretty widely used by now for many different reasons. But some of the reasons why we developed it in the first place in our paper called EG3D was that we can use a 2D CNN-based generator, generate the features on these multiple planes. We can treat the scene as multiple 2D planes. We can rearrange these 2D planes into 3D. And then we can render them using volume rendering. And it's also much faster to query this, you know, sparse volume if you want, or low rank volume. That's how I think about it, than to query a neural network. So it's much faster than NeRF, for example. And we just have a very lightweight implicit decoder on top of it with an feature aggregation function. So really fast, compatible with 2D generators. And it allowed us to train 3D GANs on 2D data that were pretty multi-view consistent. So here's a couple examples. You've probably seen these already, but we can explicitly control the camera. This person doesn't exist in reality. They're generated. The GAN has never seen any depth maps during training. It just learns that there is some depth that helps it to be more multi-view consistent. It's very diverse. It's very fast. It can generate all of this in real time with more than 30 frames per second. So that's different from most diffusion models. It's category specific, so it can't generate anything. But it looks really good. And I think just 2 years ago, this was sort of the state of the art in 3D generation. I just wanted to show it because I think all the cleverness came from the design of the inductive bias in the form of this triplane representation. And, you know, most of us don't use GANs that much anymore, but I think being clever about how to design the architecture and how to combine, you know, generation architectures with inductive biases in a meaningful way can be interesting. Okay, so here are the cats. I loved this example back then because it showed you that this is an AI and not real, because you can do interpolation in the latent space and you get semantically meaningful results. So this shows 3D semantic interpolation, and these GANs just have a nice, smoothly varying latent space, which is very nice. And most diffusion models don't have that. So, you know, yes, diffusion models are awesome, but it's hard to make them well behaved and interpolate things in the noise space. We worked on many different follow-up projects like LumiGAN, which was an idea of not generating the pixel colors directly, but the normals. The normals come automatically from the density, but the albedo and the diffuse and specular components, and then have an explicit lighting model on it. In this case, it was just a Phong model, but if we train the GAN and introduce this physical bottleneck in the form of an explicit lighting model, then we can edit these parts, right? Just like we could edit the camera for EG3D, we can now edit the camera and also the lighting, because that's the explicitly controlled part. So during runtime, once the model is trained, we can use any environment map and relight these scenes in a reasonably convincing way. So here's an example where we have the same identity, we have this latent code interpolation, and we're showing the same identity in different lighting conditions. And you know, it is pretty convincing, I think, and useful for many applications. So we've seen good first steps towards enabling relighting too with diffusion models. For example, earlier, I think Junian was talking about it. So this is great that we're seeing this now also for diffusion models, but 3D diffusion models with relighting for photorealistic heads is in real time is not quite there yet. So GANs are still interesting in some cases. We've been thinking about generating full human bodies too. Here, the challenge is that, you know, if you look at natural pictures of humans in the wild, oh, hold on. They are pretty ill-behaved. They ride tricycles and bicycles, and they wear purses and have all kinds of other accessories. So they're not really well aligned. The body poses are very different in these images. So if you look at faces, they're pretty much the same. Most people have 2 eyes, a nose, a mouth, and 2 ears, and some hair. So it's fairly easy to align them well, but for full bodies, that's actually much harder. So one way of doing that is training a 3D GAN on these types of data, was something that we explored in a project called Gaussian shell maps, which will also be presented later this week. And the idea here is that we can use a GAN framework. We take a 2D generator. It generates a whole bunch of textures. These textures encode the attributes of 3D Gaussians. They texture an inflated and deflated variance of a simple template mesh, which we can explicitly control the body pose for, and then we can just render it and use a GAN discriminator to train it. So this allows us to take large data sets of single view images, train a 3D GAN that is now articulable. So we can do the interpolation of these Gaussians, we can make the character walk or jump or swing or do really any other thing. Like we can explicitly control the body pose. All right, so here's just a couple of examples of different poses. So it's getting better and better, even with the GANs. This brings me almost to the end of the talk. I want to show one more outlook of a really cool project that is going to come up at SIGGRAPH this year. It's not published yet, but it's going to come out any day now. This was a collaboration with Noah Snavely's team at Google Research. And the idea was to train sort of like a 3D video model, like towards 4D generation on street view data. So my student Boyang was working on this with partly at an internship with Noah. And the idea is that we have a map. We know the height. So we have proxy geometry, boxes, basically, of all the different buildings. We can now train an animate diff-like video generation model, just a few frames, but we came up with some tricks to make it auto-regressive. So we can generate arbitrary long sequences. And the nice thing is that we can also control the camera using a camera control mechanism. We can do text prompting, all kinds of things. We can run NeRF on top of it, and it's really multi-view consistent. It has a tiny little amount of flickering in the video generation model, but that totally goes away once you look at the 3D scene. And then what you can do with that is you can edit the weather, the time of day, the geometry. We trained it on a couple of different cities, and you can make New York look like London or Barcelona, and so on and so forth. So it's a little bit difficult to appreciate that for a small video. So here's the result. On the left, you see the map, cars driving around. We render the proxy geometry and some other additional information into a G buffer, use that to condition the video generation model in the middle, where you see the output. There's a tiny amount of flickering still, but it's good enough for us to nerf it. And that gives us a really nice 3D reconstruction. So these are large scale 3D generated scenes, basically. All right. Shamelessly, I'd like to advertise a couple of things. One is our state-of-the-art report on diffusion models for visual computing. We wrote this with a whole bunch of different co-authors, which is a really good survey paper that just came out a few months ago. It's on arXiv. It's been on arXiv for a while. And then I lead the computational imaging lab. So I sort of started this talk talking about wearables a little bit, but we are working a lot on neural scene representations, rendering and generation, but we are also working on AR, VR, wearable computing, actually a whole bunch of projects on generative AI for proteins and some computational optics and imaging. I'm also advising a startup called Apparat Labs, and we just released our very, very first model very recently, just a couple of days ago. Just want to play that teaser real quick. Single image to 3D or 4D and be fully controlled. Voice driven.
八百标兵奔北坡，炮兵并排被颠跑，炮兵怕把标兵碰，标兵怕碰炮。
How can I test this out?
Interact with our AI avatars directly on Twitch.
Okay, so the sound is not synchronized actually with this video right now. But you can test this live on Twitch. We have these Twitch streams. You can actually chat with the AI, and it's a visual embodiment of an AI, basically. If you're interested in this technology, let us know, again, real time. Or if you are looking for a job, we're hiring. We'd love to talk to you. And that brings me to the end of my talk. I'd like to thank all the people who did all the work, including Eric, Connor, Boyang, Shengshu, Ramin, Po, Yinghao, Zifan, the camera control team, Gaze GPT team, and the Apparats team. So thanks for your attention and enjoy the rest of the week.
Right, thank you for the talk. If anyone has questions, we have time for a few. You can use the microphone here in the middle. I have one question for you while people are thinking of theirs. You talked about this camera controllability. I was wondering how you collected data for that. Like, did you use automatic camera annotations for the pose, or can you use noisy estimations from video and that kind of thing to get extra controllability, or is it too noisy to use those?
Yeah, I think we use these noisy sort of conditioning information from existing videos, which are okay, but not great. And it's part of the reason why it's not perfectly controllable, but also the mechanism itself doesn't really guarantee any accuracy, right? It's just like more like a guidance signal. Moreover, if you use these plugger embeddings, it's really object motion and is also not really part of that. So there's actually a couple of problems with this camera control mechanism, and there's a lot of room for improvement there, both on the training data, on the mechanism itself, and on other aspects of it. All right, thank you.
All right, if there's no more questions, we'll move on. Thank you, Gordon.
All right. Next up, we have Jun Gao here for a talk. So for people working on 3D representations or isosurface extraction, you've definitely heard of Jun. Jun is a research scientist at NVIDIA in Toronto, and he's also wrapping up his PhD at the University of Toronto. He will be joining University of Michigan as an assistant professor in 2025. So for all you new PhD students looking for an advisor, Jin's looking for students. And with that, I'll hand it over to Jin. Very excited for your talk.
Thank you. Oh, sure. 1 second. So. Okay, so hi everyone. So it's really great. It's really my honor to be here, and thanks everyone for joining. So today I'm going to talk about the 3D representations for 3D content creation. In the past few years, we have seen amazing progress on using machine learning to create digital content, such as language, image, or video. However, the world that we human lives in is fundamentally a 3D world. We study and learn in a 3D environment since childhood. We perceive these very beautiful 3D animals and forests. We communicate with each other in a 3D environment, such as in this room. We also perform some actions like driving a car in a 3D environment as well. So therefore, to broaden the impact of generative AI to our life, I envision in the future, the generative AI system will help us to create realistic 3D virtual worlds and enable the immersive interactions between the human and the simulated virtual environment. For example, in this movie, the main character could seamlessly interact with this virtual city. Such 3D generative AI systems will revolutionize many applications beyond entertainment, such as the VR, AR, robotics, self-driving, education, or digital factory. So this is going to be a very exciting future. That being said, the future is not here yet. Generating 3D content with AI faces fundamental challenges that are very different from the generating images or language. First, as we have been talking about a lot in this workshop, the size of the data set that we have in 3D is much smaller compared with image data set. Even until very recently, the size of the largest 3D data set that we have is still around 2 orders of magnitude smaller compared with image data set. At the same time, while we have much less data, the complexity that we need to deal with in 3D is much higher than the 2D image. And this additional complexity is not just we have an additional dimension in 3D, it is also the complexity in terms of the 3D geometry, materials, and the final lighting effects. We need to create all of this information when generating the 3D content for realism and the immersive experience. Before we go to the technical part, let's take a step back and zoom out a little bit. Actually, the problem of creating 3D content itself is not a new problem. It has a very long history from the computer graphics back to 1960s. The computer graphics community has studied many techniques, from modeling the 3D geometry to animating the created 3D content, from modeling the appearance to finally rendering and showing a photorealistic image to the user. This is very cool because we do have some tools that can create realistic 3D virtual worlds. And these tools provide a lot of domain knowledge on how we should model the 3D content, such as the 3D geometry, appearance, etc. However, many of these tools are often designed for experts, and therefore it is very hard to scale up and allow much more people to create 3D content. So therefore, to push toward the future and tackle the challenges that we have, my area of research has been developing the generative AI system for 3D content by incorporating the domain knowledge from the computer graphics. And this is a really multidisciplinary area in between vision, graphics, and machine learning. More specifically, we have been working on 2 axes along this line over the past few years. First, to tackle the challenge of the 3D complexity, we study how we could incorporate the 3D modeling techniques from the computer graphics into the 3D generative AI system, such that we are able to regularize the generation behavior and reduce the 3D complexity. Through this approach, we are able to improve the efficiency, fidelity, and the usability when creating the 3D content. Second, to alleviate the issue of dataset scarcity, we study how we could leverage the foundation models and extract the 3D structures from these foundation models by incorporating the inverse graphics. In this approach, we are able to improve the diversity and the realism when creating the 3D content. By combining the approach we have for 3D modeling and also the algorithms to leverage the foundation models, we are able to turbocharge the applications in the whole spectrum of 3D generative AI, including 3D generation from single view image, 3D reconstruction from multi-view image, building a 3D generative model, or finally text to 3D generation. And in this talk, I will mainly highlight our 3D modeling techniques because the algorithm we do for this leveraging foundation models are mainly building on top of our 3D modeling approach. Okay, so with this motivation, let's look at the 3D modeling approach that we have in 3D computer vision. So 3D computer vision community has witnessed a really great success with neural field-based approach, such as using a neural network to model assigned distance fields. Neural field-based approach has inspired a lot of work in 3D computer vision, such as neural radiance field, NeRF, and many others. This approach is very suitable for machine learning because it has a continuous definition in the 3D space. And such a continuous definition makes the optimization of a 3D generation very easy. It can also represent very complex 3D geometry, such as a complex shape that we can see from the NeRF. However, such a continuous modeling approach is also very redundant. For example, suppose we want to model this bunny, then we need to not only model what's inside of this object, but also what's outside all of this empty region of this bunny. And such redundancy further makes the rendering of a neural field very inefficient. More importantly, in many applications, such as if I want to render this object with lighting, or if I want to touch this object with a hand, what matters most is the location of the actual 3D surface. However, since that 3D surface is only implicitly encoded in the parameters of a neural network, such explicit reasoning on the 3D geometry is much harder. From the other side of the computer graphics, actually, we do have one representation that specifically focuses on the 3D surface. And this representation is 3D mesh. Mesh is super efficient, it's super compact in modeling the 3D geometry because it is specifically localized where the surface is. And because of such compactness, rendering 3D mesh is very fast. However, the key challenge of incorporating the mesh into the generative AI framework is that generating the mesh is not trivial, especially if we want to change the topology of the mesh, because this will involve learning the discrete connectivities between the mesh vertices. So to bring the mesh into the generative AI framework and incorporate the key rationale that we should focus on the actual 3D surface, we developed a differentiable isosurfacing approach for 3D modeling. And this is a joint work with my fantastic collaborator, Frank, on the right side. So specifically, in the forward pass during training, we hope to differentially extract a neuron, we hope to differentially convert a neuron field into a 3D mesh. And this 3D mesh is the isosurface of this neuron field. With this operation, we are then able to define a lot of objectives that are directly evaluated on the 3D surface. Such objectives could range from a loss function by comparing with visual observations to more complex geometric energy functions that are defined on the 3D surface. It could even be a loss function from a physical simulator. In the backward pass, since the operation is differentiable, we could then backpropagate the gradient from these objectives into the neuron field to generate the 3D content that we really want by minimizing these different objectives. In this approach, we could regularize the neural network to specifically on the 3D surface, and further unlocks new capabilities by allowing us to define new objectives that could be well defined on the 3D surface. Such operation can also gain the efficiency by leveraging the hardware accelerated rendering and solvers that are developed for the 3D mesh. So with the time constraint, I will not go to technical part of how we achieve this differential isosurfacing. So if you are interested, please check our paper for more details. And I will show some applications that our model is able to achieve with this differential isosurfacing. So let's first look at a vision-based objectives, which means in this case, given a set of images with the camera parameters of these images, we hope to extract the 3D information from this image, such as the 3D geometry or the appearance, which is always called multi-view reconstruction. And we can achieve this application by simply using our differentiable isosurfacing to model the underlying 3D geometry, and differentially render this 3D geometry into the 3D mesh. The loss function is then computed by comparing the rendered image and the visual observation. Since our operation is differentiable, we can then backpropagate the gradient from this loss function into the 3D geometry through differentiable rendering and our differentiable isosurfacing. As we can see in this animation, after training, we are able to reconstruct 3D shapes that aligns well with the visual observation. Compared with other baselines, which are using the neuron field to model the underlying 3D geometry, our method is able to achieve better alignment with the 3D surface because differentiable isosurfacing allows us to specifically focus and optimize for the 3D surface that aligns with the visual observation. We could even optimize a soft body simulator. We can even optimize with a soft body simulator to reconstruct a deformable object by minimizing a physical objective. In this case, we optimize both the 3D geometry and the physical parameters that control the simulation of this object. And this is achieved by combining our differentiable isosurfacing to model the underlying 3D geometry with a differentiable soft body simulator to simulate the 3D geometry. As we can see in this animation, we can also reconstruct a deformable object that aligns well with video observation. We could further use this operation to train a 3D generative model for 3D mesh. Here I'm showing some of the generated 3D assets from our model. Our model is able to generate diverse and high quality 3D outputs, especially on the 3D geometry. And this work is actually building on top of the triplane representation introduced by Gordon before. We could also turbocharge the text to 3D generation with our representation. So to give a very brief recap of a typical pipeline for text to 3D generation with score distillation sampling loss functions, we can first have a neural network to model the underlying 3D content on the left side and render this 3D content into the 2D image. We can then feed these 2D images into the diffusion model and get a gradient direction that can help us update this 2D image. And this the meaning of this gradient direction is basically like, if I walk through my image along this direction, the image will be more realistic. And then we can backpropagate the gradient from this diffusion model into our neuron fields. The key challenge here is the computational cost, because in this case, the whole computational cost for one pass will be the number of images we rendered for a neuron field times number of pixels to render one image, and further times number of points that we will sample per ray to render one pixel. And typically, to render a nerve, we probably need to sample hundreds of points along the ray, which means the last item in this equation will be hundreds. Furthermore, because of the such high computational cost, we could only render a very low resolution image, and such low resolution rendering will miss a lot of details on geometry and appearance. For example, in this video, I'm showing some of the results from the prior work, which does not have enough geometric details. On the other side, one thing we do know is that rendering a 3D mesh can be super efficient. For example, suppose we have a 3D mesh. To render this mesh into an image, we can shoot a ray from the camera, and this ray will intersect with one point on this mesh. Collecting the colors of this point will immediately give us the color of the corresponding pixel. And therefore, suppose we have the mesh in the loop, the whole computational cost will be the number of images times number of pixels for one image and times 1. And this equation is almost 2 orders of magnitude smaller compared with the previous equation. Furthermore, once we have the mesh, we could even render the image at a much higher resolution. And such high resolution rendering will allow us to capture a lot of details on geometry and appearance. Such efficiency and the quality enhancement can be easily achieved by incorporating our differentiable isosurfacing in this generation process. In this case, the gradient from this diffusion model will be backpropagated into the 3D shape through differentiable rendering and our differentiable isosurfacing. Here I'm showing some of the more examples of the generated result from our methods. Our model is able to produce fine-grained details, and there are 2 reasons why we can produce such details. The first is differentiable isosurfacing. As I was mentioning before, it allows us to focus on the actual 3D surface and optimize for that 3D surface. And second, we can also render the image at a very high resolution, and such high resolution rendering provide sufficient supervision signals of how such high frequency details will behave. Beyond the applications that we have demonstrated, we are also very excited to see the broader adaptations of our method in other applications, such as articulated object generation, single image to 3D generation, human generation, etc. We have also open sourced our code in NVIDIA coding library. And on the right side, there's also a very wonderful CUDA implementations from UCSD. Okay, so until now we have talked about the advantages of having a mesh and incorporating the mesh into this generative AI framework through differentiable isosurfacing. However, I'm also not here to say that we should definitely focus on one particular representation, such as a mesh for 3D content creation, because mesh itself also has limitations. For example, in the first image, I took this picture yesterday under the Space Needle. It is very hard to use the mesh to represent the cloud of this of the sky. And in the second image on the right side, it's also very hard to use a mesh to model the fur of my cat. So to analyze this, let's consider this human model as an example. Suppose we want to render this human model, and then there are two different types of regions that deserves our attention. First, the hair region of this human. For example, the hair region here. The hair region here contains both the fuzzy and semi-transparent patterns. And then these complex regions actually will benefit a lot with neuron field-based approach. For example, we can use neuron rendering to render the hair region, and we can get really great rendering of that. But if we use if we use a surface-based rendering with a mesh, then it will likely produce a lot of artifacts because it's super hard. Like this regions is not possible. It's super hard to represent it with a 3D mesh. On the other side, if we focus on the regions such as the surface or such as the face of this human, this location will be actually benefits a lot with surface-based approach. For example, in this case, we probably only need to sample one point to render this to render the face of this human head. But if we want to use volume rendering to render this face, then we will sacrifice a lot of unnecessary points there. And these two different types of regions on one particular object reminds us we should probably need different representations for different regions of a particular scene, or maybe different representations for different scenes. So in our new representation, adaptive shell here, we aim to model such spatial varying complexities across different scenes and distribute the computational cost on surfaces depends on the complexities of the local surface regions. And this is also a joint work with my collaborators, Zian, Frank, and Merlin. So specifically, we hope to automatically derive the regions such as the hard surface, like the face of this human head, and also the fuzzy regions such as the hair of this human head. With this different region notations, then we hope to define two shells to spatially regularize the geometry. Specifically, in this figure, blue means the outer shell, and yellow means the inner shell. And we assume the whole 3D content will be spatially bounded within these two shells. And then during the inference, we will only render the content within these two shells. The key benefit of such bounding shells is that we can spatially change the width of these bands according to the complexities of the surface. For example, for the hard surface on the face of this human head, we can have very narrow band, and this very narrow band will be corresponds to a surface-based rendering such as a mesh. And for the fuzzy region of this head, we can have much wider band, and this wider band will be more closer to the surface-based volume rendering. In this way, we are able to achieve a very smooth transition between volume rendering, between volume-based representation and surface-based representation. So during the inference, to render the neuron shell is actually very efficient. For example, suppose we have two shells. One is the outer shell, and the other is the inner shell, and we shoot one ray. If this ray doesn't hit any shell, then this means like it will hit the background. We does not need to sample any points here. And then if this ray has if the two intersecting point of these two shells is very narrow, then that means this is a very hard regions. Then we probably only need to sample one point along this ray, and this sampling one point will equivalent to a surface rendering. If the intersection interval is very wide, then we'll try to mimic the volume rendering by sample multiple points along this ray. And the key benefits of our representation is everything can be achieved within one framework. So everything is done in one pass. In this video, I'm showing some of the runtime comparison with Instant NGP. So in the scene with single object, our model is able to achieve 5 to 6 times speed up compared to Instant NGP. We can also extend our works into unbounded 360 scenes, and our methods maintains real-time performance. as a like competitive qualities with other interactive methods. We can further export our representations with the animation. So in this case, even with the presence of the deformation, the rendering process still benefits a lot with our adaptive shell representation to efficiently sample the underlying volumes. Okay, so with all of this, like I want to kind of slightly looking ahead of the future. So this is like, this is still the beginning of my chapter. There's a long way to go to achieve the final goal of creating realistic 3D virtual world for immersive interactions with a human. To achieve these goals, there are two directions I think we need to push. The first is how we are able to generate artist-level 3D content for quality and the realism. And second is how we are able to generate interactive, functional, and dynamic 4D content. For example, for the first part, when we look at the object in our real life, we could really zoom in and discover super fine-grained details, such as a wrinkle on the face of this man. To generate such levels of details, we need to study both the 3D modeling techniques that are able to model such fine-grained details and also the learning algorithms that can provide the supervision for such fine-grained details. Along this direction, actually, although we talk a lot about that we do not have enough 3D data, but actually there exists a lot of 3D information within the current existing 3D data sets, such as the mesh tessellation or the UV mapping. Many current 3D generative AI systems neglect this information. However, such information is particularly important when exporting the generative 3D asset into the graphic engines for animation or simulation. So, like, I hope we can also explore more on how we could explore these different properties within the 3D data sets. So the second one is that how we are able to produce 4D generative AI for interaction and dynamic 4D content. The 3D virtual world that we are building should be able to support interactions with human in a way similar to how we would interact with this real world. For example, in this video, the human could interact with this puppy dog, and the puppy dog will react to the interactions of this human. And this direction will also require more explorations on how we could model the physics and dynamic 4D content. So with all of this, I'd like to thank to all of my collaborators and thanks you all for listening to my presentation. I'm happy to take any questions. Thank you.
Thanks a lot for that wonderful talk. If people have questions, please come up to the microphone right in the middle. Please come ahead. You could use the microphone that's right there. We have time for a few questions.
Thank you for your presentation. It was very interesting. I liked a lot also your especially your work on the adaptive shell, and I was wondering how would you you didn't mention point clouds, right? Would you integrate point clouds as a mesh representation, and when do you think it's a 3D representation, and when do you think it could be useful to do so?
Yeah, I think point cloud is also actually very wonderful representation actually, and especially is the benefit of the point cloud such as 3D Gaussian is very fast, and it can also represent the dynamics. And actually there is also one follow-ups of combining the adaptive shell with the 3D Gaussian, such as I didn't show in the talk. It's basically this Gaussian for listing, which is basically we can also regularize the point cloud using our adaptive shell, which means like the Gaussian point cloud is restricted within the shell. So I see there's also mutual benefit between this mesh and the point clouds. Thank you.
Thank you so much for the talk. I just have a small question. Sorry, I didn't follow. What's the exact name of the paper for differentiable isosurface extraction?
Oh, yeah, sorry, I didn't mention that. I did very quick. So let me go to that part. So actually we have a line of work along this direction. So the first paper I would say I would recommend to check is like deep marching TET. We call it DMTET. And the second paper is in SIGGRAPH last year. It's called FlexiCube. And you can also go to my web page. I have that in my web page. Thank you.
Thank you.
All right, let's thank Jun again for this wonderful talk, and we'll move on to the next one.
All right, so it's my great pleasure to introduce our next speaker and a great friend of mine, Alex Kolinsky. So Alex got his PhD from UW here in Seattle, where he worked with Steve Zeitz, Brian Careless, and Rick Zelinsky. Since then, he has been jointly at Google Research and now Google DeepMind as a research scientist and a postdoc at UC Berkeley. Together, we're working with Anxo Kanazawa and Aliosa Efros. And the most recent news, of course, as of last week, is that Alex will be joining Columbia University as an assistant professor in recent future, which is exciting. And yes, Alex's work has been recognized with the Best Student Paper Award last year in ICCV. He has one more paper that is best paper candidate this year, and I think that with this space, regardless, I can see him. It won't be long until he will be on that stage again. And Alex has done impressive work in the space of 3D generative AI, and I think that today he will cover some of his recent Cat 3D work, which turned a few heads last month when it came out. So yeah. Alex, we're very excited. You can take it away whenever you're ready. Yes, you can.
Wow, what an intro. Can everyone hear me? Yeah? All right, cool. All right, so today I'm going to be presenting our paper, a very recent paper called Cat 3D, Create Anything in 3D with Multi-View Diffusion Models. And this was joint, very close work with Ruiqi Gao and Ben Poole and a handful of other very wonderful collaborators at Google Research and Google DeepMind. So first, I thought it might be good to start by offering a little bit of motivation for why we even want 3D generation. And, you know, this might be obvious to a lot of you because, you know, well, this is a workshop for 3D generation, but I do often hear people saying things like, what's the point? You know, video models have already been shown to be useful for a bunch of things that we use 3D for nowadays, like movie quality CGI. So maybe we don't even need 3D models anymore. Maybe we can just do everything with a video model. Well, you know, I get this argument, I really do, but you really need to think about, you know, some of these hot new VR, AR, and mixed reality devices. You know, with these and really with any other kind of interactive 3D medium, the most natural way of consuming content simply isn't on a 2D plane. It's an actual 3D entity that you can walk around and explore and see from different viewpoints. And for what it's worth, I think that this is also true for more traditional forms of consuming content, like phones and laptops. You know, if you generate a video, if you get, you know, if you run it through a generative model, you only really just get that one video as output. But people often want to like explore, control, or interact with the worlds that are being generated by these models. And with the video model, how do you do that? Well, you can certainly train these models to take in new signals so that every time, say, you make a gesture, you get a new different sample that respects the user inputs or shows the scene from a new viewpoint. And we've definitely seen how to train image models to respect camera viewpoints. So we know that this is doable. But practically speaking, you're really not going to be wanting to run a video model on these edge devices anytime soon. And even if you can, it's probably just not a great idea. You know, they're not going to be fast enough to generate new high quality videos 60 times a second on a phone, or they're just going to be too power hungry to actually be useful. So really, a better solution here is a 3D model. You know, 3D content checks all these boxes. You send over a single 3D model and a user can interactively move the camera around and explore the scene by just rendering that model from new viewpoints, which is something that we've known how to do efficiently for some decades now. And how do we create 3D content? Well, traditionally, this has been done through, you know, processes with trained 3D artists. And this process can take sometimes hours for a single asset, which means that creating a full 3D room, a scene, can take up to days of work, depending on how detailed it needs to be. But fortunately, you know, over the past few years, we've also gotten new tools for replicating real 3D content, things like, you know, NeRFs. And NeRFs are great because they let you capture and reconstruct real 3D scenes in great detail, which lets you render arbitrary new viewpoints, fly around the scene interactively, and basically all the things you'd want to do with a 3D model. But one thing that you don't often hear people talking about is that capturing a NeRF requires a really careful capture process. You need to take hundreds to thousands of images of the scene in a pretty deliberate way that covers all the structure of the scene from multiple viewpoints. So here you can see this little Lego bulldozer has been reconstructed pretty well, but it's taken over 80 images captured in a ring around the object. And in the absence of this number of images, NeRF really just doesn't work all that well. So let's say instead of 80 images, we only have 3. Well, you'll probably end up with degenerate reconstructions of the scene like this one that don't look good at novel viewpoints and don't have reasonable geometry. And this is really the result of an under-constrained system. There's some degenerate solutions, like simply pasting the captured images on random geometry, that satisfy all the constraints in optimization. And so a few months ago, we put out this paper called Reconfusion that we'll be presenting on Friday morning in the poster session that was aimed at making reconstruction more reliable in the cases where you have very few captured views. And so if we look back at that failed few view reconstruction we just saw, once we add in some magic from Reconfusion, we can get a pretty reasonable reconstruction of the scene, which again is from only 3 input images. So how does it work? Well, the core idea is to simply try to simulate the existence of additional views in the NeRF optimization process. So typical NeRF optimization works by rendering out views and then supervising those renders against pixels from real captured images. But if we don't have enough views, we also don't have enough constraints to guide our optimization process towards a reasonable solution. So in Reconfusion, in addition to supervising the captured views, we can additionally sample new unseen views that weren't captured of the scene. And at those viewpoints, we can query a generative model for an estimate of what the scene might have looked like from that viewpoint, conditioned on all the other information that we've been given. And what I'm describing here is a generative model that's not the standard text-to-image models that we've all come to know and love, but rather a new kind of generative model that takes in multi-view observations of a 3D scene, as well as a target pose, and produces samples of the 3D scene from that new viewpoint. Effectively, this is a novel view synthesis diffusion model. And here you can see an example. It takes a few images as input, as well as their poses, and takes in a novel target camera pose, and it produces a novel view synthesized on the right. So the big challenge of this particular paper was figuring out how to build this model. From choosing the architecture and figuring out how exactly to condition the model on the input information of image and pose pairs, to also the data set, where we needed posed multi-view images that covered a sufficiently wide range of scene types, as well as an even coverage of potential novel viewpoints. So we ultimately here settled on a mixture of real and synthetic data from a handful of different sources like Real Estate 10K, CO3D, and renders from Objaverse. And by the end, we managed to get a pretty decent model, that could create plausible novel views of the scene given as few as 3 input images. And this was great, but there was still one big problem to be solved. If you sampled the model, a handful of different times from different viewpoints, or even from the same viewpoint with different seeds, you'd get super inconsistent estimates because the model was really only trained to produce a single image at a time. So we had to figure out the right strategy for actually integrating these inconsistent signals into the NeRF optimization process. And our solution to this was something not too different from DreamFusion, in which, in each iteration, you render an image from the 3D model, and then you pass a partially noised version of that render into the diffusion model and ask it to produce a clean image. And then you simply guide the 3D model towards that clean image that the diffusion model produced. And effectively, this iterative partial noising and denoising process leverages the guaranteed consistency of the 3D representation to encourage the sampled images to be more and more consistent with each other. And, our version of this is slightly different in ways that I won't really get into now, but basically, this ends up being pretty effective for observed parts of the scene. So here you can see some pretty complex scenes, reconstructed at the top with very few views. So this is anything from like 3 to 9 images. But while this is very impressive, you've probably also noticed a few key issues so far. So first of all, if you know anything about these large diffusion models, you'll know that this iterative optimization process I just described is really slow, because it requires calling a diffusion model multiple times for each NeRF optimization step, which turns what would otherwise be a minute-long process into something that's like 20 or 30 minutes. And this is fine, as long as we're getting good results that would otherwise be impossible to get. But even the quality isn't perfect sometimes, because while Reconfusion worked very well for observed images or regions where the input images offer a strong enough signal for what should be there, for unobserved regions, like occluded or entirely uncaptured parts of the scene, the model would basically produce entirely inconsistent content, which is very hard to consolidate even through our iterative optimization process. And you get to see this most prominently in our single image results. So these results here are showing what happens when you feed in only a single input image to the system. Most of the scene is entirely unobserved, so the samples are very disparate and optimization becomes really hard. Most of the unobserved parts of the scene end up being just reconstructed as sort of blurry or gray blobs. So here's where Cap3D comes in. So we first started this project as a follow-up, trying to solve some of the problems that we had with Reconfusion. And the first problem that we realized that we needed to solve was to make sampled images from the diffusion model consistent with each other. Since, as we just saw, if we have samples that are very inconsistent, we end up with reconstructions that are blurry or otherwise don't look plausible from novel viewpoints. So the core reason why samples were inconsistent in Reconfusion is because it was built as an image model. In other words, it was really only trained to produce one image at a time. So there's really no surprise that multiple images weren't consistent. But we've also seen that video models are possible. And we've seen that these can generate consistent content across many, many frames. So we can borrow some of the design decisions to build the corresponding multi-image or video novel view synthesis model. And this multi-view latent model is the core innovation in Cap3D that makes most of the difference. This is building on a lot of the learnings over the past year in video model architectures where information is shared between the different frames that are being generated. And this model here is sort of like a special case of a video model. And I'll walk you through a bit of how it works. So it takes in as input 2 different types of inputs. So the first is captured or otherwise observed views, which contain an input image and the corresponding camera parameters of pose and intrinsics. And we encode all of this before passing it to the diffusion model. So the image gets encoded by a pre-trained VAE into a set of latents, since our model is built on a base latent diffusion model, and the pose and the camera information is encoded into per pixel ray coordinate maps, which is basically just contains each pixel's ray information. So simply, it's just the ray origin and direction per pixel. And for novel views, we don't have an input image. So we simply feed in the same set of information, but set the input image, the input latent image, to be pure noise. And to help distinguish between these 2 different types of inputs to the model, we also feed in a mask that tells the model which views are observed and which views are not observed. And so, crucially, the input information to the model can be any mixture of these 2 different types of inputs. They're treated exactly the same by the model, just as sort of a large set of views that may be, variably known or unknown. And although this probably already seems a lot like a video model, a key distinction here is that these inputs don't have any temporal information, and they interact only through attention operations without any kind of temporal position embedding. So they are like almost truly an unordered set of posed frames. And so the model takes in all this information and simply produces a set of generated novel views for the specified target camera poses. And of course, we train this with sets of posed multi-view images, so it's supervised to produce multiple consistent frames at once. And this uses exactly the same training data set that I just showed before for Reconfusion. So it's, Objaverse, MV ImageNet, CO3D, and Real Estate 10K. And so within the model, there are attention interactions between these different frames that are being generated. So you can actually get, really consistent samples out. And here are a few of those. So you can see, simply modeling sets of frames instead of a single frame at once, the samples already look a lot better, almost as consistent as some of the reconstruction results that we were looking at earlier. And so all of this brings us back to the question of speed. Seeing how consistent our samples were, this made us realize that maybe we didn't need to do all of that fancy iterative optimization stuff that we were doing in Reconfusion. And instead, since our sampled novel views are consistent enough, we can just decouple these two parts of the process. First, we can pass our inputs into the model and generate a whole bunch of novel views, synthesize novel views. And then we can simply reconstruct those views using a standard, relatively standard NeRF pipeline. And while these samples are not entirely 3D consistent, they're consistent enough that some of the standard robust NeRF reconstruction tricks like perceptual losses and so on are enough to consolidate them into a consistent 3D model. And this decoupling that I'm showing here also basically solves the speed problem from before, because we don't need to repeatedly sample from the model. And we instead only do it once at the very beginning of the process. So we just sample a set of frames and we reconstruct them. And in the case of Reconfusion, where before it would take an hour to reconstruct a decent scene from 3 images, Cat3D now only takes a couple minutes and produces reconstructions that are notably sharper and more coherent. So this lets us produce full 3D scenes in as little as a minute from any number of inputs, like 3 images shown here, or now, since we made such an improvement to the consistency problem, even just a single image. And that single image can be a real captured photo, like this photo of a dog, or it can be a generated image that was created with a text-to-image model. So you can really get creative and create a 3D scene out of more or less anything that you want. So I'll scrub through a couple more of these examples just to give you an idea of what the results look like. But definitely do check out the website where we have a full gallery of results, including some synthetic scenes that we came up with prompts ourselves, as well as some real captured photos of our own. And here's what that gallery looks like. So at the top, you've got a search bar, and you can search for whatever thing you're interested in seeing. And running on such a large collection. Oh, okay. Sorry, Zoom problems. Is that good? Yeah, all right. Okay, so, running on a large collection of examples like we have here in the gallery was really only possible because, the method is as fast as it is. It takes only about a minute of processing time total per sequence, per model that we want to generate. And, on the website, we also have an interactive viewer where I just recorded this, minutes ago, sitting in the audience. So this is as slow as the loading time gets. And, we've reconstructed some of the scenes with Gaussian splats, and we're rendering them in real time on the browser. So you can play around with all of these models, interactively on your phone or on your laptop. So definitely give it a try. And so to close out, I've got a couple slides on what our learnings were throughout this process, and then also what some of the failure modes are. So let me take you through some of those. So first of all, what are some of the things that we learned? Well, we learned that, robust and perceptual losses are super effective at reconstructing sets of slightly inconsistent images, but they don't really do much if the images are too inconsistent, meaning if they describe entirely different scenes. We also learned that, camera trajectories are really important. Since we're sampling the scene at novel, uncaptured viewpoints, these need to be valid viewpoints. And the same virtual camera trajectory might not necessarily apply to all different kinds of scenes. Some scenes might need more orbital, object-centric views. Some might need more forward-facing camera dollies. We also learned that the way that you pass in conditioning information to the diffusion model, it makes a very big difference. So the choice of passing in ray information, as we did, worked way better than a lot of the alternatives that we tried. And lastly, we found that certain advanced sampling techniques can be used to encourage more views to be consistent, like, you know, autoregressive sampling and anchoring. And I'll leave this for you guys to read about a little bit more in the paper. Okay, so finally, there are a lot of things left to be done here. Like this problem is far from solved. And this points us towards, you know, directions that might be interesting for future work. So, you know, first of all, you know, geometry sometimes just isn't great. And this is largely because of ambiguity in photometric only reconstruction. So maybe adding things like depth priors might be useful here. And also, as I mentioned before, you know, not every scene is compatible with the same camera trajectories. And our current MO here is to just try a couple different camera trajectories and pick the one that worked best. But the correct way is to actually somehow predict which set of poses would be reasonable to sample the scene at given a particular input image. Also, you know, our training data here is super biased. You know, we've used a small collection of data sets that definitely don't cover the full spectrum of possible scenes, camera poses, or even camera intrinsics. So either coming up with better data sets or better ways of generalizing would be very helpful to the eventual reconstruction quality. And finally, and this is the obvious one, which is that, you know, our method requires, you know, static observations of a scene. So it doesn't work well if you pass in multiple observations of a scene that were captured reason why you see more generated images here is because it's much easier for us to run text to image on 1,000 images. It's much harder for us to collect, thousands of images that we might want to release on our website.
Thank you. Thank you for the presentation. My question is for the few view settings. Does your method depends on the text prompt? And if true, how carefully it should be picked?
So both these models, the Reconfusion model I showed at the beginning, and then Cat3D, both of them are fine-tuned from a base text-to-image model that does take text as input. For Reconfusion, we removed that text dependency by replacing the clip embedding as input with a clip image embedding. So it's fine-tuned to sort of not need text as input. For Cat3D, we removed that embedding altogether in the fine-tuning process. Although I do expect that adding it back in or keeping it altogether might improve results. Even if you were to say just caption the input images, that would probably help preserve some of the prior from the base model that you started training with.
Got it. Thank you.
We'll need to take the rest of the questions offline because we are 10 minutes behind. I'm sorry.
Okay. Sorry.
And we can continue with the next speaker. So yes, the next speaker is the legendary Alex Yu. So Alex is with Luma AI, where he and his team are responsible for some of the amazing things that you see out of the company. Alex did his undergrad at UC Berkeley, where he worked with a group of Angus Kanazawa. And during that time, he was the responsible and the strongest force behind one of the strongest and most memorable trinities of papers in this space, PixelNerf, Plenoctris, and the Plenoxels. And after his undergrad, he joined Luma AI. And I hope that we can lift a bit the curtain when it comes to all the amazing things that they are doing with his team, including the latest Dream Machine release that took Twitter by storm last week. So as soon as we resolve the technical issues, Okay, so Alex, you can take it away.
Okay, thank you for the introduction. Yeah, and yes, my name is Alex Yu, and I'm co-founder and CTO of Luma AI. And today I will be talking about our recently released video model, which is Dream Machine, and also connected with 3D generation. Generation, including the Imagine and Genie. So, but there was always some gap between the two streams. Like then it feels like to get past the reliability problems of NeRFs, we need to add in the generative priors that we're able to learn from large data sets. Oh no. Okay. However, as it has been brought up multiple times at this workshop, 3D generative models are quite bottlenecked by the availability of data. The foundation of recent generative AI boom is these massive internet scale data sets of text, images, and videos. And despite considerable efforts to expand 3D data, we still only have like millions of them, of objects and captures, which is a lot more than a few years ago, but still tiny compared to the images and videos. And the videos are something that people in general take, and that they're like, they have an intrinsic level of quality since they usually reflect the real world. Meanwhile, 3D models are not as abundant or high quality and may come in like various formats. And what's more, like even if we do have a lot of these data, like what is really important for 3D are things like topology, UV materials, articulations, and so on. And it is very difficult to collect data with these additional properties. And more generally, I think there are also like limits to how much we can use computer graphics-based priors for solving 3D problems. With like static 3D objects and scenes, 3D methods like NeRF and Gaussian splats have been successfully applied in many problems, but they are already like quite slow and sometimes require a lot of heuristics. And in 4D, this becomes a bit more challenging. But maybe it's still like reasonable. However, if like what people are really interested in is still like all these additional properties of like light transport and also like simulating physics in various ways. But like to be able to code in all kinds of physics, we have to handle various graphics problems like articulated objects, cloth simulations, and so on. And by introducing many degrees of freedom, the problem becomes more and more ill-posed and more difficulties arise. So like in this direction, ultimately you will need to build a game engine and somehow differentiate all the features. So I think that is not very scalable if we want to be able to solve the problem of simulating physics and things like that. So recently, the direction that seems promising is using these, by using the 2D data sets for which have a lot of 3D information in them. And like as Alex Polinsky just presented the work Cat3D. And also like several works last year, like NVDream and Instant3D, doing these multi-view diffusion approaches. But over the last several months at Luma, we have been focusing on the first part of this problem, which is to build a video foundation model. And this video is a generation that I made of a drone shot of a Luma ice statue. And here are some more examples of amazing generations with 3D camera movements. This one is, the left one is a generation from a Japanese creator. And this one is something that one of the team members made for the release day. And here are some more examples of 3D trajectories around these like skull, and also a pig riding a motorcycle. And one of the things that ways to test 3D consistency is by running these outputs through a NeRF or Gaussian pipeline. And in this case, we uploaded it to the Luma interactive scenes and generated this Gaussian from the video to produce like a plausible 3D scene to some extent. So let me try that. So another interesting sort of experiment I tried was giving some popular NeRF data sets to the image to video pipeline. So this is actually a screenshot from the Zip NeRF paper from John Barron. And as you can see, it generates some drone trajectory through the house. And here are some more results from the MIPNEF 360 data set that's like you see all the time in the NeRF literature. Wait, what? And I also tried these like LFF scenes, which are taken from VLSB in Berkeley. But like going beyond just these 3D scenes, one problem that was always very challenging in NeRFs was actually handling specularity and reflection. Despite initially seeming to promise to solve these problems and also works like RefNeRF, like the specularities are just like very high frequency to model with just the view dependency or spherical harmonics. And as you can see, like, well, it sort of models the reflections. It has some artifacts. Maybe it's, well, like, I guess with the video model, it can somewhat solve these like light effects. But no. And here are some more examples of generations from the model. There's a lot of reflections and refractions in the car. And here's like some cinematic shots from a creator of a sci-fi setting. So you can, in this one, the teddy bear swimming in the ocean. You can see the reflection of the bear in the waves. And like this is a from a long-time Luma user. And you can see there's the complex refraction effects in the bulb around the plant. And this one is actually using our recent extend feature to make the video longer than by 3 times. And furthermore, like beyond just materials and light transport, the model can also have some idea of dynamic, like 4D. This is like also just a fluffy teddy bear swimming in the ocean. You can see like the model handles the movement, fur and water. Okay. And this one's actually a photo of one of my cats from a while ago. And there's like a giraffe roller skating in a park. It's just some additional examples. Beyond just animals and humans, we find that the model can also somewhat simulate physical interactions. Here's a beautiful example with debris flying around and the fire, smoke, and explosion at the end. And this one showcases some human and some cloth. And another one with clothing and shows some 3D camera movement. We find that also the model is like kind of able to reason across cuts sometimes. Like this scene is a little bit like horror, but just to illustrate the point, you can see that at the beginning there's like an eye, and then the girl looks horrified. And in this case, there's a monster, and then you can see the monster from the back. So another capability that the model has is generating very stylized videos. So beyond realistic effects, oftentimes creators are interested in making videos with various specific styles. And this is like a short film from the monster library called Monster Camp. That and throughout they're able to make an entire short film with this kind of style. And there are like other styles like this anime and this kind of oil painting, which is, you can see like the whole scene is quite consistent. Okay, I guess finally I will discuss some limitations, since this is like academic workshop. And the current model still has like a number of limitations. For example, it's not always consistent like with the shapes. And there's actually this one with kind of Janus effect, which is something from the 3D generation literature. But when the bear's head goes under the water, you can see there's another head. It's just. And then there's like also sometimes it does strange physics. Like in this case, I gave it the LK99 picture. And well, it adds a rock on top of it. And then the rock somehow becomes long and then becomes electric. So maybe I interpreted that there's a cut in the middle where suddenly the rock becomes a long one. And this is like I gave it an image from the Clever, which is like a BQA dataset that's also used in some 3D project. And while it has some like cool shadow effects, it's like doing something very strange, like the objects merged and kind of clip past each other. And something to be improved is the camera control. So like currently, like we didn't actually train with the kind of precise camera controls. You can somewhat prompt it with the text, but I think it will just give like some trajectory that looks reasonable, and like of course for the 3D and 4D generation, like it'll be very important to add precise camera control. But in any case, we still find the results quite interesting, encouraging, and for some future directions, and that not necessarily like for our products, but just I find it interesting. Or things like to make the camera controllable and maybe like train on egocentric data. You can have like a game engine, maybe kind of but generative. And also recently there has been work in using the video models for robotics, which is pretty related. And I think as a kind of like universal imagination or world model. I think these are very exciting directions that may have like a large impact on extending AI advances to the physical world. And I guess finally, special thanks to all of the Luma team. Basically, everyone contributed to some part of the project, either the model development, data infra, or like the product. So like we are also hiring if you're interested, please check out this link.
Great. Thank you very much, Alex. If you have questions, you can come at the mic here at the center.
Hi, Alex. First of all, congratulations on your successful release of Dream Machine. So in your talk, you first mentioned that they are serious data constraint for the 3D generation, and also I noticed that so the Luma Genie hasn't updated for a long time, quite a long time, and doesn't mean that you guys abandon the product line of Luma Genie, and how would you envision the future of 3D Gen AI? Thank you.
Right. So, like as I kind of explained in this talk, like our view is that we kind of need these to be able to leverage videos and images to like further advance 3D, because like just doing these using the existing or like asset data sets is difficult to make the model much better.
All right. So then do you have a plan for, I mean, future release of the next version of the Luma Genie? Like,
yeah, I mean, like I think we are planning to like use these like video models to release more 3D products.
All right. Yeah. Thank you.
Congratulations for your great talk, and all the demos are pretty amazing. So I have one question. So I will assume Dream Machine will using 3D models like NeRF or 3D GS. So can you give more details about how do you do text to 3D? Like do you firstly using like text to video to generate video, then transform to 3D, or like you directly generate 3D parameters like
Gaussian splatting, you directly generate the Gaussian points. Like is it in an end-to-end model or like separate? Oh, that would be great if you give me more details.
Yeah, I mean, I think this is not entirely resolved, but the Cat3D approach or something like this, maybe like where you fine tune on just 3D multi-view data after training on lots of videos. Something like this could be.
Okay, cool, thanks.
Hi, yeah, thanks for the talk. So I guess I'm still trying to understand what is the differentiator here in terms of other video diffusion models. Like, I couldn't understand where the 3D part was involved. If you can elaborate a bit on that. Like while creating the 3D, like the Dream Machine, what?
I mean, I don't think you need the 3D for Dream Machine. Like, I'm just trying to say, like, you need something like this for 3D.
Okay.
And then, like, in the case of most of the other models, like, currently, I don't think the public can access them. And like, I guess we have to build it ourselves for.
Thank you.
Okay, so let's thank Alex again. And this was the last talk of this session. We will continue with the poster session that's happening right next door, and we come back at 4:30 for the last session of the workshop. Thank you.
No, no, per carità, però a quel punto puoi andare a parlarne. Non so, mi sembra.
我也没说啥坏话呀。
So I should present the Zoom. So can I start sharing? Okay. it's
Yeah.
already on.
It looks like it's mirroring your screen. I don't know.
That's okay.
All right, hello everyone. We're going to get started with the last talk of the day here for the workshop on AI for 3D generation. Our grand finale is Sergey Tulyakov, who is a principal research scientist at Snap Research, where he also heads the creative vision team. In general, his work focuses on creating methods for manipulating the world via computer vision and machine learning. And he was really an early trailblazer in problems like animated 2D images, video generation, and motion retargeting. And Sergey has also worked on generative models for 3D objects and scenes, especially focused on controllability. So I think it'd be a great talk to wrap up the day. With that, I'll let you get started.
Thanks, Davis. So yeah, I mean, it took me some time, to find this room. Also, it's a pretty big room, but I mean, I went in the book, it was written in the other building, so got some exercise. Anyway, so very excited to talk here today, and I imagine this is the last talk of the day and people are tired, so I'll try to add maybe a bit of a humor somewhere, so please laugh, it will make me feel better. So, we talk today about generation of 2D, generation of 3D, generation of 4D. I don't know if we can generate 5D, but maybe if we look into the past, have people generated 3D in the past, or is it something very recent that happened this year in computer vision community and graphics? And so the answer is clearly no. People have been doing lots of things with 3D. And maybe here we just quickly go through like some generations of 3D in the past. So the first ever 3D, sculpture or generation that I was able to find is this Venus. So it's essentially a pebble found on a beach somewhere. And there are traces of human processing on it. And you can see that humans were really not skilled at doing that. And also it's a woman. And if you don't recognize that it's a woman, maybe there are many reasons. It's very old. And also maybe people were not skilled, or people looked differently back then or wanted to look different. So then we have this, which is roughly 40,000 years ago. And this is not yet a Spider-Man, but it's already a Lion Man. And this one is interesting because it adds some creativity to the process, combining some two different entities like a lion and a man, and also you see better fidelity. Also, it survived 40,000 years and still looks okay. And then maybe 800 years ago, we see some pottery, and this is much more developed. And also, this one had some use. It was useful for some daily life, maybe. And we arrive at the pinnacle of Renaissance art, which is considered one of the most notable statues, and everyone knows about it. And people are probably, we cannot do better than this even today. And so these were generations or some sort of 3D sculptures, and how they were created. Clearly, they didn't have generative networks. The tools were quite primitive. And for the pebble, to create a pebble, you actually maybe used another pebble to create this pebble. Then for the Lion Man, maybe the tools were a bit more advanced and developed. And then to do the pottery, you need a pottery wheel, which is already a quite sophisticated device. And finally, to do to have a statue done, you actually need not only skill, but also you have to have a lot of experience, training, and some talent. And so this clearly shows that 3D creation has seen a really great development in the last couple, like 250,000 years. How does it look today? And today it seems to be simple. So this video supposedly shows that, hey, learning Blender in just 30 minutes. I made this video 60 times faster to show you that it's really simple, it's nothing particularly you can do. So you move things here and there, you just create some stuff. So, well, in fact, what I want to say with this video that it's actually not so easy, and you still need to have a lot of experience. And after you spend all this time, you get this. I mean, I have nothing against that, but maybe you can do something better than this. And still, it was just 30 minutes of Blender. And to get something more creative, you need to spend probably way more time. But the good thing is that it doesn't have to be that hard. And today, with the advantages that or advances that we have with generative AI technology or generative modeling, we can generate from images to 3D. We can go from text to 3D. We can go from text to 4D. If we have a scene, we can texturize or have an object, we can texturize it easily, and it looks really good. So creating something like that would take some time if you know Photoshop, and if you don't know, it probably will take forever. Then we can also manipulate different rooms. So for example, here, this is actually a CVPR paper that will be presented at the main conference. So you can, with just a prompt, generate the texture for the entire room. And so how did this become possible? So there are a couple of things that happened roughly at the same time. The first thing that happened was neural radiance field. And what happened there and why is it important is that there were graphics, there was vision, there was machine learning. And now with the use of neural radiance field, they are all combined together, and people from different fields can, introduce methods from graphics to ML and vice versa. So that's one thing. And, I want you to really understand how things work. So I show you this example, how NeRF can be understood. So you can consider NeRF as two things. One is learning the volume, which is the laser on the right, on the left, according to, if you look from there. So the laser leaves some footprint in the volume, which is some neural rendering that you trace the rays and learn what's the radiance in that point. And then when the volume is ready, you can rotate it from different ways and generate novel views, which is on the right. I think it's a cool example I use sometimes when I show what's NeRFs to kids, In the meantime, a lot of stuff happened in the generative domain, and from first GANs and W GANs, we got progressive GANs. And at this point, 6 years ago, you cannot really tell if this face is real or if this face is generated. And then roughly in 2019, two parallel tracks started. One was with diffusion models, one was with style GAN, and fortunately or unfortunately, there is no more. Well, there are some GANs, but not too many. So, and from 2020, we have diffusion. And beyond, maybe we'll have autoregressive models, but what I want to say here is that there was a tremendous progress done in generative domain, combined with advances in the 3D domain. But then these things appeared, and these things are trained on huge amounts of data, billions and billions of images from the internet. And this is really exciting. The question is, are we able to do something like that for 3D or maybe even for 4D? And to get the answer, let's look at the data or lack of the data. So there is really a lot of data in 2D in videos, and it's extremely simple to take your phone and take a picture of you nice, wonderful people. But if I want to reconstruct this entire thing in 3D, it's not possible because I first don't see what's behind you. So I can do depth, but getting 3D is hardly possible. And so that's why we have, we have large 3D data sets such as Objaverse, or we have some multi-view data sets, but these are orders of magnitude lower than the number of objects there is lower than in any good 2D or video data set because of the difficulty of creating 3D. So we can maybe assume that civilization hasn't just created enough 3D data. So there's just not enough data. And maybe the path to 3D and 4D generation, maybe it lies through the valley of 2D generation. And I think in the last year, this was discussed at CVPR, and this year we see a lot of evidence. So how about this? This is DreamBooth, and DreamBooth has capabilities that are quite interesting from the 3D standpoint. You can take images that are on the left, And you can fine tune your model so that it can generate this object. And then you provide some prompting, and it seems that it can generate this object from viewpoints that haven't been seen in those images. And the question is, can we use these capabilities for 3D and 4D generation? So maybe just think about it. If diffusion model was trained on all the images that exist in the world, it have seen your cat from behind. It has seen everything. So, and we saw many works like, for example, Dream Fusion that can do this. They introduce a score distillation sampling loss that can reuse the gradients of the denoising process and generate images, or sorry, generate 3D objects. And this is a very exciting work because first, it doesn't use any 3D, just 3D representation to generate 3D, and then use 2D images. And there are, of course, some problems with this. First, there is Janus. This is a Greek god Janus. If you don't know, he has two faces. This squirrel has more problem. It has three faces, and that's called like a Janus problem for those non-3D aware 3D generation methods. And there is another problem that generation is actually pretty slow. So it's 30 minutes per object. So, you know, you type your prompt, you get a coffee, maybe another coffee, and maybe after that another coffee, maybe a couple of more coffee, and then you get the squirrel with three faces, and then you need to do it again. So, I mean, it's very exciting, but we probably can do better. And so some of the works that appeared in the community was this interest in Instance 3D. For example, they diffuse 4 views at the same time. And so to train this model, they require multi-view data. So how can they get it? They take this existing dataset Observerse that they can render from multiple views, and then can take a pre-trained diffusion model and fine-tune it to generate these 4 views. So it still uses a lot of prior from 2D training, but it also uses something from the 3D, and then it doesn't have these issues with Janus problem. And then the second step is to take these 4 views and reconstruct 3D out of those 4 views, which can be done through, you know, take these 4 views, run a transformer or any other model that reconstructs you some sort of triplanes. Then you can do volumetric rendering, and that works. And recently, I think we just submitted this to arXiv last week. We introduced a work called GTR, which improves geometry and texture through refinement. And I will just show some, you know, some ideas. Clearly, the paper has many more of them. But we take not only the images, but we also take the masks and also rays encoded as Plucker coordinates. You see those rainbowish kind of maps. And we can train a large transformer, relatively large, and learn some triplane tokens, reconstruct high-resolution triplanes, and decode them into differentiable meshes. And through this, we can also use some 3D data to fine-tune and train this approach. And we saw that we can just from a couple of images, we can have much improved texture quality and geometry quality. So what's interesting, you see the scan, and on this scan, you see that you actually see what's written on the texture, which is a difficult problem. And it can also go from just one single image. These images on the left were generated by a diffusion model, and then we can lift them to 3D space with high resolution. So, you know, this advances, and I'm going to announce something like that. So I think it's tomorrow that Snap will release SnapML Kit, where you could generate different meshes from prompts and use them. Well, hopefully you will use them in Snapchat, but probably maybe there are ways to use them somewhere else. And then these are some of the examples that we can get. So it's just from one image or from text. So it seems that 3D creation has become simple. Maybe it's still not very good. Maybe we still have a long way to go, but it's already, you know, not like a couple of years. or not 30 minutes to learn Blender. So now one can say, okay, cool. How about scenes? Can we generate scenes with different objects as easy as we are generating objects? Clearly, since I asked this question, the answer should be yes. And if you check out this work, this is also a CVPR paper this year. This work can generate different scenes with different objects. And not only that, it can move objects around. It can add objects to the scene. It can be different number of objects. So how does it work? And here I will go a little bit more deeper in detail, so bear with me. I know it's late, so I'll try to make it quick. So we have a prompt. For example, we want to generate a scene, and there are a couple of things we can do. For example, we can say an astronaut in space, and then there are two ways we can get a mesh. We can, use an LLM that will understand that the prompt contains this kind of objects, and it will extract those objects, and then we can use a 3D generator to generate those objects. For example, if we have a bed and a chair, we can use LLM to understand that the prompt requires us to generate a bed or a chair. And then, or the user can provide a bed or a chair. So it can be either generated or it can be provided by the user, so it allows for some flexibility. So then we can represent this bed or a chair as signed distance functions. And now the question is, we want to put them in some context. So we have a hybrid representation here. So chair and a bed are represented as SDF, so explicitly, or can be extracted meshes, while environment is represented as a radiance field. And so what we want to do there, we want to find good places for those objects in this environment. Assume we can do this, and if we can, then we can train this system by using, we can generate an images and backprobe through depth models, through some diffusion models, or through some perception losses. We also fine-tuned a panoramic RGBD model to train it. But the key question: how do we generate layouts? So this is really difficult, and I will go a bit deeper in detail here. So layouts are difficult. So what we can do, we need to find size, rotation, position for each foreground object. So what we can do, we can put an object somewhere in the scene, and then we can try to maximize clip similarity or clip score between the rendered images and the text prompt that we used. So how to do this? We can use backpropagation to do that. So we can optimize the parameters of the layout using clip similarity. And so a simpler case of that is quite interesting. So imagine we have this plate, and we want to change the position of the burger so that it dropped into the plate. Or similarly, we can get glasses and try to optimize the position of the glasses so that they get where they should. So if we compute clip similarity, we see that the most heat map position of where they should be is actually located in the plate or near the eyes. But if we do gradient descent or backprop, we see that it kind of diverges, so it doesn't work. So that's because optimization landscape is non-trivial and has multiple minima, and so it's very hard to optimize. So what do we do? So, these days is all about deep learning things from the data. So we might have forgotten some of the old school stuff, but think about this. This might be very well a landscape that we want to optimize. It has multiple minima, and depending where you initialize, you will get into different place. How about some more old school methods? For example, particle swarm optimization. So this is our global minimum. This is where we want to get. And so this is our cost function from the top. So what we can do, we can initialize randomly multiple points in this location. And for each point, we also have direction. So we have location, direction, and speed. So these points move. And we randomly initialize the location, direction, and speed. So the next step, we analyze those points and find the one that has the lowest loss. So what we do then, we update all the particles such that they try to get into this best position that we have just identified. And then we run another step and we see that particles currently converge to better location, and we find even better location. So we do these iterations a couple of times and we see that we arrived at convergence. So this is a relatively simple algorithm that has been forgotten maybe, but if you look how it looks, it's actually like that, and it's quite efficient. And why it is called particle swarm optimization, I hope this image, this video gives you an idea. So actually birds do something like that. It's not only birds, it's also fishes, but I didn't find a good image with fish. So now this happens if you do gradient descent, and this happens if you do particle swarm optimization. So we can put a burger where it belongs, on a plate. And so we can do this in 3D. And now we can generate diverse styles. We can generate different rooms. It depends on what you train. So we can generate all sorts of things. Different styles. We can also move objects, generate people, multiple different cars. But you can say, all right, but it's not realistic. Now I have a question. If you were, not very tired and attended to my talk, you might have noticed that I showed these videos in the beginning. And how do you think I got it? How do you think I generated those videos? Clearly, it's not me doing these things. I have zero skills. And also, I'm not bold like this gentleman who is doing sculpting. But these are generated by a Snap Video model that is also a paper here at CUPR. So please stop by at our poster. And now you can say, but okay, how does this video generation, how it is related to 3D? And I'm very glad you asked that because I have an answer. So you could actually provide a prompt, which would be a camera rotates around an object and you get a very nice 3D and very consistent. And so the question is, can we use this to generate 4D, which would be a volumetric video? And since I asked this question clearly, there is also an answer. And imagine this is video generated. This is a bulldog wearing a parrot's hat, eating candy generated by Snap Video. And now with our recent work that was, I think on arXiv last week, we can generate this thing happening from multiple views. And you would ask why and how. It's a Gaussian splat representation. So we can generate, this is where I show just a Gaussian splat representation for one frame. So it's not, this one is not dynamic, but there are many frames like that. And in the same way, like we became experts on nerves after seeing this slide, I want you to become experts in Gaussian splats by seeing this one. So a gentle introduction to Gaussian splats. So this is a triangle, right? This is a key element of graphics. This is a Gaussian. These are 3 Gaussians. These are 7 million Gaussians. And these are 7 million Gaussians rendered using all the parameters such as opacity, scale, and also other tricks that are used in Gaussian splats. So now when we're experts in Gaussian splats, we can a bit move forward. So I want to maybe first explain a bit how Snap Video works. So in Snap Video, it's a cascaded model. It has 2 cascades. One generates videos at low resolution. The second one generates videos at high resolution. So imagine we have a prompt. We say 2 pandas sitting at a table playing cards and blah, 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 and a lot of other prompt-based engineering. So we pick a frame. Take this frame, and use Snap Video to generate a different video. We take the frame and ask Snap Video to generate a video in which camera will be circling around these 2 pandas. This is what you get. It's a masked model, so it can do kind of conditional or masked generation. Then we can upsample all this stuff. So when we upsample this stuff, we get higher resolution, we upsample the frame, and also upsample this somewhat supposed to be freeze time video. But you can see that it's not freeze time. It has still some movement there. So we want to ideally decompose the movement of the camera from the movement of the object. But you can still see that there is some movement. So how do we build Gaussian splats on top of that? And also these are 4-dimensional Gaussian splats. So we have freeze time video and we have reference video. So in freeze time video, we have camera moving around an object, but we assume that the object is not moving, although it's not true. The object is still moving, but just a little bit. And in the reference video, we have camera which is fixed, but the object is moving. So what we can do, first thing we can fit some per frame deformations that we can optimize. We know the camera poses because we can run some sort of call map. Call map is still not accurate on those videos because there are some inconsistencies. So we also need to optimize slightly the camera poses. And this gives us canonical 3D Gaussian splats. And then given we have a reference video, so we can now do the motion part. So we have a reference camera, the reference camera doesn't move. So we know that whatever happens in that video is related to motion. And then we can learn temporal deformations here. So then how to train this, we can apply, temporal and multi-view SDS loss. So in temporal multi-view SDS loss, we assume that the camera is fixed and we sample different time. In multi-view SDS loss, we sample the camera and fix the time. So, and we can do this to learn canonical Gaussian splats and temporal deformations. So this is how we get 4D splats. So we have canonical 3D splats and temporal deformations. And now we can generate multi-view for different time steps. For example, you can see that this baby is at different stage of eating the ice cream. So on one frame, the mouse is open, on the other one is closed. So they're different time and we can render it from different viewpoints. Also, we can kind of choose two cameras and change the time basically and play the video. So we are generating multi-view videos in that sense. So there are many more we can generate. This is, for example, a blue monster is reading a book. And these are two, raccoons on Times Square reading a book or something like that. What's interesting that it works actually with several objects because it's a bit difficult. And then if you wanted, to see how an alligator playing drums looks from different viewpoints, you can do this. If you wanted to have corgi playing with a ball, or panda eating ice cream, or your favorite flower growing, you can now do this. And maybe one other point I wanted to make is that, 4D generation is not a new topic. And what interesting enough, so we have another paper here at CVPR, which is called 4DFI, and we compare here at 4DFI. An interesting thing here is that, papers, before they even presented, they can get outdated before they even were presented because our field moves so fast. But that's also a very exciting time to live in. And maybe, I have convinced you in this talk that, 3D and 4D generation is not a new thing. People have been doing this even 250,000 years ago. So nothing is novel. So reviewers too is right. And then maybe the road to generating 3D and 4D lies through reusing the priors, the rich priors used in learned by 2D image and video models. And I think with this, I think that's the last slide. We have time, can take some questions.
All right, thanks for the talk. If anyone has questions, you can ask at the microphone there. We've got time for a few.
Thanks, Sergey, for the talk. Regarding the for real work, it's based on a video diffusion model, I guess, right?
That's right.
Could you elaborate a bit on how that was trained?
How video diffusion was
Yeah.
trained. Well, there is a poster session, I don't know which day, but essentially is a large 4 billion parameters transformer model
I see.
that generates realistic videos that we built at the time of submission.
And just a follow-up question. So I think for real is basically adding on top of that so that you can create some consistent 4D videos from that.
That's correct. But the way you say it sounds simple, and it was
No, no,
pretty
no.
hard to do. Yeah.
But that's really amazing. Like, thanks
yeah.
for that, bro.
I mean, yeah, this this is pretty hard to do. The question is, how do we build methods that can reuse the rich prior? And it takes some time. Yeah, please.
Yeah, I had a question about using diffusion to do 3D and 4D editing, because like in this case, we kind of saw generation. And I feel like there are like 2 research lines right now, like doing generation and like doing editing. And like, I'm kind of saying that doing the editing is like kind of harder in a way to do, because like getting the multi-view of the editing is like kind of more difficult than for the generation. It's like, are you trying to kind of go into also the editing 3D stuff using like diffusion models, or is like?
So what would you call editing? Would animation be editing?
I mean, let's say I have a table and I want like to change the texture of it, or like add something on top of it without like kind of losing the meaning of the scene, right? Like not generating something that is different, but it's like I want just to change it in a way.
And just the table, not the rest of the scene. Yeah, that's a very good question. I think and people have done a lot of work showing how to do this in images and in 3D using diffusion models. We haven't done it for videos and for 4D. I mean, not sure if it's possible. I think it's possible. It's just maybe hard, and someone needs to see how to do it. But I think that eventually, I'm a big believer that maybe there will be just a video generation model, and it will be able to do everything.
Okay, thank you.
Yeah.
Yeah, great talk. I just have one sort of detail-oriented question, but why only generate the multi-view video of the scene from one of your frames? Yeah, was there a reason, or?
You're asking what would be the alternative?
I mean, generate it from every frame or multiple frames to sort of like ensure, like, what if you you're kind of picking a canonical frame to generate a 3D scene from? What if that's, yeah, I mean.
So, I mean, it looks like that. So you have, imagine you represent space and time as a matrix, right? And you go from a first frame to the last frame, you go down and your camera doesn't change, but the time changes, right? And when you go to the right or to the left, according to where you're standing, you change the camera, but don't change time, right?
Yeah.
But you can start at any time frame and you can use the full matrix. While what we explored only kind of the column and some row. There is no real reason why we couldn't explore the entire matrix. I mean, maybe the reason is that, you know, there is always that much time before deadline. And also, I mean, we should leave some room for future work.
Yeah, sounds great. Thanks.
Yeah.
Great presentation. Thank you. I have one question. So what do you feel is the most challenging when we go from 2D generation to 3D and 4D? Is it come from the data set part or the model design part of the real-time inference part? How do you feel
So
about
this is not real time, so clearly this is optimization based, so it's pretty slow. It's roughly, I think, 1.5 hours per scene. So it's pretty slow. We can make it faster. I think just maintaining the quality is pretty hard because certain aspects can be considered, like if things moved, is it because of the camera or is it because of the object? So was that motion caused by like that I just move my hand, or it's just a new perspective? And I think this ambiguity is actually a different one, and we're not the first to see it. It has been always like that, how to decompose style from content, how to decompose albedo from shading, how to decompose like motion and and the scene. So I think this is probably difficult, and as diffusion models become better, I think this will go away, and then we'll see probably other problems that we don't see right now.
Okay, thank you.
Yeah.
Thank you.
All right. Well, hope you that you made it till the end of the day, you know? Yeah.
Okay, let's thank Sergey once again. Yeah, so that concludes the workshop. Thanks everyone for being here. We'll have the presentations up on the website eventually, and hopefully some slides too. But yeah, thanks all for making it a great day.
Yeah.